Good morning, everyone. I hope you enjoyed the ARC 15 conference yesterday, and we'd like to welcome you all today to a new day, a new session. And we'll be starting with a session today. And for this, I would like to request Professor Dr. Suichi Hasegawa to be the chair of the session. And also, I would like to welcome Mohammad Nazwanul Haq and Anil Kumar Chowdhury to co-chair the session. The floor is yours, sir.
Thank you. Good morning. Namaste, dear all. Thank you very much for gathering keynote session. I am Shuichi Hasegawa of Kaga University, Japan. I will chair this session, and co-chairperson is.
Thank you, everybody, and good morning. I'm Najwanul Haq. I am with Sir as a co-chairperson. Thank you.
Another co-chairman is now coming on the way to the hall. So let's start. We have 6 keynotes presentation. Each presentation time is 30 minutes. First language after 20 minutes, and before 5 minutes before the end of presentation, 2 rings. First keynote speaker is Dr. Ann Williams. Please. Her title is Climate Change, Closing the Gap Between Challenges Faced by Developing and Developed Countries. Please.
Thank you very much. Right, so when I started preparing for this talk, I was thinking about all the headlines that we have seen over the last couple of years of extreme flooding and unprecedented landslide activity and so forth, whether it be Switzerland or China, the US, Bangladesh, and of course Kathmandu and Nepal and Auckland, New Zealand. So I thought I would compare Nepal and New Zealand. We have a lot in common. New Zealand straddles an active plate boundary and has mountain uplift, and Nepal has a main thrust system going through it, which also generates mountain uplift and lots of seismicity. We have steep, high country. Nepal is subject to the monsoon and also glacial melt in terms of generating landslides. New Zealand has a big coastline, which Nepal does not, and this means we're subject to tropical cyclones. Also, we have a mountain system which forms a barrier and results in a lot of dumping of rain in a single area. So we have a lot in common. I also learnt yesterday that Nepal has some 100,000 kilometres of road, and we have about 95 or 96,000. So again, another similarity, and we'll be talking a bit about highways. I wanted to share first with you this little video clip. It's from the BBC. Where's the sound
stand a chance. This weekend, 9 inches of rain fell on Nepal's capital, the worst downpour since 1970. Parts of this city of 1.5 million people have been wrecked. As well as the army, every policeman and woman in the country has been ordered to join the rescue. More than 3,000 people have been brought to safety. Where the water was too dangerous for a boat, rescue was by zipline. The annual monsoon rains usually end in mid-September, but respite is several weeks late. And people say these floods are more extreme than in previous seasons. In this valley west of Kathmandu, the downpour triggered a lethal landslide. Families watched, hoping the rescue teams would find their loved ones alive, but mostly it was bodies they found in the mud. The death toll's likely to rise as more than 40 people are missing. Major motorways connecting Kathmandu with the rest of the country are impassable. due to landslides and damaged bridges.
And so that's Kathmandu, where we are right now. And it's not so different from something that happened in Auckland in 2023, which is my hometown. Again, have we got the sound? No sound, so we'll have to guess, but you can see what's going on. Again, there's talk of unprecedented rainfall. This has never happened before.
Attached to this home swiftly carried off with the land underneath it.
Holy shit. I think we've got to go. Yeah. I think we have to go.
Buses were submerged, left floating or filled. Roads became fast-moving rivers in a matter of minutes. Rendering cars useless, many abandoned in the street. As more and more homes across the city filled with water.
I'll power into it now.
So too did businesses, supermarket groceries floating down aisles. And as buildings like the Titirangi Coast Guard toppled over, collapsing in the wet, it became clear from Dominion Road to Eden Park, in Coatesville, the CBD, and out south, Auckland had been plunged underwater.
So this extreme rainfall generated significant landsliding, and this is one that was particularly significant because it cut off one side of our Coromandel Peninsula from the other, so it meant that Aucklanders who wanted to go to their holiday homes had to drive an extra 2 or 3 hours, but also tourists were not able to access the most popular part of the Coromandel at the most popular holiday season. And this has a significant impact on our finances, on our GDP. It's a 100-metre or so section of road that was lost. And as you can imagine, challenging to go around, challenging to go below. That was a single landslide, and you perhaps could have predicted where it might have occurred. There had been prior movement, but the problem now with climate change is we're seeing just ubiquitous landsliding. It covers huge areas, so how do we anticipate where we need to put our attention? I'm going to run you very quickly through a trip across New Zealand where we have had a number of significant events. And so I've ringed in the north. I don't think the pointer works, so in the blue circle in the north is Auckland, that's where I live. There's a purple dash just to the lower right, which is the Coromandel being cut off. The big orange ring on the right is the Hawke's Bay area, significantly damaged. The blue spot in the middle is the top of the South Island, the Marlborough region, and finally the red spot in the bottom is the Canterbury region where the earthquakes have occurred recent times. This slide just shows I guess the most important is that the number of these earthquakes that have occurred in New Zealand over recent times and now flooding have a significant toll on the bottom line, if you like, on our economics. So you can see that the Canterbury earthquakes in 2011 caused about $15 to $20 billion of damage. And second to that is the hail cyclone Gabrielle, so this rainfall and landsliding damage that occurred 2023. This is a quote from insurers, not surprisingly. In a world experiencing climate change, population growth, and economic and geopolitical uncertainty, the risk environment is the highest we've faced in a generation. And so in New Zealand, we've had more than 600 fatalities from landslides in the last 160 years, so that's the length of our record. And those fatalities are more than have occurred from our earthquakes over that same period. And the average landslide cost to the country is in the order of $250 to $300 million each year. And there's a translation for those of you who are not familiar with New Zealand dollars, which is about 0.7% of GDP on average. But if you look over just the last 20 years, it's 4.3% of our GDP. And this sort of drives how we're going to respond to these events, how we think about them. So the Cyclone Gabrielle event that resulted in the flooding of the video was not actually a single event. There were a series of quite serious storms from July 2022 right through to January and then February when Cyclone Hale impacted Auckland and the anniversary day storms which impacted the Coromandel region, and then February, the Cyclone Gabrielle event itself, which significantly impacted the Hawke's Bay. And if you look at the cumulative rainfall, if we look first at Auckland, you can see the average band of rainfall there and what happened in 2023. It's just unprecedented. So the highest single day rainfall previously was recorded in 1985 at 160 odd mils. And on anniversary weekend, we had 246 mils in a single day. And that's why it resulted in such significant events. And I guess the graph on the right shows that the world is just getting warmer at an increasing rate. So in Auckland, there were these multiple extreme rainfall events. There were significant infrastructure outages. It really highlighted some of the interdependencies between infrastructure networks and called into question our resilience. Just a couple more images of Auckland anniversary flooding. What we didn't show you, the bottom left, there were evacuations in the CBD. This is a theatre complex. And on the right, our international airport was underwater, which is just unprecedented. I never imagined this would happen in my city. And perhaps more importantly, on the west coast, there was significant landsliding, which resulted in some deaths. A lot of people lost their homes, and the regional council was called to respond, which they've done by extensive mapping, understanding the mechanisms of failure, and then working through which homes need to be abandoned and which can be perhaps protected. What it has resulted in is a landslide susceptibility mapping tool, which is available to anyone online so that they can start to think about where they are developing, so that the community has some ownership and some opportunity to take some decisions itself. Now, I'll talk just a little bit about the slip that I showed you the video of, which cut off the Coromandel, as you can see in the top right corner. The media had quite an important role in this one. The Transport Agency was smart because they posted on LinkedIn and in a whole lot of different media, newspapers and so forth, local literature, to show images of how severe this was so that people's expectations were not that this road would be passable soon. In fact, people were expecting that this would take quite some time to repair. But it was repaired in 7 months, so an absolute record period of time. And how did we achieve this? Well, really the key here, I think, was recognizing that the time taken was more important than the cost of the solution. And so the government agreeing to cover the cost of the solution, whatever it might be, was really important in allowing things to just start moving. We were able to repurpose some bridge parts from another project, and as you can see in the red there, that speeding up the reopening increased tourism spend in the region by about 70 million and our GDP by almost 86 million. So the cost of the project was 50 million. And there you can see what the benefits are of speed. In Hawke's Bay, there was significant damage, and I'll show you some images of that. But prior to that severe national emergency, we had these major earthquake events, and we had set up special vehicle alliances, partnerships involving government agencies, so our roading agency, rail agency, together with construction companies, to together work collaboratively and resolve and repair and recover from those events. And as you can see, the North Canterbury one, these involved huge amounts of people, 9,000 people, 350 organisations worked together in the North Canterbury Infrastructure Recovery Alliance. So the idea when the Hawke's Bay had its issues was to set up an alliance. It was going to be called TREC, Transport Rebuild East Coast. But as you can see, I've put up there phase 2 recovery, part of it, the later part, and phase 3 final rebuild. So what happened? There was just far too much talk, and the agency wasn't set up until a year after the damage. So by that time, the emergency response, all the phase 1 work had been undertaken by the road maintenance contract parties already. So those parties worked very quickly to work out that there were many similar slips that had occurred. If you're going to put a whole large number of people from different organisations out into the field to try and assess landslides, you need to have some common way of working. You need to be being able to communicate similar information readily. And so the idea of applying a standard design, applying a similar design detail to a whole lot of different slope problems became quite attractive, and also to involve the contractors in leading some of those designs so they can get started, check where the bedrock is and so forth, and then think about what materials they have available to them. And this is an example of, 4 similar situations and a couple of standard designs that the contractors could choose from. Of course, you don't just say, contractor, go off and build this. It's really important that a brief desktop study has still been undertaken so that the mechanism is understood, that you check that the standard design fits the profile, and that there are any site-specific details agreed at the outset. And then, of course, the engineering geologist, geotech engineer, comes along frequently to observe. So what did we learn? Well, there's a difference in the needs between a new build and emergency works. You can probably get away with a little bit less rigor and detail because speed is of the essence. You need to reconnect these communities, and you need to be able to get aid workers in there. You need to be able to get people in there to repair things. Not all of these repairs stood the test of time. Some have had to be revisited already, but it did allow that immediate response. And now Marlborough. Marlborough, actually, the storms occurred a little bit earlier in 2021, and then followed by more significant rain in 2022. And it was at that point that they decided to set up a special vehicle, the Marlborough Roads Alliance. Again, you can see the first bar in that graph on the top right there, unprecedented rainfall compared to the average, which is the orange line. So the Marlborough Road story is a little bit different. There's a significant number of roads, but as you can see, they're quite narrow often and connecting rural communities. They've often just been constructed by, bulldozing along and side casting the fill, and they're over some historical landslides. So they're particularly vulnerable. The Marlborough Roads recovery team that was established was also the client, so the transport agency, but the district council as well in this case, contractors, and then they had a design hub model. So the designers were seconded in, and that's really important because it means that risk is no longer with the consultant, but it's with the collective. And that allows people to work with more speed. And it also allows this vehicle to be used frequently. So it was actually just redeployed in 2025 when flooding occurred a couple of months back by bringing in those secondees and then dropping them when they're no longer required. But there's also something else that we learned. So they have a really great tool, which is again online, Floodwatch. So anyone who's living in the region can go online, have a look at the river level, have a look at the flow, get a feeling for what is normal and what happens when it rains an awful lot. And so the team there, the consultants and the contractors, have a real sense of how much rainfall and at what levels they begin to get concerned about what might be going to happen. So during the event, they can see the rainfall, they can see hydrographs, you can look out the window and see where the flooding is getting to. But the team generally say that, if there's 40 to 60 mils of rainfall occurring on a few days in a row, they start to get alert and get in touch with each other. Then they note the river levels rising, and when they get around 150 to 200 mils cumulative rainfall, landslides tend to be set off. So we're almost predicting landslides and getting ready to respond. It also allows the local community to prepare, to have resources, to evacuate and so forth on their own. So a local collaborative response team can be scaled, works really well. Using local knowledge from people in previous events is helpful. It allows us to predict what might be going to happen. We can make use of all of that data. The important other thing here was risk acceptance. Risk level of repairs was aligned with adjacent sections of road, because oftentimes we try to repair, and actually this example in the bottom right, to a standard that is much higher than the adjacent pieces of road, but there's not really a lot of point in having one stable section and it then can fail on either side. So your resources may be better spent maintaining a road opening. So what else came out of these events? Well, we now have a online New Zealand landslides database, again accessible to everybody. It's a public reporting tool, so you can submit your information about observations of landslides as well. So it contains a lot of detail that consultants and contractors can use to inform their decision making too. And there's now a manual on standardisation of designs. So this is generated in response to the Cyclone Gabrielle, recognising that standard designs have a real place going forward, and it's all about cost. So I've asked at the bottom, is standardisation the new innovation? In summary, landslides are increasingly so widespread that I think a different response is needed from in the past. Our response needs to be managed through processes that can deal with decision making under deep uncertainty. So scenario testing, contractor-led designs, but with designer observation. Standard designs or design details can be applied across road corridors. You need to have similar geology, right? Tools that give local communities and local consultants and contractors the information to prepare and respond are invaluable. These are the tools that save lives. Response entities should be established, and I've said, in peacetime. So this was a real learning from the Trek experience, that we need to establish these entities now, before the flood and event occurs. Once it's occurred, it's really difficult to get something that's going to work and be commercially viable. And a whole system approach is needed. So do we need to design all of our roads to the same standards? What are the key routes? We need to think about these things ahead of time rather than when we're in the moment trying to respond. Asking ourselves the questions, what level of service will we accept? And should a repair be designed to a higher standard than the adjacent infrastructure? And my final comment is, this is a global issue and we need to learn from each other. Thank you. I do want to acknowledge my co-authors, and I think Christoph Kraus is somewhere here. He's been on the ground responding to these events, as well as my colleagues, partners, clients, and stakeholders. Thank you.
It's a very wonderful, nice presentation. I think that disaster is a father of innovation. So I learned from your presentation. Thank you. The second speaker is Keijian Albert Shaw, Professor Keijian Albert Shaw from Taiwan. His title is On the Catchment Sedimentation and Landslide Induced by 1999 Taiwan Chichi Earthquake. Please.
Okay, thank you, Mr. Chairman. As you can see, the title of my presentation is on the catchment sedimentation and the landslide in Dajia River. It's one of the major rivers in Taiwan, and I'm focusing on the behavior of the sedimentation and landslide in this river with the impact of Chichi earthquake. I would like to acknowledge the funding from the National Science Council of Taiwan, and also the contribution of my graduate students, and also the data from different government sectors, and also from other research groups. Okay, this is the structure I'm going to present. Introduction followed by the analysis of landslide and the sedimentation and the correlation between those two topics, and finally a brief discussion and conclusion will be given. Before I go into the details, I would like to show you a few pictures. If you look at the pictures on the left-hand side, actually this is an image in the hot spring spot called the Guguan Village. And you can see a suspension bridge crossing the river. The other side of the river, you can see a structure more like a temple. Actually, that's a portal of the tail race tunnel of Guguan Power Station. So the underground power station is inside this portal. As you can see, before the Chichi earthquake, if you look at the lower left picture, you can see actually there are two portals below the suspension bridge. So it should be, the riverbed should be like this. But if you look at the image in the middle, it's totally covered by the sediment. The elevation, the difference of elevation is more than 20 meters. So that caused a lot of problem. So this is the only one site have this kind of problem. Not only the portal of the tail race tunnel, but also the portal of the headrest tunnel in other power stations have a similar problem. So along this river, we have at least 4 underground power stations. So each power station, underground power station, have different problems. Some of the power stations flooded by water. Some of the power stations is flooded by sediment. So need a lot of work to fix or rehab, or just, tear down and build a new one. But the most difficult thing for the rehab is to find a new portal, where the new portal should be located. We not only have to consider the geologic condition, but also you have to consider the changing of the riverbed. because you can see on the right top figure is the current situation. The sediment has been transported by the river in past 25 years. So the riverbed can be changed. So when we do the rehabilitation, you can see on the right lower figure, it's the most difficult thing is not fixing the generator. It's to find the right location for the new portal. You have a lot of things you have to consider. But I think this more or less related to the engineering geology. So it's very challenging. That's what I said. The challenges create the opportunities. This is also kind of opportunities, but it's very difficult, very challenging. Okay, the second one, I would like to show you the impact of climate change. You can see those two figures shows the image of one of the largest reservoir in Taiwan, Deji, also along the Dajia River. You can see in May 2021, the capacity of the reservoir down to 1%, almost empty. At that time, we only provide the water 1 or 2 times a week. It's because we run out of water. But you can see 3 months later, the water get back to more than 90%. And this kind of situation never happened before. So this also shows because some scientists argue about the climate change, it's just a variation, not exist. But for us, it really has a strong impact to our life. But still, we as an engineer or scientist, we have to face the problem, solve the problem. Right? So no matter it's climate change or it's just a variation, we still have to face it. Okay. Okay. This is the statistics. You can see that the red line and the blue line is a regression line for the annual precipitation for past 100 years and the past 50 years. So you can see the regression line is almost the straight line, means not change too much. But you can see the rainy day right up figure reducing quite a bit. So that's why, as I mentioned in the opening remark, the rainfall is more concentrated, at least in Taiwan. It's like this. That causes the flooding, but also because this heavy rain is not distributed evenly, so cause flooding and a drought, like the previous one. No water in some watershed. Okay, so we have to build a lot of water diverting tunnel to manage the water between the watersheds. So this is the problem we have in Taiwan area. Okay, let's go back to the research. This research actually is funded by Water Resource Agency and also National Science Council. We try to study the behavior, as I said, behavior of the sedimentation and also landslide in this watershed. So especially after the Chichi earthquake. So what we did is we collect the data. We collect the rainfall data, collect the landslide data, and try to do some analysis. This is some of the results. You can see there are 4 major typhoon. Torachi is in 2001, Minduri is 2004, Sinlaku is 2008, Marak is 2009. We collected the data and try to do some analysis. You can see the left-hand side is the geology in these 3 watersheds, Dajia River, Wu River, and the Zhuoshui River. So we try to see whether there's a difference or not. Actually, they are differences because even the river mainly flowing from the east to the west, crossing the similar formation, but the behavior in the landslide is not the same. I think that could be due to the different river topography and also the rainfall distribution. so not exactly the same. So when we, do the management of the watershed, we have to understand the uncertainties, especially the major causative factors that could affect the behavior and the landslide behavior. Okay, those are some of the figures we collected and obtained, and those are the landslide distributions for different, after different landslide event. As I mentioned, there are 4 major events we try to understand. And then, actually, we wrote a paper based on the data and analysis. This is one major finding, is that we try to find the correlation between the landslide ratio and the accumulated rainfall for different typhoon event. And you can see for each watershed, we have 2 formulas. The modified means that we include the time factor. Time factor means that how much time this event happened. The time difference between the Chichi earthquake and the typhoon event. The longer the delta T means the impact of the earthquake is reducing, right? So by the modified formula, you can see we get a better correlation. Here I would like to comment on 2 things. By adding the time effect, this correlation is better. You get a better correlation. But also, from this extra time effect formula, ahead of that parenthesis, we can see that actually, I didn't show the detailed calculation, but it shows that the impact of the big earthquake, like Chichi earthquake, reduced by about 50% in about 3 years, and reduced to about 10% in about 10 years, based on the formula, y equal to the first parenthesis. But even you can see it is already more than 25 years after the Chichi earthquake. But the highway crossing the island, along this river, still not open to the public due to the rockfall hazard. So even though, based on the landslide analysis, it looks good, but still, randomly rockfall still, make the transportation unsafe. In other words, it is difficult to buy the insurance, so that even the government is dare not to, say, oh, we want to open to the public, because still, from time to time there's rockfall. So this also shows that the monitoring analysis for long-term period, especially after the big event, like a big typhoon or big earthquake, is necessary for a better management of the watershed for geohazard. So you can see from this event in this watershed, 25 years is still not enough to get it back. Even you have so many engineering method to control that, but still difficult. Okay. And then I would like to show you some of the details of this analysis. This is the geology. You can see due to the, I think most of you know that the tectonic setting of Taiwan Island. So the formation are mainly distributed in the north-south direction. The lineations also in this direction. So you can see those lineations are mainly in that direction, and also the boundary between different formations. And the formation, the west side is sedimentary, and to the east is more metamorphic. Okay. This is topography. And this is a statistic of the rainfall, the black back line, we should see to the y-axis in the left is the precipitation rainfall. Right-hand side, the earthquake magnitude. You can see there are two major earthquake events in this nearby area. So not too many. I think maybe the energy already released enough. So, the main impact to this to the geohazard in this area is rainfall, heavy rain. And this is the rainfall distribution. You can see different events have a different rainfall concentration in different areas. So that's also reveals something. So the behavior might not be the same in different sector, different watershed. And according to the landslide inventories and also the rainfall precipitation, we can summarize, get a brief summarize that the central sector, we call the second sector, between Guguan Dam and the Deji Dam is most critical area because heavy rain distributed in that area. Also heavy and also landslide inventory shows the similar trend. So we collect the because for the following analysis we need a lot of factors from the topography. So we collected the DTM, and also we either collect or we generate data layers for further analysis. As I said, we try to analyze the data due to the impact of 3 to 4 major typhoon that affect this area more seriously. So this is the boundary and the location of the dams. This is water system, river systems, and also the landslide and debris flow in different area and before and after different typhoon event. If you compare the image, slightly different, but you can see those black dot and red line are mainly distributed in the central part, right? As I said, between Guguan Dam and the Deji Dam. Okay, and we also try to classify the landslide to reactivated one and the newly developed one. Try to see this other clue to have a better analysis results or not. Okay, this is some of the summary. You can see the trend. You can see left-hand side. You can see the different typhoon event, different sector, and different type of landslide. You can see the behavior is changing because the typhoon Herb is in 1998. It's before 1996. It's before Chichi earthquake. You can see not much like strong landslide area distributed in this watershed, but you can see comparatively in Torachi, that's right after the Chichi earthquake. That happened in 2001. You can see the number jump up significantly, especially in the second sector, right? Both reacted one and also the newly generated one. Even to Minduli. Minduli happened in 2004, right? 3 years later. And even in Morocco in 2009, still the same, similar. Reduced a little bit, but still the same. Okay, so this is a short summary. The landslide concentrated in the segment 2. let's move on to the analysis of the sedimentation. The raw data was developed by another group, National Cheng Kung University, is a hydraulic engineering group. So we use their data for our analysis because we try to find the correlation between the causative factors for the sedimentation generation and the sedimentation transportation, and also the sedimentation behavior with the landslide, right? So this is the, again, this is a summary. You can see the third column is sedimentation generation, fourth column sediment deposition. You can see the behavior is different, right? For example, in Minduli typhoon, more sediment deposited in segment 1, not instead of segment 2, right? More generation happened in segment 2. So each segment have a different behavior. Some segment have more, accumulation. Some have more transportation. So behavior is changing. So that's why I said that long-term monitoring, long-term analysis is very critical for the management, proper management of the watershed. And so I think I almost run out of time. I would like to say one more thing. We try to find a correlation. So we try to develop like a derivative formula. It's actually it's an equilibrium equation for the sediment. But after derivation, we end up with this. So you can see the sediment deposition is function of sediment generation and the sediment transportation. So we introduce two independent index, and each independent index have as causative factors or control factors. Okay, this is the control factors for the sediment generation index. We have another one. This is the sediment transportation index. Also have control factors. We try to, try to establish this equation and train it and make it more mature, and then we can have a better idea about the behavior, considering the time and also the impact of the major event. So those are some of the results. So, so that's the idea. We keep collect the new data, try to have this like a logic or this two formulas more mature to make our index more reliable, useful. Okay. So a summary is that again the central part is still unstable, although the landslide reduced quite a bit, but still, as I said, maybe our analysis should focusing more on the rockfall because we didn't classify, to the details. Although one or two of my students try to classify shallow landslide and the deep city landslide in this area, but still, the rockfall is not properly analyzed. Still need to do more analysis in details. But for the sedimentation analysis, we found that sedimentation has a very close relationship with landslide. Okay, and right after the Chichi earthquake, you can see the sediment generation and also landslide, induced landslide is heavily distributed in segment 2, and also the trend is different in different segments, and also can be different in different watershed. Even they have a similar geography and geology, but I think the difference could be due to the river morphology. Okay. Okay. One last comment, as I would like to restate that again. For the watershed management, long-term management analysis based on updated data is very critical, very important. Okay, thank you very much for your attention.
Thank you very much, Albert. Yeah, it's a very interesting presentation. After the teacher's cake, the abnormal sedimentation continue. Oh, so long. This is a surprise for me. Thank you so much.
Okay, thank you.
Thank you. The third speaker is, keynote speaker is Dr. Daniel Jordan. Dr. Daniel Jordan is a senior researcher at Italian National Research Council, Institute of Hydrological Protection. Please.
Good morning, everybody.
Excuse me. Yeah, his title is Glacier Instabilities, Identification and Monitoring Case Study in the Alps.
So thank you very much for giving me the opportunity to present some results of our research activity. So I'm working in Torino, in the north of Italy, and I work at the Research Institute for Geohydrological Protection, and I'm the scientific coordinator of the GEASAR monitoring group, that is a research group that works mainly on the development of monitoring solution for slope instabilities. We work a lot of landslides, and we started more than 10 years ago working also on glacier instabilities. In this picture you see in blue the map of the Italian Alps glaciers, and I would like to first of all point it out that the scale of the Alps is different from the Himalayan scale. Okay, so what I will show you is something that belongs to the Alpine scale, okay, where the top of the mountain is Mont Blanc, that is 4,800 meters. Okay, so we are not close to the Everest, but on the opposite side, we are really much more close to glacier. We will see that the elemental risks are really close to the glacier, and that is why the glacier-related high-risk processes can be really dangerous. You know that this is just some examples. Okay, first of all, the ice avalanches. GLOF are a very dangerous process. Of course, debris flow, but also complex events. This the picture on the right low is a photo related to a rock ice avalanche occurred in 1997. What happened? In July 3, 2022, a huge ice avalanche with an estimated initial volume of 70,000 cubic meters failed from the Marmolada Glacier in the east of the Italian Alpine belt. You see the picture of the glacier before and after the failure, and unfortunately these ice and rock avalanche caused 11 fatalities. Okay, so this is a turning point in Italy. Okay, we are before Blatten, so before what happened this year in Switzerland. For us has been an important point because at the national scale, the Civil Protection Department activating a working group to reach the goal of the publication of guidelines for the management of glacier and pre-glacial related risk. This guideline has been developed since 2022. I'm in charge of part of these guidelines, and of course the approach is an approach that considers all the possible technological solutions, starting from satellite, but also for aerial, the use of drones and the use of terrestrial monitoring solution. The base of these guidelines is mainly based on the monitoring plan that has been developed in particular in the Aosta Valley, so in the northwest of Italy, in the last 15 years by the regional authority, Fondazione Montagna Sicura, and my office. So the idea of these guidelines is to define a procedure and following this procedure, making a first screening of glacier, define the activity of the glaciers, and then focus on the glacier that have a particular behavior that can create a dangerous condition. Only in that case we can decide to activate more technological solution that can be used to manage the area risk. This is the Italian side of the Mont Blanc chain. Okay, you see on the left the Mont Blanc, and on the right the Grand Joras part of the massif. In the red square you have the Grand Joras area, and inside the Grand Joras there are two different glaciers. There are hanging glaciers that are called Plainpensieux and Grand Joras glaciers. Why we started to study these glaciers, we will see in the next slide that at the base of the glacier we have the Ferre Valley, okay, that is one of the most touristic valley of the Aosta Valley, with people that come from every part of the world. So we have an incredible number of tourists during, in particular during the summer season, and we will see that we are really, really close to the glacier. So this is beautiful from one side, but it's also dangerous on the opposite side. We started to develop this open-air laboratory, working with the regional authority, and starting in 2009. And the regional authority invests more than €1 million during the time to develop probably one of the most advanced open-air laboratory for the development of new technological solution for glacier instability monitoring. Just to change the point of view, so these are the two glaciers that I presented before, Plainpensieux and Grand Joras, but this is a different point of view. So the point of view of glaciers, okay, you see the frontal part of the glacier, you also see the valley, the bottom of the valley that is really, really close, okay? It means that in a few seconds, more or less 15, 20 seconds, an ice avalanche can reach the bottom of the valley and can seriously damage or destroy all the elemental risk. Consider that in Plainpensieux village there are many, many hotels, camping, and during the summer season an incredible amount of people. In the two maps you see some simulation that highlights how these ice avalanches can reach the bottom of the valley, and this simulation also pointed out the presence, the interaction between the ice avalanche and several elemental risks. First of all, the road, but also the settlements, the camping, and the other structure built in the bottom of the valley. On the left, in the upper part, you see the Wimper Serac. Okay, we are at 4,000 meters. Okay, the steep is more than 40 degrees, so it's very, very steep. This is a cold glacier, and this is a glacier that is characterized by the activation of frequent big ice avalanches that can reach the bottom of the valley. So, in this presentation, I would like to show the procedure that we developed to identify the most critical glacier instabilities and using different technological solutions. Some of them we can consider low-cost solution, other no, are not cheap, but have a different level of performance. the main change is the frequency of acquisition. Okay, so we start with low acquisition. That means that we have the possibility to evaluate the yearly or seasonal evolution, and then we can move to weekly or daily, and we arrive to also systems that can react in a few seconds, that are used to manage the real-time alert system. Of course, we can start with satellite images. This is the map of the Mont Blanc area. Okay, you see all the mapped glaciers, and using Sentinel-2 images that are free of charge, we analyze not the yearly evolution of the glacier, but we analyze the monthly evolution of the glacier, starting to study how the glacier react and move more or less faster month per month in the last 10 years. And this has been really important because this analysis pointed out the presence of several glaciers that have a very, very different behavior with potential critical acceleration. So this is the screening base that we adopt to starting to classify glacier in one that have normal evolution and other that can have critical acceleration. Then, of course, we have to characterize from the morphological point of view, and the use of drones LiDAR can be a very, very useful solution to obtain very detailed digital terrain models. So this is the typical sequence of that starts with drone acquisition, and using the structure from motion, you can obtain a dense point cloud, the digital elevation model, and the orthophoto. And it is the base for geomorphological analysis, ultra-detailed geomorphological analysis of our case study. Then we move to, we are moving to more detailed analysis also in frequency, and we arrive to the use of camera. We worked in the last 10 years to the development of this system based of low-cost camera, because we think that this is very useful to have an idea of the daily evolution of the glacier. That is essential to have a characterization of the dynamic of the glacier, and to have a correct base for the identification of possible instabilities. We developed two different approaches. The monoscopic approach, that means that we have a single camera that is able to measure the component of the movement orthogonal to the line of sight, and the stereoscopic approach that is really, really more technological complex, that have the possibility to see the change of volume. So in this sequence of image, you see the movement of the glacier. Okay, so this is a sequence of the image acquired by the camera that is installed at more than 4 kilometers on the opposite side of the valley. Today, this camera is covered by more than 1 meter of snow. You see that in the plot there are 3 different lines that belongs to points in different position of the glacier, and you clearly see that this angle glacier is characterized by an increase of the velocity, and the direct correlation between the increase of velocity and the failure of big blocks from the frontal part. So, of course, if you don't have the possibility to have a daily acquisition of images, if you don't have the possibility to characterize the dynamic of the glacier, you are not able to understand the real evolution that is at the base for a full study of the risk related to the glacier activity. This is another example. We are in another glacier. Using a stereoscopic camera, we are not only able to see the movement of the glacier, but we are also able to see the volume change of the frontal part. And in this plot, we have the possibility to see the correlation between the volume change, that of course is related to the ice melting, and the temperature. So using this camera, we are able to measure the glacier that is moving in the direction of the camera. The frontal part is melting, and using the temperature, we are able to characterize the dynamic of the glacier and how the glacier is able to answer to external factors, in particular the temperature. This is a more complex approach. To using the stereoscopic approach, we have to develop an artificial intelligence code that is aimed to create the 3D volume for every hour. Okay, so every hour we have a new three-dimensional model, and we use it to follow the evolution of the frontal part of the glacier. Then, of course, we can adopt more technological solution. If we want to work at the Wimper-Serac, that is a really, really incredible environment. The video of the helicopter is made by myself during the last campaign. You see that this is the only horizontal space. There is not enough to land the helicopter, just to stop for a little bit and give the people the possibility to to reach the area. Okay, you also see how this hanging glacier is steep. Okay, and on this very, very steep glacier, we installed several prisms. Okay, that are measured by a robotized total station. So using this prism, that is a quite common monitoring solution in landslide analysis, we are able to follow the movement of the glacier. And in that case, in particular for Cold Glacier, we are able to detect the critical acceleration phases that we have before the failure. That means that using an inverse velocity approach that has been developed by Fukuzono many years ago, we are able to forecast when the failure of the ice block will occur. This can be done with cold glacier. It is more difficult with temperate glacier, but in that case, since this glacier will be cold, because of course the rise of temperature is changing also the glacier from cold to temperate, we are able to adopt this solution. Of course, this is an extensive, critical installation, but guarantee the possibility to measure even with bad weather condition. If we increase also, unfortunately, the price of monitoring solution, we can install, and we installed in 2019 a ground-based SAR. Okay, this is a synthetic aperture radar, the ground-based version of the synthetic aperture radar. And this radar is able, again, to measure the glacier, not only following the points, but measuring all the movement of the glacier. You see the map of the glacier movement measured by the radar. Consider that the distance between the radar and the glacier is more than 5 kilometers, so it's a very, very long-range solution. And the added value of this system is that it can work on, even with bad weather, even with clouds or rain, and we have a new image every few minutes. That means that we are moving to a daily analysis to a few minutes analysis that can support the evaluation of the movement of the glacier, looking for critical accelerations. So this is one of the best solution, and also, unfortunately, the most expensive. But the last one that I will show you is the alert solution that has been installed, that is a Doppler radar. Okay, so the system that I mentioned before are systems that are able to monitor the evolution of the glacier at different scale with different resolution, and give us the possibility to study the evolution of the glacier and recognize the critical acceleration. On the contrary, this Doppler radar is a radar that is able in a few seconds, means that in less than 3 seconds the system is able to detect the beginning of the failure, evaluate the volume of the failure, and decide if autonomously if send a warning or not. The system has been installed because if the volume of failure is more than 1,000 cubic meters, the scenario, the model shows us that the failure will reach the road, and so this Doppler radar is connected to a network of traffic light. We are able in less than 15 seconds to stop the road, close the road, and avoid that people be in the part of the road that is in danger. So this is the most advanced example that we have in Italy to monitor glacier. Okay, we have just this open air laboratory because the elemental risk in the Ferre Valley has been considered as so important to decide to invest, I would say, a lot of money to follow the evolution of the glacier and guarantee the possibility to manage the valley, to guarantee the valley opened, but also to give the possibility to population and tourists to visit this valley with a good security condition. We also developed a bulletin because during the most critical acceleration of the Plan-Pensia glacier, the critical scenario that we had in particular during the emergency of 2019 was the possibility of an ice failure of 500,000 cubic meters. That means a very, very huge ice avalanche that can reach the bottom of the valley and destroy everything. So we developed also a bulletin that is shared with the population to inform the results of the monitoring network, to try to involve the population also in the management of this valley, giving them the possibility to know the evolution of the glacier following the monitoring solution. So just a few slides to say that I try to share some example of our research activity related to the development of new technological solution that can be used for glacier monitoring. In particular, I think that the use of terrestrial camera can be very useful because they are low-cost solution that give us the possibility to analyze the evolution of the glacier and try to understand how the glacier can accelerate and what are the critical conditions. But my last slide is something that I will share also this lesson learned from landslides, because I have a quite good experience in landslide monitor, and then I apply this experience also in glaciers. And what I would like to highlight is that, first of all, as in landslide, we need to start from a geological model of the landslide, okay? In the study of glacier, and in particular glacier instability, we have to start from a glaciological model. That means an analysis of the geomorphological condition of the structure of the glacier. Using this data, we can develop the monitoring model. Okay, so we can develop a monitoring strategy, and once we start to have the data from the monitoring network, we can have more information about the kinematic domains. So we move from a static model to the dynamic model. Once this first interaction give the possibility to have a stronger model of our glacier, then we can use all these data set to develop numerical models that can be used for the definition of critical failure parameters or the use mainly in cold glacier or the failure forecast approach. So thank you very much for your attention.
Dr. Daniel, thank you very much for excellent presentation. The whole approach is very attractive for me. Thank you, sir.
Thank you very much for your invitation, and thank you much for introducing this presentation. I'd like to welcome you to my presentation about deep-seated rock slides, understanding processes and assessing impacts on infrastructure. My presentation is based on a short introduction on the topic, the structure and processes of deep-seated rock slides, impact mechanism on dams, hydropower, bandstocks, bridges, roads and highways. And I conclude with also the impact of rock slides in glaciated terrain, which is a challenge in the last, I would say, the last 20 years or something. And in the topic is also increasing. And then I will conclude with a short summary. This presentation provides an overview of processes and impact mechanisms that slow-moving, and it's about slow-moving deep-seated rock slides, can have on infrastructure. And the case studies are used to illustrate interactions with dams, pressure pipelines, with highways, road and highway foundations and bridges. All selected case studies are from Western Austria in the Council Tyrol, which is in Austria the high mountain area. So mountains are up to close to 4,000 meters. And I will align on the classification proposed by Warnes or Kronen-Warnes. So a slide is a downslope movement of a soil or rock mass occurring dominantly on surfaces of rupture or on relatively thin zones of intensive shear strain. We found this type of deep-seated rock slides typically in phyllites, in schist, in gneissic rocks, and the formation is often controlled by geological structures like foliation plains, schistosity joints and faults. So it's also, even if the landslides are typically have a large scale, they are controlled by structural features. The formation mainly occurs along discrete shear zones, so that's the main issue. And depending on the geometry of the rock slide mass and the internal and basal shear zones, minor or pronounced deformation of the sliding mass occurs. So we have Hurst and Graham structures, internal shear zones, but the block fragmentation according also to Hunger et al. 2014, a combined sliding mechanism. I focus on velocities are typically ranging from extremely slow, so a few millimeters per year, to very slow, a few centimeters, decimeters per year. If they are meters per year, then it's already quite a fast and serious situation. So I present some results from a very well investigated case study, which is a reservoir in Western Austria. It's a 140 million cubic hydropower reservoir built in the 60s. And it's used as electricity supply system. So all this you can see in the yellow lines on the auto images are showing boundaries of different slabs or active and inactive boundaries, scarps, so the main scarps of these different deep-seated rock slides. Some of these rock slides reach thicknesses of close to 250 meters. Some move still with a few centimeters, I would say 2 to 3 centimeters per year, and some show some type of acceleration related to reservoir level change. So these rock slides are very well investigated by drilling, but also by investigation drifts. So, and they could show highly fractured and decomposed rock slide mass, development of sliding slabs separated by shear zones, inactive and active shear zones. That's also a quite interesting topic because we found these different types. So when were the inactive shear zones active, why are only the active shear zones still active today, and things like that. And below we have the undeformed bedrock, and we have the structural effect on rock slide geometry. Here in this case it's related to jointing, but also to foliation, folding, and things like that. So here I will focus, maybe I go back. I have to go back, sorry. I will focus on the slide here on the right side, the Glasgarten rock slide, and here it's the right, on the orographic right side. In the next slide, so you can see the main scarps. So the red line is the main scarp, which is also the active one, and the green lines are the inactive scarps. You can also see an investigation drift with boreholes based or drilled from this investigation drift, either horizontal or sub-horizontal or vertically into the rock slide. But of course it was also the intention to build this investigation drift mainly outside or below the basal shear zone of these deep-seated rock slides. I would also like to mention on surface observations, which is based on tachymetric observation, but also automatic total station measurements. And here you can see a cross-section, a geological cross-section, showing these different sliding slabs, but also showing the horizontal drillings, and also providing some information about the groundwater table before the investigation drift, and the groundwater table below building or below after construction of the investigation drift. And at the top we have a quite, there's no laser pointer, sorry. Okay, in the next slide you can see a horizontal geological cross-section showing the different basal shear zone, but also showing the horizontal drillings, the vertical drillings, and we also did some investigation based on hydraulic bucket tests on these drillings to investigate the hydraulic or the hydrogeological properties of the basal shear zone. And you can also see some red lines. The red lines are showing the basal shear zone, but also the internal shear zone, and the drift already penetrated also into the active part of the landslide. Here you can see shear zone properties are highly relevant for slope stability assessment, and here you can see a borehole showing the upper part of the rock slide mass of this rock slide, but also showing RQD values which related very nicely to the low or high variation of RQD values related nicely to the rock slide mass, where below the rock slide mass we have not so much fluctuation of the RQD values anymore. So we also observed uncemented fall breccia and gouge, which is newly formed by cataclasis of the rock during slope deformation. We did some mineralogical investigations, also some geotechnical laboratory analysis, creeping testing, shear testing, and things like that. So to investigate the soil-like material with high implications on the mechanical and hydrogeological behavior, and localization of shear zones by inclinometers and by the investigation drifts. So monitoring is well experienced here because you can have a wire extensometer along the shear zone in the investigation drift. And here you can see a picture from this investigation drift showing nicely the rock slide mass above, but also showing the shear zone, which is here is about 1 meter. That's a basal shear zone based on fault gouge, but also on fault fracture. And in the middle photo, you can see a detailed view of this shear zone showing the shear direction, but also showing the behavior and the two pictures or the two figures on the right showing this fault gouge material where we did some laboratory testing. And it was interesting also to find in this fault gouge material slicken sites, striations, which are related very similar to tectonically formed shear zones. We also observed, or we did some hydraulic bucker testing and laboratory testing of the fault gouge material, but hydraulic bucker testing of the undeformed bedrock below the rock slide mass, and also a few tests were done within the rock slide mass. And on the right, on the figure, you can see the orange bars are representing hydraulic bucker intervals in the undeformed bedrock in this area, and the blue bars represent hydraulic bucker tests in rock slide masses in this area of the reservoir. So what we found fractured bedrock below the rock slide mass show a strong variation of 10 to minus 6 to 10 to minus 10 meters per second hydraulic conductivity, but the rock slide mass shows a very high range of hydraulic conductivity from 10 to minus 10 to 10 to minus 7 meters per second. And the clay ridge shear zones show very low hydraulic conductivity of, I think, less than 10 to minus 9 meters per second. And we also did some consolidation tests of these shear zones showing a low hydraulic diffusivity of 10 to minus 6. Finally, we observed flat groundwater tables in the rock slide mass, but then a steep increase of the gradient, of the groundwater table gradient in the underformed bedrock and also the basal shear zone. And we also observed a trend towards higher hydraulic conductivities in the fractured rock slide mass, of course, with a high variation. So a very heterogeneous hydrogeological situation is there. In the next figure, I show the other case study on the opposite side of the reservoir, which is also very well investigated since the 60s, since construction. And here you can see a map, a hill-shade map with the main scarps, A, B, C, D, and E of different active sliding slabs. And I would like to show in the next slides the evolution of the geological kinematical model over time. So sometimes we think geological models are a kind of static, but in reality this experience showed nicely also to me how geological models change and maybe improve with the degree of investigation, with the degree of knowledge. So, and I would like to show, for example, this is a first cross-section drawn by a very popular and famous geologist in the 60s, and it's showing more or less the most active upper rock slide slab. In 1995, they made a new drilling campaign and showing also a new geological kinematical model, also not really focusing on the basic, the basis of the deep-seated rock slides, which here reach nearly close to 200 meters. So, and finally, I had the opportunity to get new data, get new drillings data, and that was the model I constructed 2010 with seeing the different sliding slabs. These sliding slabs have different activity. So some are mass D is about 2 to 3 centimeters, mass C is about 1.5 centimeter per year, and mass B is about 1 centimeter per year. And rock slide mass A is inactive today, so it's not moving again. So, but still, they made some new boreholes with new inclinometer installations And maybe the model will change also in terms because of the active part of the model. So you can see there's different changing in geological models. And of course, if the geological model is not coping the main issues, the key aspects, also the numerical modeling following the geological modeling is somewhere questionable. So my message would also be to say, okay, we have to think a geological model is a present investigation, and especially for deep-seated rock slides, it can change over time. We need time, especially for monitoring, because usually we have only a few millimeters or centimeters per year. So we need time to check where is the basal shear zone by inclinometers and stuff like that. We have also to interpret the inactive shear zones, which is a challenge because sometimes we don't know it's a tectonic fault or it's related to the landslide or the rock slide forming process. And here I would like to show some impact on reservoirs for the first time impounding effect. So reactivation, we can have acceleration of pre-existing rock slides. We can have also a formation of new slabs, or maybe in the worst case we can really produce a new deep-seated rock slide, but in many cases it's already there and we can reactivate or form new slabs. And the impact of the geometry and slope stability during the first impounding, we did some investigation based on the impact of the geometry of the rock slide mass. And here on the left side you can see some are real cross sections from real landslides, some are generic, and on the right side you see it's a very simple limit equilibrium analysis. The change of factor of safety over impounding height, infilling of the reservoir height in relation, starting with a factor of safety 1, which is just a generic factor, but you see there's quite a strong impact from the geometry, so it's very useful and very helpful to get a good impression of the geometry of the rock slide system. We also observed in this reservoir case study at the beginning, this is sliding slab D, a strong acceleration and the forming of a new sliding slab, a smaller sliding slab. It was in 1964, and you can see some impounding triggered acceleration and forming of this new sliding slab, which could managed by 3 impounding cycles where the velocity of the sliding slab reduced. But later on, annual acceleration during operation occurred, so when lowering the water table, the slope sliding mass D accelerated. So that's every year. That's effect from infilling effect and lowering effect. So it's a groundwater-based impact on this system. But not all of these rock slides in this area, for example, show this behavior. It's just one of these. Further on, I will go also to another case study, the impact on hydropower penstocks. Here you can see a deep-seated rock slide, which is in cultural schists and fillets. There are some locations with evaporites. It's about 200 meters thick rock slide, and there's an old pressure shaft penetrates through the basal shear zone. I will show a cross-section later on. And this rock slide shows extremely slow displacements of only, I would say, a few millimeters per year, less than 1 centimeter. I think it's about half a centimeter per year or even less. But however, long-term deformation of the steel lining due to continuous slope displacements also had some impact. And there was a new construction. There had to be a new construction with a new pressure benchstock and pressure shaft. Here I can show you the situation. Here's the pressure pipe, and here you can also see the main scarps of these deep-seated rock slides. And here you can see the basal shear zone, the basis of the deep-seated rock slides, where the green line shows the penetration or the location of the old pressure shaft. And the new pressure shaft was built below these deep-seated rock slides to avoid any problems in the future. Even if this movement is so small, it caused over long term some financial loss, for example, because they had to make a new pressure shaft. I will also focus on a old dam in my home region. It's also built in the 60s, so it's a 80-meter high earthfill dam. It's a reservoir with 52 million cubic meters. It's also in fillets, in calcareous fillets and schists. We have green schists, so rock types which are highly prone for forming deep-seated rock slides. And we have rock slides here of 300 million cubic meters affect the dam foundation. And here you can see the location of the dam, which cause these two, on both sides, these deep-seated rock slides cause valley closure, upstream sedimentation process. But of course, long before the dam was built. And of course, some slab formation with some of the slabs reached velocities or not velocities, reached displacements of 3.2 meters from 1966 to 1997. But what was the issue here? So there was compression and deformation of alluvial sediments because of the deep-seated rock slides from both sides made a kind of damming. So it caused a really heterogeneous subsurface. So we have fluviatile sediments of sands and gravel, so with a higher hydraulic conductivity. But there are also silt, we have glacial with a lower conductivity, and clay lenses, for example. So there are glacial tilts, there are talus deposits, and also the rock slide mass. So there's a complex hydrogeological situation with different hydrogeological properties, leading to complex hydrogeological situations and causing seepage water, but also causing high piezometric heights in the downstream area, leading to a low safety factor calculation for the dam. So they had to make some relief wells to reduce the bore pressure and to in a confined aquifer. Here you can see the green area, which is a silty layer. Finally, I would like also to show some examples on the impact of bridges and roads and highways. So we had an extreme flood event 20 years ago, in August 20 years ago in Tyrol in Austria. And the main river measured in Innsbruck a discharge of 50,000 cubic meters per second. And this was the highest measured discharge since 1871. So climate change effects already start much earlier, but now we see we are facing more increasing of this behavior. And last year, 2024, we had a very high rainfall event in the eastern part of Austria, causing a lot of destruction and also causing destruction of newly built tunnels. So a railway tunnel was destroyed after just 8 years. A lot of not wasted, but lost money. Here you can see some impressions, and I would like to show the event caused a complete closure of both tributary valleys, the Stanzer and Bad Snauntal. So you can see these two valleys. You can also see the red lines show the scarps of deep-seated rock slides, or at least slabs of these deep-seated rock slides. So we had slope foot erosion on these deep-seated rock slides. We had reactivation, acceleration, and new slab formation. And of course, at the time of the flood event, there was also the hazard of blocking the rivers with flood wave hazard. Displacement of road section, bridge foundation, and pressure pipes. So a lot of impact, and I would show some. This photo shows the displacement of the road by several meters by this active or triggered rock slide slab. It's not the base of the big one. It's just a more shallow rock slide slab. And here you can see the bridge, which was also just a few decades old, impacted at the toe by rockfall events and also moving parts of these deep-seated rock slides. We are located in a tectonic complex area. It's the northern Calcar Alps, the contact, the Landecker fillet zone. So we have fillets, we have also crystalline rocks, we have schists, we have gneisses, we have flits, and we have a lot of tectonic overprint. Tectonic cataclassis fracturing led to low strength rock masses which are prone to rock slide formation. It caused a short lifetime of the bridge from 1971 to 2005, only 34 years. So usually we plan these bridges for 100 years. So a new tunnel was to be built, and nearly completed highway tunnel was used as a detour for the other valley. Otherwise, the other valley where the road displaced by several meters would be blocked. So that's a nice example of multi-hazard, and we have more and more to think on these multi-hazard problems, so flood causing landslide interaction. And finally, that's my latest case study I would like to show. That's impact of rock slides in glaciated terrain. And this is a case study in the central part, in the western part of Austria, where a rock slide mass, more than 60 meters thick rock slide mass with a glacier on top was reactivated in 2027. And here you can see in the scarp area, in the main scarp area, the displacement of the glacier and exposure of the basal shear zone. And here it's the basal shear zone, which was nothing more than just a reactivated fault plane, a tectonic fault plane, were used here as a weakness zone for this deep-seated rock slide. And here you can see the change in, sorry, wrong side. Here you can see the change of the topographical situation. So in June 2007, we had this formation of the 65 meter thick sliding mass of a total volume of about 4 million cubic meters. We are again in foliated metamorphic rocks, paragneissic rock mass with a foliation dipping moderately to north. We had a glacier on top. We had intensive rock and ice fall activity. And we did some 10 years of remote sensing and monitoring based on airborne laser scanning, terrestrial laser scanning, auto images, and webcam images. And this is a laser scan image between two scans, airborne laser scanning between 2006 and 2007. And you can see the big changes. So we in the main scarp area, we have 40 meters of displacement. And the important part is we had a lot of failure events, ice, rock avalanches, small events, formation of different slabs. But we had no total failure of this event. So that's the important issue. And you can see a lot of accumulation of material in the lower part. And here you can see some slab formation processes, the change in the glacier. On the left side, the red line shows the scarp, the initial scarp, and the blue line shows the displacement over time. Also here, formation of another slab. And finally, cross-section of this area accomplished by numerical modeling. So investigation of the processes which were leading to this rock slide formation. For example, we investigated permafrost degradation causing to rock strength degradation. We also investigated the impact of permafrost degradation or cold and warm-based glacier behavior on the groundwater situation, which has the highest impact, and things like that, and also the glacial unloading process in the lower part of this slope. Okay, so I'm finally at the end and the conclusion. I would like to summarize. So we have rock slides and reservoirs. So we have acceleration problems, we have new slab formations, we have hazard assessment of rapid failure, and we have to, of course, install monitoring systems. So it's a great expense to improve safety and monitoring, continuous monitoring. Rock slide and band stocks and pressure shafts, long-term deformation of pressure pipe, failure and reduction of lifetime. Same with rock slides and dams, dam deformation, pore pressure and seepage water problems, stability problems, rock slides and highways, multi-hazard, slope, foot erosion, reactivation, acceleration and slab formations. So maybe also cause to a strong reduction of the expected line time and a high financial losses. And there is also, I would say, in the last decades, and especially it's accelerating in my impression, there's a need for consideration of climate change effects. So we have extreme precipitation. We have also observed 2019 extreme snow melting events, which causing acceleration of pre-existing rock slides, flood triggered slope, tow erosion and destabilization, and large and far-reaching rock avalanches in the high mountain due to glacier-related and permafrost degradation. Thank you very much for your attention.
Yes, thank you very much for Professor Christian for very excellent presentation. I am great impressed your presentation of deep sea rock slide. It's affect infrastructure, how to observe and how to analyze it, how to survey it. Thank you so much. Thank you.
Okay, thank you very much. Bye.
Next presenter, keynote presenter is Mr. Aniel Pokarel. Mr. Aniel Pokarel is a former chief executive of Nepal's National Disaster Risk Reduction and Management Authority.
Good morning, everyone.
Yeah, please. His title is Interdisciplinary Approach to Disaster Risk Reduction and Management and Sustainable Development in Nepal. Please.
Thank you. Once again, good morning, everyone. Thanks to the organizers for having me and allowing me to share my own experiences working as the Chief Executive of Nepal's National Disaster Reduction and Management Authority. I've just, earlier this year, I've ended my 5-year term as the Chief Executive, but I no longer represent, at this outset, I want to share this disclaimer that I don't represent the National Disaster Reduction and Management Authority. I'm an independent expert working on disaster risk, resilience, and a bit on climate change. How do I flip this? On your way to Kathmandu, you might have awakened by this volcano. And this is the one that happened in Ethiopia. You might have, some of you all might have been diverted your flights or perhaps delayed. What we could see is the world is increasingly becoming interdependent. And the risks, the hazards, the exposure and vulnerabilities, they are often cutting across boundaries, our national boundaries. They're cutting across communities, cutting across infrastructures, physical infrastructures, societies and communities in a very complex ways. And they often lead to cascading and systemic risks, such as the one that Nepal experienced recently just before the onset of monsoon. These are pictures from the Melamchi fiasco. I use the word fiasco because it's one of those complex, systemic, cascading risks that was very far from our reach to understand and address it. What happened was a massive volume of, again, debris, sediment that came across. You see a human standing over there for his survey. That's the scale of sedimentation deposition that happened upstream of this reservoir. Some of you all might have even been involved in this study. The headworks that you see down, the yellow works, is nearly 24 meters under debris. So these systemic and cascading disasters wipe out our investments and decades long of investments in a fraction of a second. This case itself is a classic telling story that looks at, again, a problem that we all confront, not only in Nepal, but also globally. Just predecessor speaker also did highlight the role of climate change, and this is what we've been started experiencing in the mountains in the Himalaya. We're fortunate on that day because the tunnel just happened to be, the headworks had just been left open to do an inspection of the tunnel. Had it been closed, had the gates been closed, the entire sediments perhaps would have entered inside the sediment, and a pressure tunnel would have been completely foregone. So these are the scales of interactions and complexities that we've been facing in the Nepal Himalaya. At the outset, I also want to share a recent phenomenon that happened. It's a Gloff story. A glacial lake outburst flood in a village called Thame burst out. It was a very teeny-weeny lake that didn't even fall into the radars of any risk assessments of glacial lakes. This was perhaps the size of half of the swimming pool that you might have seen here in the hotel. Our assessments would never consider these lakes would be risky. Anything that's size of 2.5 the size of an Olympic-sized swimming pool would only be considered fit for risk assessments. But if you look at the scale of devastation, it's enormous, it's cascading, and it perhaps continues even until this year. This started last year. Within half an hour, a settlement got wiped out, a very serene settlement very close by Everest within that area got wiped out, and you could see the extent of boulders and sediments and the floods wiping out these settlements. So in terms of risk management, we've seen that, again, even within ourselves, within the room, we've seen different set of perspectives, different set of disciplines coming together. Some of us, and I see, especially from day before yesterday, some are more concerned, more interested on the analysis, on modeling side of things. Some are more interested on risk reduction, either through the use of anchors or the bolts, or perhaps even nature-based solutions. Some even avoid risk. Perhaps a flight was diverted. Perhaps the flight was halted in that case of volcano. The humanitarian sectors, the disciplines would be prepared for it and then mobilize for it. The governments, particularly the Ministry of Home Affairs, the Army, and the police would want to control it, whereas the Ministry of Finance or economists would want to transfer those risks. So these are different perspectives and different disciplines trying to kind of commonly solve a problem as complex as disaster and climate change risk. This is where our speakers, especially our president of IAEG yesterday, Mr. Vasilas, mentioned in his keynote the need for interdisciplinarity. I was also touched upon his talk on the triangle about how these disciplines do intersect each other to find common solutions. So was I touched with the Vice Chancellor, Mr. Professor Achyut Wagle's talk, where he really highlighted the need for interdisciplinarity. We're already in the age of interdisciplinarity. So it is in this context, my title, I found it very pertinent, especially for this audience, and basically highlight that while multidisciplinary efforts have been there, especially for the last 2 decades or so, especially that has made efforts to bring in experts from various disciplines, from engineering, various facets of engineering, to geology, engineering geology itself as a discipline, but also social sciences, economics, more often the use of public health disciplines, information technology. Our previous presentation was a classic example of how do you use the technologies and modernization, but also looked at governance. And these collaborations, often what happens is runs parallel without appreciating other disciplines. And so this is where we often tend to fail. Now, if you just look into the numbers in the Nepali context, these are diagrams that would illustrate us, again, what went through, especially within the last couple of years. I'm sharing a couple of slides for this one's for 2020, where you'd see the largest human death has been through road accidents. Safety has been compromised, has not been that much of a priority. But if you look at the biggest yellow, the orange thing, the human death was because of COVID. Landslide would come in third, with nearly 400 people dying that particular year, and that too within the monsoon period. Floods, the number of deaths have gone down, something to around like 70 or 80 a year. Lightning still holds the chart up, something around like 100 people a year. This is 2022. 2 years later, the scenarios are a lot changed don't see COVID deaths, but what you see still is road accidents. The proper design of roads, that was highlighted a bit yesterday, but also safety, these are critical elements. But what's really concerning us is, again, the landslides and floods killing more people, and the need for transcending from multidisciplinary, where a lot of disciplinary experts do come into the table, or perhaps collaborate on certain projects, but not respect for others' discipline, and then really understanding the interdisciplinarity side of things. 2024 was another brutal year for us. The 2024 overall loss and damage has been one of those humongous in terms of, again, deaths, but also resulting economic losses. We've lost nearly 600 people, another like 70, 80 people missing. The financial losses has been humongous. The reconstruction process is still, in some places, especially in the highways, have just begun, whereas a lot of reconstruction for private houses, schools, and others are yet to begin. What I want to highlight is not only the full throughout the monsoon, but those 2 days in September where we experienced a heavy rainfall of around 331 millimeters for 2 consecutive days, and that led to a death of nearly half of that population, nearly 600, half of that, 250 deaths alone on those 2 nights, and an ensuing amount of, again, debris flow, deaths, destruction. So this is where perhaps the need for transcending from a multidisciplinary perspective to a more interdisciplinary perspective is what we could start looking into it. I don't want to go to the detailed numbers on what was lost in terms of infrastructures, in terms of, again, communications and other sectors, but what we see is as mentioned earlier as well, the World Weather Attribution, a global body of scientists and independent reviewers came together for this case, which with the National Disaster Risk Reduction Management Authority triggered it. They've come out with a rigorous publication and an assessment that said that this is clearly attributable to climate change. 10% of the rainfall that happened in that particular day was clearly attributable to the climate change and the greenhouse gas emissions that we've been experiencing it. So this perhaps for the first time, there's been a lot of, again, incidents around water-induced disasters, such as the one in Melamchi, or the ones that we've experienced before, such as the ones in Thame, Glaf. But this one is where the scientific body's been able to come together, work with institutions like NDRMA to clearly attribute the science, the climate change science, to make it a clear, compelling case for loss and damage. In 2024, we've also experienced another extreme case where we've never in history, in the last 70, 80 years of history of our measuring rainfall, have come across such levels of rainfall. This was 624 millimeters of rainfall happening overnight. We were fortunate that this system, we were able to forecast in advance, mobilize all walks of life, the whole of society, including the security apparatus, the humanitarian sectors, private citizens, and humanitarian workers. So this was a case where there was only 1 death in that particular area. This has been again attributable to the climate change impacts that we've been experiencing. So what we see is the need for, again, address such complex disasters that's happening. This is again the case of last year, where a hydropower plant, this is the power generation site in eastern Nepal, that got nearly wiped out. There could be a lot of faults. Again, you all could clearly say that this might have been wrongly placed and designed, but our interactions tell us that, again, had we cut off some of those trees on those areas, that the trees would not have formed as a trap to those boulders and the sediments. Perhaps a solution which was out of the box would have been perhaps cutting those trees in those areas, which might sound a bit weird, but this is where, again, understanding disciplinary perspectives and then see how you find common solutions to a problem is perhaps needed. This hydropower plant had just been operational around 50 days back, and you could see again the turbines green and vibrant in colors, completely been washed out. The pictures on the right shows again what happened after that. And so these are investments being made by the private sector. some of which is insured. The risk transfer has been done. But again, it comes at a huge price to those investors, especially for a country like Nepal. So this is where the need, again, to really understand these risks and to really move away from just looking at the multidisciplinary aspects to interdisciplinary aspects is really needed at the hour. Nepal is a country case where we've been inching forward more fast, especially since 2019. And I'm going to come back on that and how we're doing it. So from really, again, if I want to sum up, the multidisciplinary aspects is good. It looks at, again, various disciplines. It does, often at times, brings different disciplines into the table. But these are often running parallel. Each of these expertise would contribute it. But they do not really have that respect to the other disciplines. If I'm a civil engineer, I would perhaps brush aside engineering geologist or an economist perspective, batting only on my back. But here, the need is to really kind of transcend to that into an approach that really appreciates the other disciplines as well. Often at times, the legal aspects, the social dimensions are much bigger, and then really our risk assessments contributing to the interdisciplinary perspective is really important. This aspect is much talked about, but what really stops is not having an institutional grounding as who does that integration or who does that bringing into that interdisciplinary is often missed. Nepal's case, and this is what my contention in the paper is Nepal's Disaster Risk Reduction and Management Act. The policy and the strategic framework allows this particular institution that was promulgated by the parliament in 2017 does allow that space. It brings in all ministries together under the chair of the Prime Minister. So this is where the Finance Minister would then be working with, discussing with the Ministry of Physical Infrastructure and Works, or even the Energy Minister. It allows the highest level of, again, agencies, governments to even come and talk together to find a solution to a common problem. Transcending that at the secretarial level, at the highest level of bureaucracy, is the executive committee, which is headed by the Home Minister. This allows the secretaries from each of those ministries, like the ones we had Kesav Sarma sir yesterday, interacting with other ministries to share common set of ideas. So this is possible in the case of Nepal because of the governance change and the law that we came out in 2017 and the establishment of NDRMA. So this is quite a unique case that I want to kind of share where this exchange and making decisions either through the executive committee or through highest level where the ministers sit down together. The NDRMA as a chief executive would then serve as a secretariat for those meetings, host those meetings periodically to address some of these problems. So this is where I see, again, Nepal's DRM Act does allow this. It even specifies to the detail that the use of, again, remote sensing, the kind of presentation, or the use of drones, use of satellite imageries for finding solutions to understanding risk and finding risk reduction measures are important and needs to be coordinated by NDRMA. So that's the level of details and the finesse that it did provide us. My submission to you all today is that Nepal's Disaster Risk Reduction Management Act that has allowed us to come up with numerous guidelines, something around like 30 guidelines over the last 5 years, has helped us advance us from a multidisciplinary way of looking things, which perhaps didn't even exist even some 2 decades back. We've been really making progress towards interdisciplinarity because of the governance change that we've been able to bring in through the promulgation of this DRM Act. And so with this, again, in the last couple of years, we've been able to identify our priority areas in terms of, again, how would we, there's 200 odd different things to really focus on, but among those are 8 areas that needs to be really on top of the priority, starting all the way from risk assessments to early warning systems and risk transfers, some of these 8 areas. And this does not only rest within the federal agencies like the Central National Disaster Risk Reduction Management Authority, but it cuts across the local governments, the district, the provincial, and the federal. Having this set of dialogues across these 4 levels of governance is equally important, in addition to having this different disciplines reflection on a common set of problems. This is exactly what Nepal's DRM Act does allow. And if we compare this to perhaps with other country cases, even cases with India, where there's such a disjunction between, again, between the national or the federal agencies and what happens at the provinces, states, and the local level. Our case is what allows a classic case, it allows these interactions among these 4 levels of governance at the federal, the provincial, the district, and the local level. This also brings to a point that, again, it cannot be solved by the government alone. Even in this room, what we see is at least 3 different perspectives. The bureaucratic, the government system, representatives are there. You see tons of logos out there, all the way from National Disaster Research and Management Authority to Ministry of Energy. The ministries are there. But it's also driven by market solutions, some of which we see outside being displayed. On the other hand, the community of practice, the academicians, the research, the contributions without which we wouldn't get there to that, the value, the recognition in terms of the recognition of other disciplines. So this is where Mary Douglas and others, especially through cultural theory, have come up with this argument that having these three perspectives, coming together, trading off some of these trade-offs, coming together is a way to really look at integration and look at interdisciplinary aspects. So this takes me to the last part of my presentation. So how we've taken this DRM Act, the governance, but also imbibing on the respect of all of a society approach. If you look at some of these cases, these case examples we've been able to bring success are around risk assessments, understanding risk. I'm cognizant of the time. I'm trying to wrap up in another 3 minutes, if you may allow, Sensei. So these 5 cases is what I'd be perhaps discussing with some of you later, or during the hallways, or writing in this paper, is A, around understanding risks, B, around understanding sediments, which is least understood, at least in the Himalayan case, using this information for designing and developing early warning systems, asset registry for risk transfer and risk financing. These are details that we could perhaps discuss later. There's one area that I want to touch upon, and then end of this presentation is around risk assessments. Before this executive committee, or before NDRMA was established, risk assessment the practice wasn't there to really, again, who does what. And so NDRMA, through executive orders, we've been able to come up with executive orders that allows us to share all hazard assessments, vulnerability assessments, including exposure assessment, into a common national system, the BIPAD portal. BIPAD is a word in Nepali, that's disasters. So BIPAD portal is an open source system that allows our local governments, our other institutions, including departments and ministries, to share data. So it allows us to, again, look at various hazards, whether it's landslides, whether it's earthquake, whether it's floods, whether it's lightning, all into a common space. But the beauty with that is this is a classic example of, again, landslides, hazard assessments were resting on perhaps in some experts' drives, or perhaps only with Department of Mines and Geology, or some with Department of Irrigation. This executive order allowed us to kind of reach out to all those agencies, bring this data, and to put it in a common platform accessible by students, by academicians, and an open source system that you could really download those layers. Not only the size of the landslides, its progression over the time, but also mapping of houses, mapping of assets, mapping of again, infrastructures. That does allow us to really use this information to compute risk rather than only come up with colored maps. I want to share my first year as the CEO. When I went to the Prime Minister's office, the Prime Minister himself, next to him was the Finance Minister, the Finance Secretary. The Finance Secretary said, like, this means nothing to me, Anil. These are colorful maps, this is wonderful, but I don't understand a bit on this. I only understand numbers, I only understand amount of money. So as risk assessment experts, if we're not able to communicate to the Ministry of Finance using numbers, I think we fail. This is a major area that we could really kind of change our ways how our risk assessments are done. One of our biggest gap was, again, not having those platforms and not having those executive orders to bring all this together. You need the social scientists to understand the human vulnerability, the disability side of things, the women, the gender side of things, whereas you need asset registries, you need building experts, you need highway experts, you need roads. But you also need, again, the sciences of, again, the remote sensing, the satellite imageries, you need surveyors, all computed using models, computer models. You'd then be triangulated and validated through various stakeholder dialogues. And this is how you could use it to not only come up with colorful maps to tell your high risk, moderate, or low risk zones, but compute that in terms of something that is used for making decisions, like the Ministry of Finance, to set aside your budgetary allocations, either at the municipal level or at the provincial level or at a sectoral level. This way of working perhaps is a classic case of, again, interdisciplinarity. Respecting other disciplines is equally important, but also having systems that allows us to interact, find solutions to a problem that we all had been grappling with. Sharing data is a taboo, especially in South Asia, especially in Asia, where it's kind of closed, put it in the closed doors. I think that's where having that opened up, the chest of drawers opened up, is perhaps one way of looking at these solutions. These are a case example of, again, how we've done in the Nepali case. I've only highlighted the risk assessment and this platform as an entry point because other cases would actually, the decision making for, say for instance, whether it's risk financing, whether it's insurance, whether placing your hydropower sites on a location A or location B, all depends upon understanding of risk. So we've been able to really make a huge progress, especially in terms of really bringing in these systems through continuous dialogues across multiple scales, respecting the other disciplines, and having NDRMA as a classic case that allows to do that integration to help our infrastructures and be more sustainable and build resilience in such a complex environment. Thank you. I'd like to end my presentation here. Thanks once again for allowing me this time. Oh, thanks. I'm sorry. Thanks. And so that's really wonderful. So in terms of, again, other case that I wanted to kind of mention was early warning systems. Again, even until recently, our early warning systems would only mean a forecast that would come out from our centralized agency, the DHM. That's the mandatory agencies. But the forecast that would hardly be understood by a local community or a local government. The other three pillars of a functional early warning system, especially around communicating those risks, wasn't there. That's a different set of discipline that requires investments. Risk communication is one of those poorest areas. Third is how do you, again, pre-position your stockpiles, and so basically looking at, again, logistics. That's a discipline is again, within South Asia and in particular in Nepal, having stockpiles, having those stockpiles into a common national registry as an emergency manager, if you're a local government leader or if you're a district in charge. If you don't have those stockpiles into your systems, if you don't understand where those boats are, or your hard hats or your ambulances are, you'll not be able to effectively manage a response exercise. So we then worked with, again, used AI, using the power of, again, crowdsourcing, using multiple municipalities to, again, have those numbers, whether it's ambulances, whether it's, again, those trucks, or whether those fire trucks, into a common national platform called Godam. And that allows to help crack the third pillar, whereas on the fourth, having those humanitarian workers, the responders, trained human responders, also be part of that common system. So having those four pillars of early warning system connected into one common system using common alerting protocols has been what we've been working towards. This is also through the National Disaster Risk Reduction Management Authority, through executive orders, made decisions to work together among multiple, at least two dozen different ministries and agencies. So this is another classic example of, again, how we could use this hazard, exposure, and vulnerability data to inform local communities in advance. In some cases, in some municipalities, in the case of Sindhupalchok that I'd shown earlier, we could also identify where those are families with disabilities, or perhaps who would not even have a cell phone, would hard to understand even a Nepali language, or even language language that we sent it in Nepali. So you could use this through systems to evacuate those people. The same data sets could also be, and then again, the fifth example case study that I mentioned earlier was around, again, doing asset registry for risk transfer and risk financing. So this is how, again, a key decision around, again, working across multiple disciplines, getting together into a common national system through consultative process and identifying a common solution is a classic story that I want to tell from Nepal. That could perhaps also be of support to other country cases where the need to really look into, again, transcend from a multidisciplinary into a transdisciplinary system. So I conclude by saying that, again, we've not been able to address all those problems, but I want to really conclude by saying that, again, taking this interdisciplinary approach is essential for really addressing the complex disaster and climate change risk in such a high-risk environment. And so this approach would be effective, especially in terms of coming up with an inclusive and a sustainable development that addresses some of these problems. Thank you.
Thank you. Thank you, Mr. Anil Pokare, for wonderful presentation. I learned the outline of overview of disaster in Nepal. And Nepal is a top runner of disaster country. So the government policy is, I think, top runner of the world. We must learn from Nepal. Thank you so much. Thank you. Next presenter is Dr. Scott Anderson. He is a senior principal geotechnical engineer at BGC Engineering.
Thank you very much. It's a distinct pleasure and a privilege to be here today with these speakers and with all of you in attendance at this conference. I really am grateful to the organizers for allowing me this opportunity. I don't want to talk about evolution today, though. I want to talk about revolution. I want to have a revolution with you, and I felt those words were probably a little too strong for a title slide in Nepal. But what I'm talking about, I'll make clear here today. This is a picture I took 2 years ago in Sikkim, India, just east of here, in between the Malamshi and Tami examples. And what I'm talking about is ways that we can make this less surprising and less impactful. We can help communities get back to business sooner. And to do that, I'm going to go through some definitions and then share some experiences of mine over the last 5 or 6 years. And we need to understand what I mean by regional remote sensing, because that is in my title. And this is the use of aerial and satellite-based platforms to collect data that are bigger than the project scale. That's the important distinction. How big they are, well, maybe that will change, but they're bigger than the project or the feature scale. And I also want to talk about resilience, because it's this concept of resilience, which is how we get back to a full performance level sooner. And it's really important because resilience is an acknowledgement that bad things will happen. We are not going to stop all of the bad things that happen, and we need to recover from them. And we have the skills in our profession to do that. So I'm going to start with INSAR evolution, and this is in my own experience again. This is a project scale INSAR application of mine on the coast of California. The north arrow is not due north here, but that's a northwest facing slope. And what we were using this for with the California Department of Transportation is to track movement along their highway. Now, over several years, you can see in this plot from INSAR that it's very revealing, something they didn't know before, that it's moving about 50 millimeters a year towards the Pacific Ocean, and has been probably for some time. We can see in this plot of a time history that it may indeed actually have accelerated about 5 or 6 years ago, and the line is now steeper than it was. But this is a project scale understanding. This is another project of mine in Yellowstone National Park. The black line on this image is another roadway. And these are two landslides that we were looking at improving this roadway to make it better and serve the needs of the park and the communities that live outside the park better. But we recognized in the LiDAR imagery that there were landslides there. These are paraglacial landslides. We know they're 10,000 years old, but we're going to cut into the toe of them. So I thought, well, it's relatively inexpensive. It's very inexpensive to get some INSAR data. Let's do that. And son of a gun, a landslide that was moving started 10,000 years ago is still moving. Is that a big deal or not? I don't know, but we can learn it easy enough on the project scale. 2 years after that, that was enough of an observation by my client that it was very easy for me to suggest we should really get INSAR for the entire park. There are a lot of roads in Yellowstone National Park. It's almost as big as a small state, and it has a highway department, if you will. And so we captured that. And what you'll see in this image is way more exciting than the little road, which is a green line up in the upper right corner of the park there, which is where I just was. But of course, Yellowstone is a volcano, not quite as eruptive of the type in Ethiopia, but it's still moving. And that's the red that you see in this image. At the same time I was doing that in 2019, across the Atlantic Ocean, different things were happening. Both in Norway and in Germany, they were ready to release INSAR data to the public and make it available to everyone. This is what I mean by this concept of democratization. And Norway went forward with this. Germany got cold feet and held back just a little bit, but not very long. Because soon after, all of the EU had this type of a platform so that any one of us could go onto a web browser and zoom in to our own home, our business, our projects, what have you, and see what the INSAR data were showing available to us. It wasn't until this last year that that became available to me in the United States. This is a project, this is the islands of Hawaii. Volcanoes, I guess, are running through my talk, that we now have that same type of service provided by NASA in the United States. But what's really exciting and important and why we need this revolution is India just launched a satellite on the 1st of August this year, and in partnership with the NASA space agency in the United States, will make INSAR available to anyone for free globally. And not just, I showed one example of what's called L-band INSAR, which looks through trees a little bit better than C-band INSAR, which has been more common. But the NISAR program will have both types of satellites and sensors so that we can get that information. So again, to the concept of democratization of INSAR, this is the idea of we need to be ready for when we have this successful revolution. What's it going to mean? And it's going to mean that data are going and information are going to come from a different direction than we are used to. In the geotechnical business, and engineering geologists have been very careful usually, traditionally, in their written work to separate what are the data, what are the facts, from what's an interpretation, to what's a design, to what's an expectation, and then to action, which is design or construction. But in remote sensing, we need to get that kind of deliberate consideration going as well. And this is going to be important because the democratization is happening to the data. It's not the knowledge. The knowledge is still in this room. What do those data actually mean? A lot of them will be misleading. And this is the thing that is, I was in Oslo not that long ago and talking to a colleague there, and indeed, at the NGI, they now get calls from homeowners and whatnot saying, hey, my house is moving. What do you have to say about that? And that would never have happened in the past. So that's enough on INSAR for right now. I want to talk now about aerial LiDAR, which is, again, airplane LiDAR, and what's happened in that space in the last few years. I guess this reaches back a little bit more than 5 or 6 years, but this is in the area near Seattle in western Washington in the United States. We had one of our most tragic fatal landslides in that area a little more than 10 years ago, 11 years ago now. And that landslide was really something I studied in reconnaissance right after. It was very tragic, sad place to be. But we felt fortunate at the time that we had 2 epochs of LiDAR. So not only did we have a LiDAR before the event, we had LiDAR at 2 time periods before the event, and we were able to fly for LiDAR right after that event as well. And so what you see on the bottom of this image is the blues and the reds. The blue indicates a material loss, and red indicates material gain. We've gotten a lot smarter and better about how to compare LiDAR images than when we were 11 years ago, but that's what we're doing here. Now, if you look at the image on your left, this is LiDAR over a wide area, and it might look like there's some speckles in it, that it's not really clear. But they're not speckles, they're landslides. There's some kind of ground movement. I've got the red box around the OSO slide, but there are many, many more landslides that are captured because there are multiple epochs of LiDAR in this part of Western Washington. And this map on the right here now shows in different colors where we are processing over wide areas, tens of kilometers, hundreds or thousands of square kilometers, I should say, of LiDAR change detection at a regional level to understand what's happening. If we go back to the project level at the OSO landslide, we can understand why that might be so important. Because here, this is what we can see before what we call the landslide actually happened. The purple line in this is the headscarp when the landslide occurred. But all of the oranges and blues you see are movement that had happened in the years prior to the landslide. So I say that what happened on March 22nd in 2014 was that the landslide behavior changed. It had been moving all along. We were a little bit unaware as a community that it had been moving. This is a slide that shows LiDAR in the 7 years prior. It's the image you saw on the last slide up in the upper right. And then down in the film strip in the bottom are 3 years of change detection since that landslide happened on one particular day in March. And it shows that the ground is still moving, and it's moving again. These are the things that we are coming to understand in this revolution, and we need to know what that means. Is that significant? This is the valley that's just to the north of the valley where that last landslide occurred. We can see now clearly that there is landsliding happening in this valley that's very much like in the other valley. There's not been a tragic landslide here. Nobody's lost a life. The road hasn't been taken out, the river dammed in our history. But we can see there's lots of landsliding going on. Now it's possible in that same area, working with the Department of Natural Resources in Washington, we're adding L-band INSAR to multiple epochs of LiDAR. So we're getting change detection from aerial LiDAR overlain with change monitoring at a much more frequent scale by a passing satellite using L-band LiDAR. And together we're getting a really improved understanding of how the world works in Western Washington. So I want to say that the real evolution in this is not so much that it's at the project scale, it's at the regional scale. And if I call your attention to this same image that I showed you at the beginning of the presentation, if you look carefully now down near the beach at the coastline, you can see the blues and the reds that are LiDAR change detection, and overlain with that is the L-band INSAR. So just a few examples that I won't go too deep into, but it's fun to show. That's me as a young man digging a hole on a slope, trying to develop an early warning system for landslides. This is at the site scale if there ever was one, right? I'm sticking in tensiometers to measure water pressure, and I'm going to come up with a warning system that's very localized. Now, if you look at these images on the right, they are showing ERA5 land reanalysis. This is an interpretation of ground moisture, what I was measuring with those tensiometers over the entire Western Canadian sedimentary basin. Okay, this is a huge area, and these different images are different depth profiles, up to a couple meters below the ground surface. And with that, and with our inventory of slope inclinometers, and now INSAR, we can compare ground moisture as interpreted from satellites with ground motion and make regional warning systems much more effectively. There was a wonderful presentation yesterday on the Myanmar earthquake from last year. I can't begin to get close to that, but I do want to mention that one of the things we did in support, I work with an organization called GEAR, the Geotechnical Extreme Event Reconnaissance Association. And with others, we did work in this, and very remotely, we were able to quickly get an idea by looking at the loss of coherence in INSAR images and see where ground movement as a proxy for damage, because the image was no longer coherent between passing of the satellite. And we are also able to do something using a different satellite, looking at vegetation health. And vegetation health on the ground surface might be an indication of where there was liquefaction, but on steep hillsides, it's not likely liquefaction, it's landsliding. So we're using this as a proxy for understanding where landslides are occurring. Also in 2024, in the eastern United States, we had a very tragic hurricane. It was Hurricane Helene. It came up from the Gulf of Mexico and went along the Appalachian mountain range. And when it did so, it caused a lot of damage in North Carolina. And so what you're seeing here is the same kind of image. The blue is where we've had a loss in vegetation health. You can see some of the blue is along river channels. That's because they flooded. But some of the blue is actually along ridge lines. And if you look at the actual LiDAR imagery, because we're fortunate, North Carolina is a leader in this area, like Washington. They have a lot of epics of LiDAR. And so we have good coverage of LiDAR here. We can see that there is a real difference between the windward side and the leeward side of ridges and how much vegetation and presumably precipitation came into those places. I'm showing all this data in a platform called Cambio. You may have noticed that if you're watching carefully up in the upper left. That's a platform we use at BGC to manage all of this spatial data, because when you move beyond the project, getting these data together, whether it's vegetation health, INSAR movement, LiDAR movement, you need a way of managing these data, putting them together, and what I like to call interrogating the data, using one set to challenge another set and to get the best understanding of what's going on. Also within Cambio, we have Sentinel-2 imagery. So you have satellite images that you can do an image compare with back and forth, so you can understand the actual images along with the vegetation health, along with the ground movement. So that's an important evolution. Now, with respect to resilience, I think the evolution that I want to talk about is really my evolution and how I'm thinking about resilience. At the beginning, I had a very dramatic photograph of a highway in Colorado with a very elaborate, fancy retaining wall that had been overtaken by a flood, and it looked like a challenging problem to solve. Indeed, it was a challenging problem to solve. That's a catchy image, but this image, this explanation of resilience really resonates with me. On the horizontal axis here, we're looking at time. On the vertical axis is some kind of measure of performance. You can measure anything you want for your performance. It depends what you're after. But you're moving along in time at a level of performance. But then there's some kind of an extreme event, some trigger, something that knocks you off of that performance. It could be a GLOF, it could be a flood, it could be a landslide, it could be a windstorm. And when that happens, there's a drop in performance, and there's a drop, your lower level of performance for a period of time until you can do something to bring yourself back to that upper level resilience. These 4 R's of resilience, robustness, redundancy, rapidity, and resourcefulness, we often say that's what builds up a resilient system, a resilient piece of infrastructure. And you can get your resilience by combining those in any way you want. What we're really trying to do with using building resilience and maintaining resilience as a performance objective is to minimize that little blue trapezoid. And how you minimize that is up to you, and it should be different probably on your different project settings. But what recently came to my attention is the value of rapidity and what we as a community can do to build resilience through rapidity. Robustness and redundancy, these things take money, they take forethought, they take resources, and they're not always practical. But rapidity is a much easier way, in my recent recognition, to build resilience. This is again in Yellowstone National Park in 2022. It's what led the Federal Highway Administration in the road networks in the US to think more about resilience. This was a rain on snow type flood. These may be happening more in a changing climate. But it was a very devastating flood, and it wiped out a lot of roadway and access into the national park. In places where we couldn't have seen it, well, we didn't see it happening. This is in British Columbia. It's in 2021, so about 6 months earlier. It was also a rain on snow event, and it led to a lot of flooding. Here we use this regional LiDAR change detection, recognizing that in this corridor, there's a highway department. We move a lot of petroleum products, oil and gas through pipelines. There's a rail line. All of this is many different infrastructure owners needing to build resilience in their system, and the regional LiDAR change detection is the way that we did that. This is the state of Colorado. Debris flows crossing our major east-west highway in Colorado. It's the way that all goods are moved from Kansas to Utah in Colorado is across this interstate highway, and it goes through a dramatic canyon, and we often get debris flows on the road here. We have statewide remote sensing at this time so that we can help the state do things. But in terms of building resilience through rapidity, what really hit home was the Helene study for me. When Helene happened, I was on weekly phone calls with the U.S. Geologic Survey. There were hundreds of people at one point. You could hear the concern and the stress in their voices. They were tired, and they were mostly talking about how do we get to North Carolina and how do we go out and see what has happened so we can learn from what's happened. I'm kind of in the reconnaissance business too, so that made sense to me. I'm on these calls, but we're telling them we have a plane ready, just like the one, that very plane that's in that image. And inside that plane, there is a laser that can collect LiDAR over the entire area. I'm not quite sure what that bell means because I missed that, but five minutes? Okay, perfect. Okay, perfect. And what the message is that we were trying to get across, which we had a hard time doing because nobody had seen it yet, was that we could put that plane in the air immediately while you're talking about logistics of how to get out to the site. This plane could be surveying data coming in, cloud batch processing in the cloud. We have change detection like is shown right here in real time while we're having meetings on phone calls. We don't need to be waiting. And the sooner we do this, the sooner we understand what needs to be done to get this community back together. They lost water supply, they lost roads, they lost schools, they lost businesses. They couldn't get to their homes, they couldn't leave their homes. All of these things happened, but we could get this in time. It turns out we eventually did get this, and we are getting more of it now, but we had to do it through a research grant that took a lot of money, and that's not the right way to do this, and it's the missed opportunity, I think. These are some examples that I'm showing just now of the change detection, whether it's from landslides that you can see. In places you might see landslides that didn't mobilize completely. They're still hanging above a community. And this is an example where we can calculate the volume of material that's up there. We can calculate the volume of material that needs to be placed to rebuild this road, to make access for the community. All of this can be done without leaving the desk, all right? And this is some flooding examples again. This is my last slide, and what I really want to say is that we have the tools that can do this. We have these satellites. We know how to use them. We have airplanes. We have more and more LiDAR. We have LiDAR from major big drones now too. We have interpreted platforms like Cambio where we can get the most information. We get data, information, knowledge. We can get it all out of a platform like Cambio. But it's the professionals that's us, that need to follow through on this data to action. The revolution in data that's available to us does not mean that there's a revolution in knowledge. That's up to us to make that true, and we just need to watch for data coming from different directions. Now, I also know that a lot of us in the room, myself included, got into this business because we want to go to these places. We want to see the earth. We want to see earth processes. And I'm not saying that that's not necessary or that's not valuable. It's very valuable. What I am saying is that these new tools that are out there can answer all of what I call the what and the where questions. We don't need to spend our energy any longer trying to answer what happened and where. That can be essentially automated. What we can devote all of our energy towards is answering the how and the why. These are the important questions that need to be answered by the skilled professionals, and they're very relevant, and they mean getting your boots on the ground and doing field work as well. So my last point is to remember what I learned recently, my evolution in resilience is that speed saves. Go fast, you'll build resilience faster in that way. Thank you very much.
Thank you very much, Dr. Scott, for informative and instructive presentation. Yeah, we learn from you. The fast, the better. Thank you.
You're very welcome. Thank you all.
Thank you so much for nice presentation. We have a, do you have a minute? No? Okay. Scott is over. So, thank you for so much for nice presentation of all the keynote speakers. I would like to appreciate splendid keynote speaker for wonderful keynote session. This keynote session is closed. Okay?
Excuse me. Hello, everyone. We still have a bit of program left. We need to distribute the certificates and token of appreciation. So if you could sit for a while. One by one. We will announce.
Yeah. 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 We'd like to present a certificate for appreciation for keynote speakers. First keynote speaker is Dr. Ann Williams. Second presenter is Professor K. Jian Shou Sensei. Third presenter is Professor Daniel Joda. fourth presenter is Dr. Christian Zangard. Fourth presenter is Mr. Anil Pokare. Last keynote presenter is Dr. Scott Anderson.
I would request all the invited speakers to please come up on the stage so that we can take a group photo. Doctor, now I would like to request Professor Dr. Kumud Raj Kafle to present the token of appreciation to our chair and co-chairs. Thank you to all the keynote speakers, the participants, and who have been here throughout the session. There are a few announcements that I would like to make. If you have any presentation or keynote today, I would like to request you all to please hand over your presentation to our volunteers who are outside. And also there is a IAEG session ongoing in Koshi Hall, so all the IAEG member and interested people I would request you to go out in the Koshi Hall. Thank you. And we'll be starting the next technical session at 12. There is tea, coffee outside as well. So please help yourself. your attention, please. We are now going to start a parallel technical session. So I would kindly invite everyone to please be seated. And for this parallel technical session on landslide and risk evaluation, I would like to request Dr. Ananta Mansingh Pradhan to take his seat as a convener. And also, I would request Mr. Sudan Kumar Subedi to be the rapporteur of the session. Thank you so much.
Thank you. Good afternoon. Welcome to our next session. Theme is landslides and risk evaluation. I am Ananta Mansingh Pradhan. For now, I am a convener of this session. And I have rapporteur Sudan Kumar Subedi with me. And this session, it will be very interesting session. So time is precious. So without any delaying, I would like to call Professor Yunte Kim, invited lecturer, and his presentation is about quantitative debris flow in this vulnerability assessment. And before that, I would like to tell you about the rule of this presentation. Yeah, you will be informed like this. Before 5 minutes, I will give one buzzer. And if you have 2 minutes left, then I will ring 2 buzzers. Okay. So, Professor Yunte Kim, I would like to hand over the mic to you. Thank you.
Yeah, thank you, convener. Yeah. Good afternoon, everyone. I am Yunte Kim from Bugyeong National University, South Korea. It is my great honor to deliver an invited lecture at 15 ARC of IAEG. Today, I'd like to talk about quantitative debris flow risk assessment with partially focused on how different building structure responds to such hazard. Before starting my invited lecture, I'd like to express my sincere thanks to National Research Foundation of Korea and CACTEP and KATE for their invaluable support on this research. Also, I'd like to express my deep appreciation to my colleague, Dr. Kang, Dr. Pradhan, Dr. Lee, Dr. Bin, Dr. Song, and Mr. Dewey. So without their dedication or contribution on this research, I cannot deliver this invited lecture. Okay, landslide is movement of mass of rock, debris, earth down the slope, so-called mass movement under influence of gravity. This landslide include rock slide or landslide, debris flow, or submarine slide. This figure shows worldwide casualty from the natural hazard, including landslide, storm, earthquake, and flooding. Left-hand side, you can see that from 1980 to 2000, the portion of landslide casualty is about 15%. But right-hand side, from 2000 to 2024, this portion slightly decreased up to 9% due to the increase of storm or earthquake casualty. However, if you consider number of fatal landslide, even though annual budget or effort increase to prevent landslide, number of fatal landslide does not decrease mainly due to climate change or people living in landslide-prone area. Okay, this figure shows the triggering factor of landslide. If you can see in this figure, mostly rainfall, human impact, or earthquake is the triggering factor. But if you can see here, the rainfall especially intense rainfall, is main key triggering factor of the landslide. Also, this climate change caused the hotter temperature, more severe storm, and more severe precipitation. Okay, let's start with risk. Risk is possibility of loss or injury or other unwelcome circumstance. The spelling risk originally come from rescue as of 1621 French word. Risk is a complex interaction between hazard, vulnerability, and element at risk. According to United Nations Office for Disaster Risk Reduction, hazard is a natural process, phenomenon, or human activity that may cause loss of life, injury, property damage, or social and economic disruption. Vulnerability, you have different conditions of vulnerability: social vulnerability, physical vulnerability, economic, environmental vulnerability that increase susceptibility to hazard impact. Element at risk or exposure is presence of people, infrastructure, housing, production capacity, or other tangible asset in vulnerable area. Okay, this figure, you have small shark. It might be cute. It is hazard, but there is no risk because no element at risk. Once a person enters the water, so now you have risk, disaster maybe. Let's assume this person would be Iron Man. So in that case, no risk because of no vulnerability. So risk, in order to risk analysis, we have to know hazard, vulnerability, and element at risk. So as I told you, so in left-hand side, the down, there is potential for landslide occurrence, but low risk. Right-hand side figure, so you have element at risk in vulnerable area. So now you have risk. So here is the vulnerable society. So if you have hazard, you have risk. This is the risk. So urbanization or bad land planning or complex society increase vulnerable society. Also, more severe rainfall event due to climate change increase the hazard impact. So now you have larger risk. So in order to risk analysis or management, we have to know several things: where, when may landslide occur. This is temporal or spatial probability of landslide, and which place are vulnerable. Also, we have to know. So how much vulnerable exists, and finally, what would be yearly risk would be. Debris flow is fast-moving mixture of water, soil, and rocks and organic materials flow down a channel or slope, especially during rainfall, heavy rainfall. Debris flow causes serious threat to life or property, especially in mountainous and landslide-prone area. This debris flow is hazard. So in order to risk assess, so we have to know not only hazard intensity, but also vulnerability of the infrastructure. So vulnerability is how likely structure may be damaged when impacted. So urbanization have significant increased the risk of debris flow to the house located in mountainous area, especially in South Korea, which cities surrounded by the mountains. Different housing, most of which are on reinforced masonry, light steel frame, wood structure are located in landslide prone area. And the damage degree of the house strongly depends on structural rigidity of the building, even when exposed to same hazard intensity. However, structural characteristics of buildings are usually disregarded in vulnerability or risk assessment. Also, we have three different types of the risk assessment: qualitative method using risk matrix, or semi-quantitative method using indice or special multi-criteria evaluation, and quantitative method using probability approach. Main objective of this presentation is to develop physical vulnerability curve considering housing structure which located in boundaries area of the landslide prone area. In order to achieve this objective, we collected and analyzed debris flow event which occurred in South Korea. Also, we analyzed relationship between hazard intensity and observed damage level. Also, we finally assessed quantitative debris flow induced risk assessment. Okay, this figure shows the framework of the risk analysis. So in here, so you can get the temporal probability of the landslide. In order to get temporal probability, you need to carry out rainfall infiltration analysis and a physical infinite slope model using Monte Carlo simulation, so you can get landslide temporal probability. Also, in this temporal probability, you can consider a climate change effect using a stationary or non-stationary extreme value analysis. Left-hand side, okay, if you have machine learning model, you can consider many various conditional factors such as topographic, hydrologic, and geological or soil conditions. And if you have landslide inventory, you can take using machine learning model, you can get susceptibility model. That is the landslide spatial probability. If you combine temporal and spatial probability of landslide, you can get hazard map. From this hazard map, you can imagine which place is the source area of the landslide. And from this source area, you can, using numerical analysis, and you can calculate impact pressure acting on building. So, sorry. Okay. So from that impact pressure, you can, if you have vulnerability curve, you can get the specific degree of risk. So vulnerability is expressed by degree of loss or damage to a given element. Vulnerability 0 means no loss. Vulnerability 1 means total loss. From this figure, so doesn't work. Oh, okay. Now working. I'm sorry. Yeah. So from that figure, you can see that vulnerability highly depends on debris flow intensity, x-axis, and structural rigidity of the building. That is the y-axis. So 2 is very important component. So you have to know what is so how can you estimate correct impact pressure in x-axis. So even though same hazard intensity provide different vulnerability, that depends on the building types, building structure types. So regarding to hazard intensity, impact pressure, we can calculate from that equation. So alpha is the empirical coefficient. But this is very difficult to measuring debris flow impact pressure directly in the field. So many researchers used plum experiment that provide high reproducibility and repeatability. However, laboratory scale plum experiment have a limitation in replicating real debris flow due to simplified topographical conditions and short travel distance. For example, most experimental fruit number range between 1 and 8. But in reality, debris flows may exceeding 30 numbers. So therefore, in order to calculate exact impact pressure, we have to develop reliable vulnerability curve, and it is very essential to estimate exact impact pressure coefficient through back analysis of the debris flow in various field conditions. So we collected 288 debris flow case. From this case, we consider both geomorphological and geotechnical characteristics. Based on this analysis, we proposed empirical equation between impact pressure and fruit number. That equation shows that the wide range of the fruit number is up to 43.6. So that is more higher value, beyond the value from the laboratory from test. Since previous study were conducted through plum experiment, there are significant difference in empirical coefficient due to difference in runout distance, slope angle, and flow volume. Okay, so now we have two different building conditions. Okay, so one is the reinforced concrete frame structure, that is the reinforced masonry, reinforced concrete or steel moment. For non-RC frame structure have steel masonry or wood structure or lightweight steel frame. So we collected debris flow event and damaged building up to 22 debris flow event and 87 damaged building. So we classified the degree of damage according to Hedges MH. So we have 4 different damage level, which is the slight, the vulnerability is 0.1 to 0.3, means slight or non-structural damage, stability not effective, damage to furnish or fitting. For regarding to complete damage, the partly or totally destroyed, evacuation necessary and complete destruction is required. So this figure shows the damage level. So reinforced concrete or reinforced masonry, that is the RC frame structure, and lower is the non-RC frame structure. So non-RC frame structure have vulnerable to debris flow impact, likely to experience complete collapse or severe damage. However, RC frame structure, high resistance to the impact, likely to experience minor damage or maintain unchanged. So this is proposed physical vulnerability curve for each type of the building: brick, masonry, lightweight steel frame, or wood structure. So, okay. So threshold to slight or moderate and extensive and complete damage is referred to PM, PE, or PC. So value of the impact pressure threshold, the PM, are slightly similar among the structural types: unreinforced masonry or lightweight steel frame, or wood structure. However, there are significant difference in the value of PE or PC among the various structural types. So non-RC frame structure rapidly increase in vulnerability curve at low impact pressure up to 5 kilopascal, reaching nearly total damage vulnerable equal to 1 at over 100 kilopascal. But RC frame structure more gradually increase higher resistance to impact pressure, can withstand up to 500 kilopascal. So this is the example of the application. So this is 2025 debris flow event in Sancheong, Korea. So we have 19 fatality and 45 cases of the building damage. So this is another case in the Sancheong. Okay, so this figure shows the debris flow simulation at Buri station. So this numerical simulation, so you can calculate velocity of the debris flow. From this velocity and empirical coefficient, you can calculate impact pressure acting on specific building. So from that impact pressure and vulnerability curve, you can predict what is the predicted vulnerability of the building. So left-hand side building is the observed damage. Right-hand side figure shows the predicted damage. So if you compare two figure, so mostly the damage condition is almost same. Also, we applied to 2023 debris flow event in the Yecheon County. So we have 23 fatality and 77 damaged building. So right-hand side on left-hand side is the observed damage and predicted damage. So if you compare, so specific building have specific impact pressure. So also they have specific damage degree, depends on the impact pressure. So let's apply to risk assessment for specific building. This is the mountain Abusan in Hiroshima. So if we have input parameter, you can calculate the landslide temporal probability, which depends on the return period. Also, if we have the many input parameter and machine learning model, you can get special probability map. So if you combine, that is the hazard map that depends on a return period. Also, if you numerical analysis from the runoff propagation, you can calculate impact pressure. And using vulnerability curve, you can predict how much of the building would be impacted, which that one. Okay, that is the equation for risk index. Okay, so this is the risk index for specific building. So proposed framework of the risk assessment. Okay, this is the risk curve. This curve depends on 6 hours or 12 hours rainfall durations. Also, you can see in this figure inverse relationship between risk index and probability, where risk index increase as the probability decrease. Degree of the risk increase as return period increase from 5 to 100 years. Okay, this is the example of the quantitative risk assessment of a specific building. So from this procedure, you can get the risk curve for RC frame structure and non-RC frame structures. Okay, now we have to finally get summary. So as I told you, this vulnerability curve highly depends on debris flow, impact pressure, and structural rigidity of the building. So we also proposed the impact pressure coefficient, alpha, in order to get reliable impact pressure. Structural type-based vulnerability curve, the different building have different vulnerability index at same hazard intensity. Quantitative risk assessment, this concept, so we need to hazard and vulnerability at element and risk. Risk depends on structural types, so non-RC or RC frame. So in order to build risk-free society, we need several reliable landslide hazard vulnerability or risk mapping. Also, we have to implement appropriate landslide risk management action. Sometimes we need litigation measures. So here is my limitation of this presentation. Thank you.
Thank you, Professor Kim. Actually, we have time constraint. Field-based data to simulation and predicted to the space is a very important thing. And for hazard mapping and hazard-free society, this kind of resource is very, very important. So thank you so much for your wonderful presentation, Professor. Thank you. Now, I would like to hand over this mic to my colleague, my reporter, Mr. Subedi, because I have presentation, so I cannot complete the dual role. So, Subedi, Mr. Subedi, please.
Okay, thank you so much, sir. And I would like to welcome Ananda sir to present his presentations.
Thank you. Okay. Thank you so much for having me here. I am Ananta Mansia Pradhan. I am working as a Senior Divisional Engineering Geologist at Water Resources Research and Development Center, Government of Nepal. Actually, this research doesn't have any rocket science type results, but our focus is mainly how do we move from landslide hazard assessment to action plan, especially in the terrain like Nepal, Himalaya. So, this is the background of my research. The position of Nepal in disaster scenario. You can see the global climate risks. Nepal is always inconsistently ranked among the top countries, and most of the landslide-prone country in the world. And similarly, Nepal is extremely vulnerable to major earthquake, and which initiate in the landslide as well. Increasing glacial melting because of the climate change. We are now facing different type of risks of gulf. Similarly, above the top, the urban vulnerability, which is maybe due to the unplanned management or without considering the engineering geological property. So we are now facing this kind of earthquake, fire, or other urban flooding condition we are facing. So from in the right side, you can see that in the different casualties, landslide govern about 36% of the casualties in Nepal, and this data is from NDRRMA during the period of 2010 to 2025. Now, the landslide batters Nepal every year because there are some key factors like fragile geology, high relief, and intense monsoon rainfall, seismic activity, and unplanned land use, which trigger the landslide. And as we know that Himalaya is still rising, and that's why the rock condition is in strained condition. That's why the Himalaya tectonic activity, diverse rock type, and steep topography, weathering condition, and human interaction with geology, it initiates the landslide in Nepal Himalaya. Now we can see the rainfall pattern, about 80% of total annual rainfall is concentrated during the monsoon period. And you can see landslides are very common during that period. And due to the climate change, Nepal is experiencing short duration and high intensity rainfall. And that's why in the monsoon period, we are facing so many landslide disasters. And the climate change, the global warming, how it can initiate the landslide or trigger the landslide, we can see that if the global temperature rises, the evaporation also rises, and the extreme rainfall or extremities also rises. That wash out the terrain. And this is the trend of landslide occurrences in Nepal. We can see so many tiny points in all over Nepal Himalaya. Actually, these are the fatal landslides only. And this landslide data are collected from 1970 to 2025, recent, today, until today. In that period, from 1970 to 2025, about 5,600 fatal landslide was reported, and similarly, more than 4,000 fatals are recorded. The occurrences of fatal landslide in Nepal has increased in recent years. So in that figure, you can see the casualties rate is increasing year by year. So we have analyzed the hotspot of landslide in the period of 1970 to 2023, actually. And I have split the timeline between 1970 to 1995 and 1996 to 2023. You can see the hotspot the trend is not drastically changed. But in the western part, you can see there are in the period of 1996 to 2023, the hotspot is now expanding in the western part of Nepal Himalaya. It may be correlated with the unmanaged road construction. So in the down here, you can see when we build the road, and we always consider about the green road belt. But every monsoon season, the green road, the concept was green road, but it turned into the brown road. So the rural road building and that kind of program which coincide with this kind of increase of the hotspot of the landslide. So landslide identification is very, very important because we are now approaching to the landslide susceptibility map of Nepal Himalaya. So for the landslide susceptibility map, the world national-wide landslide inventory is must. And in Nepal, this kind of data acquisition is too difficult. So we try to use the remote sensing technique, and in that remote sensing technique, we use Sentinel-2 data and different indices like NDVI, other SRTM slope and aspect, and we manually digitize about 5,000 landslide for the training. And from that, so we can see that the segmentation process was done, and from that segmentation process, we can predict which may be the landslide and which is not the landslide. And remember, these all things I am doing about the shallow landslide, not for the deep-seated landslide. For this deep-seated landslide, we need more exercise and more time. So this is the process. Just make a make the segmentation, and we can predict the landslide using the manually digitized landslide. So this is the result of our landslide inventory. You can see the distribution of landslide with respect to its size, because size does matter, and shows probability of density of landslide decreases with the increase of the size of the landslide. And it also fit the power law equation as well. And this is the Nepal landslide inventory map of whole Nepal Himalaya. Now it has already, we have already depicted about more than 300,000 landslides. Now the second step is the preparation of landslide susceptibility. And landslide susceptibility is a relative likelihood. So for that relative likelihood, we have collected several causative factors like geology, slope, elevation, and rainfall, etc. So from that, we use a machine learning technique, and very simple type of machine learning and similar type of machine learning we use, like XGBoost, light GBM, and random forest. So from this simulation, now the accuracy, we can see the accuracy is perfect and almost similar with these three models, like XGBoost and LGM and random forest. It's about 87–89% accuracy it has. And we also implemented the K-fold or 5-fold random cross validation. The black rectangle represents the test data in the on a right side or left side of figure, and other is remaining part represents the training data. So from that, we have made the landslide susceptibility map of Nepal Himalaya using 3 different models. But we are not relying on single model. So we try to ensemble these three models to make the perfect landslide susceptibility map without any bias. So we combine these three results with the generalized linear model, GLM, for the better prediction. And this is the landslide susceptibility map of Nepal. Now you can see the red zone is the probable occurrence of landslide, and the sign color, blue color is there is less landslide. Similarly, now what we will do, there is a technique. Let's use this landslide susceptibility map for the plan action. So action plan. So we use a landslide hazard assessment for situational awareness. This algorithm was first developed by NASA, and we try to modify this algorithm. And the algorithm is known as LASA 1.0. So LASA first check the heavy rainfall, and then it identify the highly susceptible areas, and finally it outputs a global map for the most hazardous location. And this, in this chart, you can see that there is a 7 days antecedent rainfall, and that antecedent rainfall is divided into 95% percentile, and that 95% percentile above that is high rainfall, and lower than 95% percentile is the low rainfall. So from that we can give an alarm level to the settlement. Now here we use the IMERS data, because in Nepal it's very difficult to get the data, and we have very sparse rainfall stations. That's why we rely on the IMERS data. So IMERS data has 0.1 degree resolution, spatial resolution, and 30-minute temporal resolution. So we use that data to make the landslide hazard or landslide nowcast system. So antecedent rainfall is a simple type of average weighted method. So from that average weighted method, we can predict the 7-day rainfall, and from that 7-day rainfall, we can give a nowcast, what will be happen today. So from that, now we can make a landslide nowcast system. We already implemented, and we already formed one Google Earth Engine application, that is a landslide nowcast system, which was developed in Google Earth Engine, and it's named as Landslide Hazard Assessment Model, LASA Nepal. So you can also see that apps by scanning that code. And here is the final landslide hazard map, or landslide susceptibility map here. Now you can see we are getting very mixed type of feedback, because in the eastern part we have very good result, but in the far western part we are very difficult getting that kind of good result. And recently, on the night of 4th and 5th October 2025, heavy rainfall and continuous rainfall integrated multiple landslide in Ilam district. And in Ilam district, you can see the stars are the landslide events, and these red are the nowcast. So that nowcast is little bit higher. I mean, there is a miss or false alarms is high. So we are trying to modify this kind of map, and we are also working on the long-term prediction using our climate data, using SPS and different scenario. So this is our conclusion, and this start with the field database and prediction, and then it can be implemented into the early warning system. So the conclusion you can read there. Thank you so much.
Okay, thank you so much, sir. And looking over the time limitations, I would like to welcome Masahiko Osada to his presentations.
Thank you, convener. I'm Masahiko Osada from Saitama University, Japan. Today, I would like to present entitled Fundamental Study for Real-Time Inundation Depth Estimation using a new weather radar. this is a new topic for my lab. So just started 1 year, last year. Okay. And then here is the contents of my presentation. First, after stating the background and objectives, I introduced the characteristics of the MP-PAR. MP-PAR is a multi-parameter phase array weather radar. That's the abbreviation. And then we report the results of the flood simulation using rainfall rate values obtained from MP-PAR in the target areas. Okay, and then this background. Many research presenters already said that in recent years, with an increase in typhoon and torrential rains, many regions experienced flood damage caused by inland water overflow. So, however, despite the frequent inland flood, the real-time flood prediction information is not publicly available. Therefore, this study aimed to develop real-time inundation depth estimation method specialized for inland flooding. It utilized the all-sky raindrop distribution observed at 30 seconds intervals by MP-PAR installed at Saitama University. So MP-PAR was developed under the first phase of the SIP program organized by Cabinet Office of Japan. Until then, MP radar utilizing polarized waves and the phase array weather radar employing the digital beamforming technologies exist separately, but the hybrid combination of these two radars enable us the observation of the 3D structure to be completed in just 30 seconds. Previously, it took 5 minutes. And then this is observation range of the MP-PAR. The star indicate the location of the Saitama University. We are currently conducting the continuous observation within a 60-kilometer radius shown in the blue circles from the Saitama University. In the low level mode, the shown in red circles, it covered almost the entire Arakawa River basin, one of the major river systems in Kanto Plain. This animation was created by Professor Nobuhiro Takahashi, Nagoya University. He is a leader, our group leader of the SIP project. And then to show the potential of the MP-PAR, it showed the movement of rain cloud over the Kanto Plain by MP-PAR. So here, red part is Kanto Mountains, and then arrow show the Tokyo Bay. So length of the horizontal length is around 100 kilometers. So in the vertical, we take the 15 kilometers. So it means the rain cloud is starting from the Kanto Mountains and then a little bit gradually moving to the east. And then please focus on the red part. That is a lot of raindrop is concentrated around here, around there. And then firstly, it gradually raising up and then go down. Can you see that? That is a mechanism of the torrential rains. So this figure shows a schematic illustrate such a development of the process of the rain cloud that produced localized torrential rains. So water vapor water vapor rise to form the cloud that only when the raindrops become large enough is later echo was detected. Having continued to develop, the raindrop is developed, it's been growing up, and then raindrops is falling down by their own weight. And then finally, bringing the rain to the ground. So inland flooding occurred after the heavy rains. Therefore, if the total volume of the raindrops during the peak period around there in the middle, so it is possible to estimate the rainfall on the ground in 10 to 20 minutes later. So this map shows the location map and elevation map of Koshigaya City. This is the target area of this study. Koshigaya City is located in eastern part of the Saitama prefectures and features a typical plain topography consisting of upland and lowland. The figures show a location map of the Koshigaya City and elevation map as presented as a color map. So elevation, the range of the elevation is 1 to 7 meters. It means the almost all area is below 10 meters. So in Koshigaya City, inland flooding occurred due to the typhoon in June 2023. At that time, 25% of the city area is inundated. Here is our rainfall record, and then the total rainfall over 2 days is 203 millimeters. So firstly, we examine whether the analytical rainfall is comparable to actual rainfall measured at ground surface. So our rainfall at the Koshigaya Amedas station were compared with the rainfall rate values of MP-per analyzed mesh, which include the Koshigaya Amedas station. So as a result, you can see this figure. So although the analyzed rainfall show the slightly higher value, if it can be seen that a good correlation has been obtained. So next, we conducted a flood simulation using the module in ArcGIS Pro. This module solving shallow water equations with setting rainfall intensity and the infiltration rate, infiltration into the ground. Rainfall intensity, we used 2 cases. One is Amedas hourly rainfall, and then case 2 used the MP-per rainfall rate, converted to normal rainfall. At this time, rainfall is being applied uniformly across the entire analytical domain. So infiltration rate is also set as 5 millimeter per hour for farmland and green spaces. And also for other areas, it's set to be 0. Simulation was conducted under these conditions for 48 hours period starting at midnight on June 2nd, 2023. This is a result. Start. Okay, it start. On left-hand side is for from the Amedas data, and then right-hand side show the from the MP values, like this. Pattern is quite similar, and then we can compare the such result, the water depths at each point. The finger, left finger show the inundation area on flood control topography classification map. The inundation area are concentrated in flat plains and all the river channels enclosed by a natural levee. Yellow part is a natural levee, and then pale green is a flat plain, and then a little bit green part is a back swamp, like that. And then figure B show the flood simulation result at 1 a.m. on June 3rd, when the rainfall peaked. So comparison both figures, the areas with a deeper inundation depths generally correspond to actual flooded areas. So next we check the time history of the numbered positions marked in these figures, 1, 2, 3, 4, 5, 6. This is, from this figure, it can be seen that the water depth changes over the time at all locations. The time at which the water depths begin to increase differ at each location. The rate at which the water depths increases with increasing rainfall also differed. And also, especially in point 2, orange line, show the very water depths exceeding the 4 meters. What happened, we think, and then check it, maybe around, it's located in the regulating reservoirs with a water level of 4.41 meters. Therefore, it was considered that the flooding was not significantly in its vicinity, indicating that the regulating function was working effectively. Okay. The further work, we think that following these flood disasters, Koshigaya City has a deployment of the numerous flood sensors moving forward to construct flood depth prediction systems for inland flooding using the MP per 30-second interval data. It will be necessary to obtain or utilize flood depth data for each extracted inundation area and incorporate the respective drainage capacity in its model. Here is a summary. Using this MP per rainfall intensity data, we conducted a flood simulation for 2023 Koshigaya flood. This reconfirmed the microtopography, such as natural levee, all the river channels, and flood plains, significantly contributed to flooding in plains area. Moving forward, so we plan to maximize MP PER's capabilities and advanced preparation toward the building real-time system capable of issuing flood warning before inundation occurs. So here is acknowledgement. Thank you very much for your attention.
Thank you very much, Professor Osada, for your wonderful presentation. Thank you. Yeah, due to the time constraint, and interesting that I noticed that we have another session immediately after this session without any break. So I have to move. Already we are late, so I have to move for another session. So how can I give this map? Oh yeah.
Ananta sir, if you could come here, we would do the certificate ceremony.
have a certificate program here. So first of all, I would like to invite the invited speaker, Professor Yunte Kim. Please come forward. So I also getting one certificate. Professor Osuda, please.
Now I would like to request Professor Dr. Kumud Raz Kafle to present the token of appreciation to Chair and the Rapporteur. Thank you so much for the chair and the rapporteur of the session. Now I would like to move to the next session under the theme, the training and education in engineering geology, with the sub-theme communication and education based on knowledge of engineering geology and how to get your paper published in Journal of Mountain Science. And for this, I would like to request Professor Atsuko Nonomura to be the convener of the session. And also Sanjeev Pandey and Mohammad Hossein Alam to be the rapporteur of the session. Thank you. Over to you.
Thank you very much for giving me this opportunity. And this session is training and education in engineering geology. So both training and education is related to community. So communication. So first I want to talk about why communication is important in geology. And I'm member of Japanese Society of Engineering Geology. So let me introduce JSEG activities related to the geological communication. And then I want to talk about case study of communication and application of engineering geology for community-based disaster preparedness. So why communication is necessary for geological society? No science is independent of other sciences, and geology is based on many other sciences in particular. So in order to conduct academically significant research, knowledge across multiple fields, such as physics, chemistry, and mineralogy, and biology is required. And in order to understand one geological phenomena, several fields approaches are necessary. So communication among geologists with several backgrounds is indispensable to find the answers. So why communication is necessary for engineering geology? If the construction project starts, communication for the construction of structure between contractor and geologist is necessary. And if After construction is completed, communication for user of construction and disaster management between users and geologists is necessary. So in order to have good communication, we should understand the difference between each other. Why? Differences in geological experience and knowledge. There was very interesting document published in 1902. In this document, they say, they analyze and compare several science fields. And also they talk about the differences in communication between experienced geologists and children. So based on this document idea, suppose experienced geologists and children to be standing before some complex geological phenomena. For example, Yashima is one of the most famous places in Kagawa. Kagawa is my university's location. So this is the Yashima, and if the children and experienced geologists visit, the image on the retina is absolutely the same in the eye of experienced geologists and that of children. So if they are asked to state what they see, how they answer. There might be gap of the statement. The statement of children, the most general and just what they see. However, on the other hand, experienced geologists interprets are based on a knowledge of the principles of several fields of science. They understand what is important and what is unimportant. They select and record the things which are important. So let me suppose more experienced geologists and children go to Yashima. This is that left-hand side figure shows the geology of Yashima. Base is granite and basaltic tuff and the top of Sanuki andesite. And if they visit the red flag points, they find weather granite, but some places they find terrace containing andesite gravel. So if children find this, they say there is rock and soil. But if the experienced geologists say, where is the source of the gravel and what kind of phenomena occurred? So their comments are very useful for understanding the hazard in this area. So the way to learn how to think and how to interpret is through communication in the field. So if the highly experienced geologist go to Yashima, he say the basaltic tuff deposit at Yashima are strata that accumulated in a lake. It is presumed that there was a lake surrounded by mountain in 14 million years ago. So 14 million years ago, Yashima, so if like 40 million years ago, Yashima is lake. The current topography is the red line, but 40 million years ago, Yashima is lake. So geological time scale are vastly longer than human time scale. So the scale of the event and frequency is inversely related. So it is difficult to prepare disaster because frequency is very low. But geologists can provide crucial insight for planning countermeasures against low frequency and large-scale disasters. So let me introduce the JSEG communication-related activities. JSEG have many activities. for example, education and support for learning hazard from natural disaster memorials, and communication disaster prevention activity support. In my presentation, I want to introduce to you education and communication disaster prevention support. So in the case of education, training for mid-career and junior engineers, and technology transfer and enhancement of survey and analysis techniques. For example, this is one event, one-day lecture and three-day field training. So this is the contents of lecture, fundamental natural disaster geomorphology and geology, and disaster recovery measures, and similar disasters, and case study of disaster survey using drone. So, and hazard map creation, and interpreting natural disaster from monument, stone structures, and field survey guidelines. And after lecture, they visit field training. This year, they visit in Hakone, and during the training, they did survey of typhoon damaged site in the Hakone volcano region, and also they visit geopark. And young geologists learn from the senior in the field, like this. And also learn and discuss in the field training. So in the field training, they communicate, and young geologists can learn a lot. And also senior geologists know what the young geologists are thinking. So I think this is a very good opportunity for engineers. So now I want to talk about support for community disasters prevention activities. Extreme weather patterns have caused disasters, and unprecedented disasters occur all over the world. How to prepare for never experienced disasters in community. This is very difficult because no experience for them. So insights based on terrain formation provide clue for predicting disaster of unprecedented scale. So one example is support the community where people living on the large-scale landslide. This picture shows the study area. In this picture, several houses are distributed, not so many, but some houses are there. The designated evacuation shelter for this area are not shown in the photo. Outside of the photo, left side, this is the designated evacuation shelter. So communication evacuation plan for heavy rainfall, general approach is before the heavy rainfall, check the hazard map and decide where to go and when to go. And during heavy rain, evacuate to designated public shelters. In the case of slope area settlement, slope area estimation is difficult as compared to flooding because inside the slope we cannot see. On the hazard map, the disaster-prone area are designated only surrounding the house. That's why this left-hand side map shows the hazard zone, but it's not continuous because only near the house the area is designated. So there are several roads with no hazard information. The public evacuation shelter is located very far from the house. So where should we evacuate? This is a very significant question for local people. So the local government of Crisis Management Division and Geopark Promotion Division and researchers support resident group living in the slope area settlement. this is the flow of this study. First, collecting local information with interview and field survey, and analyzing and visualizing the hazard by using GIS analysis, and evacuation planning for the heavy rain, so with workshop and discussion. So slope classification for understanding slope geomorphology and disaster propensity by using curvature across the slope and curvature along the slope. So we decide the horizontally concave slopes, drainage topography, so caution of water flow and debris flow is required. So most left-hand side slope types. And horizontally convex and flat slope, this is non-drainage area, so relatively safe during the heavy rain. However, steep slopes in this research, we set the threshold is 30 degrees. So steep slopes are susceptible to slope failure. So by using them, we classify the slope. In this research, we use 5-meter resolution DEM and calculate plane curvature and profile curvature. And by using these two curvature, we classified 9 slope type we make the 9 slope types classification. And horizontally convex slope, and horizontally concave slope. And by using mean curvature, we extract drainage. And by using slope and convex and concave curvature, we categorize 3 types of slopes. So horizontally concave with steep slope is prone to slope failure. And horizontally convex with gentle slope, we think this is relatively steep slopes. And concave and drainage, we think this is debris and water flow susceptible slopes. So this is the visualizing hazard maps. So yellow color shows the slope failure prone area, and blue color shows debris flow and water flow area, and red parts is relatively stable area. So we validate slope field survey with local community people. So blue point, the figure shows the upside, and when we visit there, spring water flow constantly, even in the not rainy day. And the local people say the rainfall days, in this area, the amount of water is very large, and huge amount of water is going down. And yellow point, during we visiting, nothing happened, but the community people say rockfall have often occurred. And also same validation we are done. So the blue point, there was a debris flow, and yellow point, slope failure have occurred. So by using this map, we try to plan evacuation. We try to make the evacuation planning by using the topographic map. The community people say this map is good because easily find pixels with relatively slope terrain in their residential area by using this map. But I think, and another researcher also think, this method is insufficient with consideration of the surrounding terrain and large-scale landslide. So for example, this black circle shows the red color. Red color means relatively stable slope. And when when we talked to the old man, he say I'm 80 years old and 8th generation to live in this house. And since there has never been a disaster here, I think it is safe, even during heavy rain, he said. But I cannot say this area is safe because many drainage come together closely close to this area. So how geologists tell to the old man, I guess the alluvial cone at the valley exit was formed by a past debris flow. So there is a risk of future debris flow. So in this research, I think more support of preparation for low frequency, large-scale disaster is necessary. So conclusion, communication in engineering geology is necessary to understand what occurred in the past, and it's useful to estimate what will occur in future. JSEG engage in numerous activities related to communication in geology. I think you'll want to visit Japan. So in 2027, JSEG will host the 6th Asian Regional Conference, ARC16 in Japan. So thank you for your kind attention and welcome to ARC16 in Japan. Thank you very much.
Thank you, Professor Dr. Sako Nonomura, for your nice, informative presentation.
Okay, let's start my presentation. And my name is Hiromi Kaji from Oyo Corporation. And before my presentation, Professor Dr. Nonomura explained the communication is very important for our work and for the engineers. And so that's today I want to present the title, Enhancing School Safety Activities, the Contribution of Geological Engineers, an example from Tochigi Prefecture's elementary schools. Okay. And at first, I would like to explain about the background of school DRR education in Japan. Japan continues to face risk from diverse natural disasters, including a major earthquake, directly under the capital, a massive Nankai Trough earthquake, and more frequent and intense heavy rains and typhoons. Disaster prevention education for students, in particular, is promoted with the aim of enhancing their awareness of disaster risk for fostering the ability of make approximate judgment and take appropriate actions during disasters. And next one is numerous disaster prevention education programs such as explanations of disaster mechanisms have been implemented to date. Furthermore, while research exists in higher education institutions and many private companies conducted disaster prevention classes or lectures and create or distribute awareness materials such as initiative remains limited. Given the geological engineers can contribute significantly to school education, this study examines how geological engineers can contribute to school DRR education and what outcome can be expected. Okay, next page. Yes. And in Japan, in Japanese school, disaster prevention is considered part of safety management school, part of safety management. Schools are required to implement not only pre-disaster measures, but also provide psychological care after an incident. As a result, the scope of responsibilities that school must handle is extremely broad. And school safety management includes not only disaster prevention, but also everyday safety measurements such as preventing injuries, illness, and traffic accidents. In accidents, all stages, before, during, and after an incident, and cover a wide range of responsibilities that school must manage. And the methodology of this study. This study was conducted through semi-structured interview with teachers and schools and responsible for the target elementary schools. The interview items are follows. Interview contents was recorded and transcribed verbatim, then analyzed as quantitative data. The items are basic policy for disaster prevention education and specific implementation contents and collaboration with parents and communities and challenges and further directions. And the next is result. And about the basic policy for disaster prevention education, there are two main targets. One is cultivating an attitude for proactive action to protect one's own life according to surrounding circumstances and enhancing instruction on fundamental knowledge and pinning disaster prevention education. And this is an example. This is the learning contents for 5th grade in elementary school. And the left side is the social subject. In social study subject, the students learn life in lowlands and life in highlands. And in this subject, students learn about the general outline of the topography and claim prevention of natural disasters, and the relationship between the information society and people's lives, and will be encouraged to consider how the environment of the country is closely related to people's lives and industry. And the right side shows science subject. They learn the contents, the function of flowing water. To help students develop an understanding of the fact that flowing water has the function of eroding land and transporting and depositing stones and soil, that rising water level can significantly change the appearance of the land, and that the amount and movement of clouds are related to change the weather. Okay. Next one is about the specific implementation contents. Specific implementation contents are conducting evacuation drills. The target school conduct 4 times annually drills. For example, the earthquake and tornado, fire, and action to take when the outsider can enter the school. And in this school, why students or why teachers conduct the evacuation for tornadoes? Tochigi Prefecture has a topography and climate conditions that are prone to tornadoes. Therefore, training is conducted to prepare for tornadoes. The photo left shows this is for the evacuation drill, the scene for the drill for tornado. And the students close the curtain, then they evacuate the opposite side of the windows. Then they sit down and make a small, like a circle, or make a small figures. And the right side photo shows the fire evacuation drills carried out under the assumption that fire breaks out for an earthquake. The drills are conducted with the cooperation of firefighters. And next one is a collaboration with parents and communities. Shown as in previous slide, handover drill conducted in collaboration with parents, as well as evacuation drill conducted with the fire department and police. Fifth grade learn how to create a personal timeline for flood preparedness and cooperation with DRR volunteers. The left side photo shows that. And the timeline taken home and encouraging discussion with family members about preparedness and evacuation method. Information about the school DRR education is shared with parents through the school website and newsletter. And the right side shows my disaster prevention action plan for flood and sedimental disasters. We call Nigekito, and this material provided by MLIT. And next one is the challenges and outlook. As shown in, fundamentally the school in Japan formulates safety management plan and conduct disaster prevention education according to a manual created by prefecture. The town school education division instructed to school to conduct virtual evacuation drill for flood. So the school will implement them start to next fiscal year. And next is discussion. Providing expert knowledge and its effect can provide expert insight into how disaster happened, can help provide students' ability to predict and make decisions by deepening their understanding of disaster causes. And second one is promoting understanding of regional geological characters and its effects. And understanding regional geological features, for example, mountains, steep slope, river plains, and coastal areas, volcanic zones, to visually disaster risk. Deepen understand of hazard map to identify safer evacuation site and routes. Strengthen disaster awareness to encourage family discussion and community resilience. And this is examples which I performed or I provided the lectures at the school as a volunteer. And yeah, in top left, what type of disaster can occur in different terrains? In top right, helping them understand the connection between geography and disaster risk. For example, the right side one shows the blue line was the old river channel. So it can be very loose ground. Such kind of information is useful to think what kind of disaster risk is higher. Okay, so time is coming. So the conclusion is the school in Tochigi are improving disaster education by adapting training to local geography and working with families and communities. Challenges include limited staff and lack of specialized knowledge. And the geological engineers can support education by sharing their experience on disaster mechanism and local geology, helping students make better decisions and act effectively. Their involvement makes strength both understanding and practical disaster preparedness in schools. Thank you for your attention.
Thank you, Professor Hiromi Kaji, for this informative presentation. Now, due to time constraint, we are not taking any questions. Now we are moving to the next session, next presentation by Kui Duni Lane on the topic tips to draft a manuscript and have it published in a Journal of Mountain Science. Thank you.
Good afternoon. Yeah, good afternoon, everyone. I'm the Executive Editor-in-Chief of Journal of Mountain Science. And today, as the time is limited, I'll make a brief introduction to Journal of Mountain Science and give some short guides on how to submit your manuscript to Journal of Mountain Science and prepare your manuscript and submit your manuscript and make a revision. Yeah. We are in Sichuan Basin, in the Chengdu Plain, neighboring the Tibet. Our Sichuan province is surrounded by high mountains. So the journal was founded in 2004 and based in Institute of Mountain Hazards and Environment under the Chinese Academy of Sciences. This journal was included in Science Citation Index since 2007. And now it has been indexed more than 20 internationally important databases such as Scopus, CSCD, CABI. And from here we can see the journals developed fast. We published the journal in quarterly before 2010, and then from 2011 it's published in bi-monthly, and since 2016 it's published monthly. The salient features of the journal is we have international science teams and authors. Our editorial members from 32 countries and authors over 100 countries. Our reviewers also from 100 countries. This is our editorial members, internationally famous scientists, and the young scientists be our scientific editors handling manuscripts. And authors, many famous scientists or distinguished scientists have the papers published in Journal of Mountain Science. And the aim of this scope is we focus on the mountains, the world's high mountains and the surrounding ecological ruins. We publish interdisciplinary research papers integrating natural sciences, engineering, and social sciences. mainly to serve mountain planning or biodiversity ecosystem services, also livelihood in mountain areas. We also published mountain hazards, eco restoration, and risk reduction in key project construction in the mountain areas. So we have 4 columns. Each issue we have 4 columns: mountain hazards, mountain environment, and mountain development, and ecological engineering. The 4 columns each issue. The key topics in these several columns, the key topics such as mountain hazards, we published the papers on debris flow, landslides, collapse, or rock falls. And mountain environment, we published papers on land use change, climate change, or mountain geochemistry, mountain ecosystem, and plant response to extreme climate conditions. About mountain development, we published the planning strategy for the mountain development, also mountain livelihood, mountain landscape, or mountain tourism. And in mountain ecological geological engineering, yes, we published the geological hazards, engineering, safety, and risk assessment, or disaster prevention and reduction in the mountain areas. The archetypes, the most of the major types is original article and review article. We also published several discussion and later, and also some editorial materials. And the handling, the publishing period from submission to acceptance, usually within 4 months. Usually, the time from editorial checking is 1 day for checking the file completeness and do cross-checking. That means to subject the manuscript for plagiarism cross-checking. And for 1 week for initial review. In this stage, about 30% of manuscript will be escape off, will not be sent for peer review and directly rejected. Maybe it's because of the high similarity index or lack of novelty or poor organization, something like that. And the peer review, after the initial review, the editors will send the manuscript for peer review. It usually lasts 40 days or within 2 months. And from acceptance to production, it's usually within 1 month. We follow publication norm standards and codes such as the governments or the state governance department. It has requirement on the journal's basic conditions, and we follow international standards such as the format and the units and many other aspects. And also follow the ethical codes about the reviewers, about the authors and the editors. We have these listed in the author guides. One can read the author guides and follow it. And we take measures to maintain the healthy academic ethics, such as authenticate, cross-check. All manuscript will be subject to anti-plagiarism checking. And then email address and affiliation should be filled in. That means if the manuscript has 5 authors, each author's email address and affiliation should be filled in. And then the manuscript center will send email to every author of this manuscript to inform them that this manuscript has been submitted to Journal Mountain Science. and every stage of from submission to acceptance. Every author can receive email notification. And we take a double-blind peer review policy. And manuscripts are usually managed by editors from a country different from the authors, or at least from different institutions. Usually, at least one reviewer are from the country outside the authors. We require the authors to recommend at least three reviewers, but we are very cautious of whether to invite the author recommended reviewers. Our editors will check the background of the recommended reviewers and decide whether to invite them for the peer review. The journal take hybrid with hybrid open access rate. That means the authors can choose open access or subscription. If you choose subscription way, the authors need to sign copyright statement. Some institutions, over 2,000 institutions from European countries, from some Middle East countries, and from the American countries, their institute has agreement with Springer. So the authors don't need to pay the open access fee. And they just, we just ask the Springer to check whether the institutions are within the agreement scope. This is, I show the reviewer distribution around the world. In the 12 years, we have about 7,000 reviewers to make review for Journal Mountain Science. And this is our authors' distribution around the world. And from the past over 10 years, the journal has developed fast, I think. In 2010, we received only 78 submissions and published 40 papers. But last year, we received 877. And this year, we received about 1,000 submissions and published about 300 each year. From the impact factor, last year the impact factor is 2.5, and the full text downloads in Springer, just in Springer link, the full text downloads in 1 year is about 200,000 articles. We promote in the journal and promoting our cover article in many international conferences around the world. I just show them in many places, in the European countries and in the South American countries, or in other American countries, and also in China, many places, promoting the journals and solicit quality manuscripts. Yeah, this is the way we also, our editors were departing international training in the United States or the Italy and in Japan, and we held editorial board member meetings in China, and we invite our board members to visit China or hold training in some university in China. And this is, I show in the past 10 years, we have held dozens of scientific writing training around China in many universities. Yeah, this is some scenarios about it. And each issue, we select cover articles cover article, and the authors provide pictures, the study area, and we select the best one as a cover picture. And then the authors write a cover story. On the back cover is the cover story. The authors introduce their study area and their article. In this way, it will enhance the cover article's impact, and will also promote the cover article in our social media. This is the cover. This covers from this study area from different parts of the world. Yeah, this is the website. The website you can use search engine Google or Bing to search the journal name, Journal Mountain Science. You can be directed to the website. This is in Springer's website. We also have another website in our institute's web. It's the first letter of geology, JMS dot, and the behind part is our institute's the name, URL name. And this is the manuscript center. From the Springer or from our institute's website, you can direct to this manuscript center. And before you prepare your manuscript, you need to read the author guides carefully, such as about the aim, the scope, and the article categories, and the manuscript structure. And all these guides carefully, and prepare your manuscript following the guides. And the paper structure is like this. You can follow the guides. And for submission, the authors need to prepare two documents. One is a title page. It includes the author's information because we take a double peer review policy. So please include the author's information, such as the author's name, email address, affiliation, funding, or author contribution into the title page. And including another part, the main document. This is the sent for peer review, such as the title, abstract, keyword, text, and figures tables. The rest of things exclude the author's information. And after a manuscript is peer reviewed, the authors should make how to back. I can't back. Is it back? Yeah, should make prepare a segment document to prepare a point-to-point response to the comments. And about a call for papers and a call for scientists to join us. We will upgrade editorial members every year. Usually we select distinguished reviewers and authors to join our editorial members and scientific editors group. And we also need reviewers to make review. Nowadays, it's difficult to find quality reviewers, so join us. And I call for special issue. We have some two special issue course papers. One is Advances in Sediment Collectivity and Sediment Dynamics Assessments for Mountain Geohazard Management. Another is Mountain Hazards and Resilient Mitigation. The third one, the geotourism in the mountain areas. Thank you.
Thank you, Professor Kui Duran, for your nice presentation. Now, this session is over, and it's time for dinner.
Yeah.
Time for lunch.
May I have your attention, please? We'll just take about 2-3 minutes for the certificate distribution, and I would like to request Professor Dr. Kumud Raj Kafle to please come up on the stage and provide the certificate to our invited speaker. No, Nomura Sensei, please. And now I would like to request the presenter to please come up on the stage to receive your certificate.
Professor Hiromikaze. And Professor Kui Dunlan.
We will now take a group photo of all the speakers. It's okay. Yeah. Boy? Now I would also again request Professor Dr. Kumud Raj Kafle to provide the token of appreciation to our convener and the rapporteurs, please. Yeah, you two can go. No, no, you two can go. Thank you everyone for joining this session. The lunch has been served outside, so we'll be back in this hall for the next technical session at 2:30. And if you have presentation today, we would like to request you to hand over the PowerPoints to the volunteers who are outside with the laptops. Thank you so much. start is on landslide. It's landslide, debris flow, and rock flow, and with the sub-theme formation of landslide reconstruction, mapping, modeling, and prediction under different influencing factors, Asian monsoon, climate, and climate-induced hazard. And for this session, I would like to request Lucas Powell to please take the seat as the convener, and Mr. Pawet Kaur as the coordinator of the session, and also Mr. Mohammad Khairul Islam and Bhavana Kharka as a reporter. Thank you so much. Over to you, sir.
Thank you. My pleasure to lead the session and to welcome the first speaker, Professor Mike Windsor.
That's excellent. You didn't hear my bumbling introduction at the start there. So I'd like to thank the organisers for the opportunity to come and give you an invited lecture this afternoon. I'm going to be talking about debris flow risks to roads and road users. This is going to be a very much truncated, quick run-through of the John Mitchell Medal lecture, which I gave now 3.5 years ago, I think. So have we got a pointer? Okay, we need a pointer. It's not there. That's why I'm asking.
Oh, really?
No. Can you slide, change? Okay, so. Right, so what I'm going to try and cover today is just a very brief look at impacts of debris flows. Then we'll look at qualitative regional risk assessment with the hybrid between fatality risk, socioeconomic and loss of utility risk. Quantitative risk assessment in terms of fatality risk, and quantitative risk assessment also in terms of socioeconomic risk, but also to some degree infrastructure loss of utility. So it's quite a lot to get through in 20 minutes. Here you can see two events that happened in Scotland now 21 years ago. This is probably where our big journey with landslides and debris flows really started as a transport organisation, but also as a group of people who work for that transport organisation. Over a 2-week period, we had some fairly substantial debris flows. Some of them, as you can see on the left there, actually ended up at the bottom of the road as a debris flood. You can tell by the limited damage that's there. But these caused some quite significant problems. Very, very similar to what you see in other parts of the world. This is an example from Busan in the Republic of Korea, which happened 5 years later. And this one went down from the position you can see at the top there, through down towards those blocks of flats you can see on the left-hand image, underneath the car park area, which was on piles, and down the hill where, of course, flatland becomes very, very in short supply, and the roads become narrow, and the cars that it actually picked up became essentially entrained particles, and about 7 people were killed in that event. This is the same event. You can see the scale of that construction. I've worked out why the pointer doesn't work, because this doesn't have a pointer, unless it's going to do, no, it's not. But here you can see another one. This is the Zhoushu debris flow in Gansu in China. 1,750 fatalities, and 2 debris flows came from high in the mountains, and from that right-hand picture coalesced and went straight through the town. And on the left, you can see the aerial imagery from before, and as you can see on the right, those flows have carved a fairly substantial pathway through the actual town. And as I said, 1,750 fatalities. which is far from insignificant. So, back to Scotland, where I live and work. Following on from August 2004, we've talked a lot about rainfall and climate change today and yesterday. But that August 2004, we were about 300% of the 30-year average. Perhaps more importantly, the rainfall radar gave us slightly higher resolution to that. So about 20 kilometers from one of the events, we had about 85 millimeters in the storm event, of which nearly 50 millimeters happened in 20 minutes. At the peak intensity of nearly 150 millimeters per hour. And that's really important because at that time we were seeing quite a lot of antecedent effects. And over the last 20-odd years, we're seeing far less antecedent effect and far more storm input. But this started off a regional assessment. It was initially GIS-based susceptibility. As you can see in that right-hand map, it was the entirety of Scotland that was covered. And it enabled us to effectively identify sites of potential high hazard and indeed eventually of a sort of low-key risk assessment, which simply looked at the amount of traffic and the difficulty of diversion around it. There are some sites, of course, where we simply have no diversion. And you can see on that far right map, that's what Scotland looks like when you plot all these on. You can very, very clearly, most of them are in the northwest, which is where I've spent most of the last 20 years working. But what that really did for us, that was useful, and we could do some low-level actions like education, we could do some signing, but what it really allowed us to do was focus in on the higher-risk sites so that we could do more quantitative risk assessment. And because this is a much more complex, much more detailed process, you don't want to be doing every single site. So we were able to pick our sites. So this was some work I did with a chap called Jeffrey Wong from the GEO, who was on secondment with me from Hong Kong. And we basically set up our risk equation as probability of the event, annual probability of the event multiplied by the probability of a vehicle being hit given that event, multiplied by the probability of a fatality given that hit. Now, you do have two scenarios. One is a vehicle being hit by debris flow as it goes past the event. And in that case, you've got very much two different things. You've got the temporal and the spatial probability of being in the wrong place and the wrong time together. And the same thing applies, of course, to a vehicle hitting a debris flow that's already on the road. One thing I will say about this is on the right-hand side is bring it up. I've shown that as very much a linear process where we aggregate the two scenarios together. It's actually really useful to calculate the risk from each scenario separately and then combine them at the end. It's a very, very informative process. So we picked our sites and essentially we calculated potential loss of life from the hazard and the traffic data. You can see this is a site called the Rest and Be Thankful, which you'll see a few times during this lecture. Length of the site is about 1.7 kilometers. It's probably our most important landslide site, well, not just in Scotland, in the UK, without a shadow of doubt. The other one was Glenogle, which you saw a picture of earlier. Longer site, but probably lower hazard level, without a shadow of a doubt. Now, we can work through, and I don't have time to work through it today, but we can work through the personal risk. But what we're really interested in is the societal risk. So the personal risk is the risk that if I drive through that site in my car once in a year, I will be killed by a landslide. Now, fortunately, those risks are actually pretty low, so we're not worried about those. But we can use those to develop the frequency number, so the number of fatalities on that x-axis against the annual frequency of n or more fatalities on the y-axis. And we don't have a pointer here, but you can see on the right there for the Rest and Be Thankful, the dark line is the aggregated probability for both scenarios, whereas the yellow is the scenario A, a vehicle being hit by a landslide. Green is scenario B, a vehicle hitting a landslide. Now, when we first saw this, it gave us a little bit of pause for thought, as you might imagine. But at that time, and this was about 2014 when we were finishing this, there'd been quite a lot of mitigation work installed at that particular site. So we actually went through the bow tie process and actually took account of that. And that brought us very much into the ALARP zone. So a little bit of comfort there. Moving on to another site, and there's a bit more of a story about the rest to be thankful coming tomorrow morning in one of the other sessions. We have another site which is actually at, oh, right, okay. Yeah, it looks as if my cycling pictures have been destroyed, copying it across. It's actually one of the main tourist sites in Scotland. It's a place called Glencoe. And we have the traffic that runs through the site. It's much the same, pretty similar traffic flow to the site at the Rest to be Thankful, within a few hundred vehicles per day. But what we also do is we have 2 car parks where people stop. Some of them put their walking boots on and go for a hike, and then come back and change out of them, go away again. Some of them stop there and have a picnic, but we also get buses. And as you can see on the left there, you see 2 buses there. There's a lot of people there. My old guesstimate from sort of drive-bys and odd stops over the years, but we might actually have up to 200 people at some points in the car parks. The hazard assessment for this was actually pretty straightforward because we had quite a decent information. The elements at risk was really complicated because we didn't have any data at all. So when I first left paid employment, I actually spent 4 days in August, September, October 2019, and 1 in January 2020, counting people in the car parks for 12 hours for the day, which is great fun. But what's really fun is when you actually start looking at the numbers. That bottom left diagram shows that at one point we have 280 people in the car parks combined. Now, that's a lot of people. That's a pretty high exposure level for me anyway. And I would say the pictures you can see on the side there, they're all taken during the quiet parts of the day when I've actually had time to stop and do something else, rather than just counting and then finishing a count and then starting up again. But if you look at this site, and we use those numbers, I should say, on that previous slide to actually aggregate up and try to work out. Normally, we would use, for traffic, we use something called AADT, which is the annual average daily traffic. What I did was effectively make a new metric, AADV, which is annual average daily visits of 15 minutes. So if people were staying there for an hour, they would be AADV4, for example. And then use some fairly well-established tourist data for the northwest of Scotland as a whole to spread that across the different months. And this is characteristically different to a road. A road, we've got a central point, the risk is or the probability of a fatality given a hit is pretty much the same wherever you are across the road. Here, we've got a slope, the debris flow comes down, and if you're on that slope and get hit by the debris flow, you haven't got much chance. So the probability of you becoming a fatality is probably about 0.9. If you go to the bottom of the slope, you've got a bit more opportunity to move sideways, so it comes down a bit, probably not as much as you'd like. Once we get to the road, we've got the people in the cars, we know what it is from the previous work, the previous 2 sites. We've then got buses stopping, and some of them are letting people out on the roadside, and in which case there's probably a pretty high fatality risk. Others are letting them out away from the road where they're a bit more protected, lowering that probability. You've then got a flat car park where the debris flow will slow, so your risk is coming down further. You've then got a wall which protects you a little bit more. Somebody suggested to me that actually these figures were too high because everybody could run across the car park, jump over the wall, and go down the hill. Well, actually, I would dispute that to a significant degree. And the reason for that is it is very steep, it's quite unstable, and I would say it's actually significantly higher Plus, a lot of the people who stop in these car parks are mobility impaired, shall we say. So that's not going to be an option for them. So I don't take that. So we can actually get, for calculation purposes, a nice sort of average-ish figure of about 0.01 for P fatality hit, which, thank you, allows us to put all this stuff on the diagram. So you can see in blue, that's Glenogle, which is well within the ALARP. We've then got green, we've got the rest of me thankful, which is slightly unacceptable zone. We've got the dash green, which is where we've taken account of the mitigation measures. We've then got the brown, which is for the traffic in Glencoe, which is the site we're looking at. We've got the yellow line, which is for the people in the car park. Add them together, we get the red line. We have got some substantial numbers inside the unacceptable zone here. And not only are we in the unacceptable zone, but we're in the unacceptable zone for the higher numbers of fatalities. So there's quite a lot of work going on there as a result. So, conscious of time slipping by, that's fatality risk. That's probably the thing that scares us all most about these events. What gives us most hassle, grief, day to day, is actually the socioeconomic impacts. And we can divide those into direct economic impacts, the cleanup, the repair, the search and rescue, and so on and so forth, which we can quantify fairly easily as long as we do it soon after the event. We've then got the direct consequential impacts, which are, they're more about the loss of utility, so it's about the cost of the diversion, it's about any additional cost to likely traffic accidents, and so on and so forth. The third group we have is the indirect consequential economic impacts, and these are the ones that really give us most grief. These are the ones where people tell us that they are losing money from their business because people can't access it, they can't get in, they can't get out, so on and so forth. So we broke it down to three lumps. As I said, the direct economic impacts, well, they really come down to what's happened. So it could be anything from, I mean, the one in red is actually for a flood, so I'm just going to ignore that for today. But it can be anything from a few tens of thousands right the way up to 1, 2 million, and these are all returned to 2012 costs. Similarly, with the direct consequential impacts, we have a model which we can use to determine these. The numbers are quite variable. The one that's proven most useful to me over the years is the one on the far right, bottom right of the top table. So the daily cost of a closure at the Rest Me Thankful is about £90,000 to society. The third lot, the socioeconomic risk, is really interesting. We did a lot of work with state of preference surveys with my transport economic colleagues, and really when we got the data back, we could almost interpret it in any way we wanted. It wasn't very successful, but what we did get was, on the left, we took the words that people had used in the free-form parts of the survey and pumped them into what used to be called Wordle. I can't remember what it's called now, but it basically counts the number of similar words. So on the left there, we have the 85 Glenogle event, which is pretty much in our lifetimes a one-off. And people were talking about the landslide, it had an impact. Oh, we couldn't get deliveries for a day or two. But in all honesty, the words were fairly positive. The one that always springs to my mind is there's a bike hire shop in the next village along. And they said it was the first time ever in 20 years of operating they'd had all their bikes out on a single weekend. So they were making money hand over fist compared to usual. The one on the right is Rest Me Thankful, where up until 2014 we were getting at least one disruptive event a year. And you can perhaps see there's a little bit of a change there. It's landslides road, visitors lost, time, closed, customers, deliveries, they're all negative. Guests, people can't get in or out. So this has proved a really useful little tool for just trying to understand that. And I'm going to skip the flood bit. So, okay, quickly, infrastructure vulnerability. This is something that's sort of come out of the seismic arena. These are called fragility curves. We're still using the same equation as we were for the other assessments, R equals H times E times V. It's a really useful method of defining vulnerability. And this we did as part of an EU FP7 project a few years back. It's quite a few years back now. I think it was published, 2014. It's there. How about that? And we developed these curves. Now, if we were to start again, remember this first time we'd do it slightly different, we'd get slightly different answers, but we tested them against events in Korea and indeed Scotland, and it seemed to work pretty well. So that takes me to conclusions. So the impacts are potentially pretty severe. We've got lots of tools available to us, and we need to engage not just the clients, but the public, the politicians, to actually determine what their risk assessment needs are. And I think, given we're on time, I'll stop there. Thank you.
Yeah, thank you. Thank you very much for your presentation. I think we have time for one or two questions.
Namaste, I'm from Tribhuvan University. I have a questions. What hydrological threshold have proven most reliable for predicting debris flow? Yeah, rainfall.
We've developed a number of rainfall models. I mean, we started out with the deterministic one, which we first published in about 2006 and then kept adapting, improving, refining till about 2010. But at that point, we switched to a probabilistic model using Bayes' theorem. So that allowed us to take account of not just events that cause landslides, rainfall events that cause landslides, but also rainfall events that didn't cause landslides. It's almost like you're coming at the threshold from both directions. Since then, we've actually switched to a saturation model, which the operating company are running, which seems to work fairly well in the context of operating the road. I did say there's a bit of a story about that AH3 Rest Me Thankful site, and the story is that basically, since 2014, the hazard level has gone up enormously. We're now seeing, where we were seeing maybe one landslide a year, frequency about 0.8 to 0.9 to 1, maximum about 1,000 cubic meters. Now we're seeing about 2 landslides a year, but the magnitudes are now in the tens of thousands of cubic meters of some of them. Some of them are still small, but others are much bigger. So the risk has gone up quite substantially. We've done quite a lot of work in terms of mitigation, but at the minute I'm involved with a project where we're designing a 1.8 kilometre long debris shelter and wall so that we can trap the debris behind and then remove it after. So things have moved on. So that suction model is no longer fit for purpose for the construction. So we're now looking at installing things like permanent LiDAR, permanent GBSAR, so on and so forth. Long answer, short question.
Any other question?
I have a short question. Probably your risk assessment should be concentrated on 3-4 months of the summer, yeah? Not
no.
annually. Yeah?
Why do you want to concentrate on summer?
Because of the summer rainfall in our climate, no? It's concentrated in between June and July.
Nope. This is the west of Scotland. The annual rainfall, off the top of my head at that site, is about 3,600 millimetres. And while there are variations between months, there's not a lot between these. It's sort of like this. If you look at the east of Scotland and go back to 2004, then, and this is the east of Scotland, not the west of Scotland where that site is, July and August would be by far away their brightest months. If I now look at the last 30 years of data to 2024, that is no longer the case. We have a very flat profile, slightly more rainfall in total. Slightly more rainfall in total, but the July and August dominance has disappeared completely. So now we have October is just slightly above the rest. I think July and August rank about 3rd and 5th. So really big changes in just 20 years or so.
Thank you very much. My name is Paweł Kroch. I will be a co-leader of the session because leader of the session will have a presentation now, so he will not introduce himself. Professor Łukasz Pawlik from Poland, from Silesian University. He will talk about our research about landslides in Vietnam.
Okay, thank you. Thank you, Paweł, for this introduction. Welcome, everyone. My name is Łukasz Pawlik, and I'm from University of Silesia in Poland. It's my pleasure to be here and present some initial results of our project on landslide susceptibility. No, that's fine. Yeah, thank you. Yeah, today I want to focus on the geomorphic features of some interesting landscape in northern part of Vietnam. This is a part of a larger project which was financed by National Science Foundation. We focus in this project on landslide debris flow and flash floods events, and we want to find some hopefully some regional and local scale relationship between rainfall amount, rainfall intensity, and features which you can find analyzing soils, analyzing weathering profiles, and doing laser scanning in Vietnam, and relying on some satellite data in order to detect landslides and build machine learning models, and then construct landslide susceptibility maps. The main aim of this project is evaluating spatial and temporal clustering of mass movements and disasters related to this kind of mass movements, and isolating the key contributing factors triggering those events related to hillslope instability and dynamics. Vietnam is well known as a hotspot of landslide activity. Here you can see some summaries of data, global scale, which points to higher or high landslide density in this part of the world. Of course, these data sets, they are not complete, and they require regular update in order to build better models, and in order to give some more reliable predictions of landslide activity in this part of the world. And as we know that climate change is an important issue, and according to the latest IPCC report, this part of the world will experience growing rainfall intensity. In terms of 10-year and 50 years event, it can be much higher than it is observed nowadays. According to some recent machine learning analysis, we can see that of course rainfall is the most important factor which triggers landslide in this part of the world and in other parts as well. But we want to focus on geomorphic features and geomorphology in order to find some features which can help spatial distribution of landslides in this part of the world, in northern Vietnam. And what we can see here, elevation can be seen as quite important factor if we train models based on large data sets. But we in this small part of the project, we want to see much closer and to analyze relief of this part of Vietnam much closer. Why geomorphology? Because rainfall data is quite sparse. It is not so easy to get dense rainfall data sets, but digital elevation models are much more accessible. Availability of these data sets are much more widespread than rainfall data sets, especially in high temporal resolution, like hourly or daily temporal resolution. So within this project, we have 4 main aims or questions. We want to answer one question which is related to geomorphology. What were the geomorphic conditions and how did they impact landslide formation in the Hobon and Hajiang provinces? So we selected 2 study sites which were affected by landslide in 2022 and 2023, and then we conducted some basic analysis and statistical testing between those 2 regions. This is the first study site, which is in Hobon commune. The elevation range is up to 2,000 meters above sea level. Then drainage season is May to October, and of course 70% of annual rainfall is related to monsoon season. This is the most important factor bringing high rainfall totals in this part of Vietnam. And then average temperature is around 19 degrees, and mean annual rainfall range is up to 2,000 millimeters. As you can see here on this right-hand graph, that landslide event which resulted in more than 500 landslides. It was related to very intense precipitation, hourly precipitation, which happened in 5th August 2022. Our second study site was in Xuan Minh commune. Here we have elevation range up to 1,200 meters above sea level. And then rainfall intensity is much higher. Rainfall range is much higher than in Hobon commune. And again, these landslides were triggered by very intense rainfall, which happened in September 2022. Geology is, generally speaking, geology is very similar between the sites. We based our analysis on manually vectorized landslides. We use as a base map, planet base map data set, which is 5-meter resolution, and some of them were also mapped using Google Earth software. So what we mapped initiation zone, we mapped accumulation zone, and then we constructed a data set for two different study regions, and we tried to compare them in terms of geomorphic features. This is our methodological approach, which was mainly based on digital elevation model, which was acquired from Amazon Web Service terrain tiles. And our analyses were based on workflow which we constructed in R. First, we downloaded the dataset using Elevat R package. This dataset was resampled to 4-meter resolution, and then we calculated some geomorphic indices like first it was slope height, of course, slope aspect, and then we also calculated based on polygons which we mapped from PlanetScope. We calculated basic feature of those landside polygons like length, like minimum and maximum elevation, and surface of each polygon. Then we extracted information from raster layers using points within each polygon. So we were able to get even much higher data set using this method of extracting specific values of geomorphic indices based on those landslide polygons. Here are examples of maps of geomorphic features which were calculated based on DMs. The first study site, which was Hobon, we mapped 992 landslide. The accumulating area was 2 square kilometers, and the mean landslide size was around 2,000 square meters. And for Xuanmin, that event in 2023 resulted in 509 landslides with a total landslide area of around 3 square kilometers, and the mean size of landslide, it was 6,000 square meters. And for that data set, we try to find first some differences between sites, which could help us to build better models. We think geomorphology is important in this kind of situation, and what we can see here, here we found in all cases, in all indices, and landslide feature, the differences were, statistical differences were significant. So for instance, for elevation maximum, and then elevation difference between the maximum and minimum point of the landslide body, landslide size, then landslide length, elevation, and slope height, which is the difference between the highest ridge and the surface bottom of river valleys. Now it's time to follow with some general discussion and conclusions. Of course, both regions are very active. We know that rainfall is the most important triggering factor in these places. However, there are other factors which can contribute to landslide activity. Here, we are going to analyze soil properties as well and weathering profile properties. But here we also add some information about geomorphology. The slope height and elevation were greater for Hobon, and this difference between the study sites was statistically significant. In Hobon, landslide formed predominantly in a higher position over 750 meters above sea level, and slopes exposed to northeast and south, which were characterized by slightly higher topographic wetness index, which is, I think, a good indicator of soil moisture condition, a potential soil moisture condition, which can be used as a factor for modeling. And then such features like landslide area length and elevation difference were greater for Xuanmin area. And then values of the maximum elevation of landslide scars were greater and significantly different from those in Xuanmin. The main conclusion in terms of these two study sites is that in Hobon we have smaller and shorter landslide in higher elevation, and the situation is opposite for Xuanmin. I think the good explanation is that, of course, some people can argue that landslides are predominantly caused by human impact or road infrastructure, but we also need to observe that with higher elevation, I think road density decreases. So maybe this factor is not the most important one in terms of landslide size and density. So what we have here, we can speak about a concept of landslide pulses, which are largely stochastic in nature. They follow rainfall intensity and sums, which are not necessarily a direct outcome of atmospheric dynamics itself. So for instance, for machine learning modeling, we normally consider several factors, and then we come up with some interpretation in terms of their importance. So we acknowledge that rainfall is very important, especially in monsoon climate, but we are trying to find some geomorphic features which can also explain the complexity of landslide dynamics in this place. We also know that vegetation cover, human impact, topography, and the stage of soil development are important. However, when we have a high rainfall intensity, those factors can be not so important when they reach extreme levels. What we have here, we have landslide clusters, which are quite common in different parts of the world. And these clusters can be related to extreme rainfall events, but also geomorphic features of the terrain, which we analyzed here, and we tried to find some regional differences of these features. The insights of the present study can contribute to landslide modeling, as the regional differences in the geomorphological characteristics need to be taken into consideration. And as a final note, I want to acknowledge support from National Science Center from Poland, which allowed us to conduct this study in Vietnam. Thank you for your attention.
Thank you very much, Łukasz, for the presentation. We don't have a lot of time, but maybe one short question from the audience. Yeah, Mike.
Thank you. It always troubles me when I see some sort of susceptibility assessment when lithology or geology has a very low factor, but presumably that's because, in this case, you've got a very consistent lithology within the area you're looking at. The factors you gave in some of your earlier slides, lithology was well down the list, 0.04, compared to the peak of 0.12, which always sort of troubles my geology mind. And I wonder if that's simply because in this area, the lithology is actually quite consistent. Yeah, thank you.
Yeah, that might be the most important. Sorry. Yeah, that might be the most important factor, because it's homogeneous geological pattern. That's why the importance of this feature is not so high.
I have a small announcement to make. Whoever has a poster presentation outside, I would request you to please stand by your posters. And who participated in the workshop, like pre-conference workshop, your certificates are at the registration desk. So we request you to please kindly collect it before leaving. Thank you.
Okay, thank you. Our next speaker is Dr. Paweł Kroch from the University of National Education Commission in Poland.
Thank you very much, ladies and gentlemen. It's a pleasure to be here. I would like to present more, let's say, lighter maybe topic. I'm geographer and geomorphologist, also as the Professor Łukasz that he presented our detail results. But I would like to give more questions maybe than the conclusions in this presentation. How to look at the landslides in a regional scale. When we have a huge diverse of the landforms that are really difficult to classify. That's why I would like more, maybe not the present. Of course, I will present landslide topology, maybe the sketch of the landslide topology. We would like to improve later on, but to point some obvious thing actually, that landslide topology is a tool, but it is. We have a lot of typologies in classifications, but still they are not good enough to talk about the very specific areas that we have in Vietnam. The area is quite interesting from the landslide point of view. Most of, maybe even more than 90% of the landslides in this area are connected with the monsoons or typhoons. We had field campaigns in the last 3 years in this area. This is a very prone for the landsliding area because of the very huge amount of the wind, wet air masses that are coming from the ocean to the area, to this area, and the elevations are quite big also, because the highest peak of the Vietnam is more than 3,000 meters, and the valley just nearby the China border is 70 meters above the sea level, so the denivellation of the slopes are really big. So after these 3 campaigns, we've seen dozens of landslides, of course, and 14 of them we sampled and observed more detailed. But our friends who are better in modeling are starting to thought and model, of course, the rainfall trigger, because, of course, this is the main triggering factor. But I would like to point to the problem of regional looking for the very diverse landslide types. As you can see in these two landslide areas that was caused by a rainfall in 2022 and 2023, we have hundreds of landslides. Most of them are quite small. Most of them are shallow landslides, but anyway, the landform are very diverse from each other. What is the problem I would like to present? It's more question than a problem. We have a very popular Verness classification of the landforms, and this is worldwide known and worldwide accepted, actually. But in our situation, we have a problem that the main trigger rainfall causes that the soil, rock masses, or whatever it's sliding down through the slope is getting very strongly saturated, and it's getting to be airflow. Actually, it depends how it doesn't matter actually how this landslide starts. It almost always ends as an airflow, sometimes debris flow. So, in fact, in the best known and well accepted categories worldwide, we have only one category that fits maybe 2 categories: airflow and the complex one, to hundreds of landslides that we have seen in Vietnam. So the problem is how to classify them if actually we can say that 90% of our landslides are complex type. Yeah? It's not very informative. The classification is very good, worldwide accepted, but it do not give any answers for our problem that we are trying to look regionally on landslides in this North Vietnam, but we cannot talk about the group of landslides, in fact, using the categories that they are well known. So the scientific problem is that we have a lot of landslide classifications. One of the landslide researchers have written not far ago that he calculated more than 150 different landslide classifications worldwide in the history. Most accepted is Verness one, of course, but anyway, is there any need for getting new classifications if we have so many already published? So the easiest answer is no. But the existing classifications did not give any answer for us in our study sites in North Vietnam. So worldwide accepted classifications are very good, yeah? But actually all the landslides you can see on the pictures, deep-seated, shallow, small ones, huge ones, clusters of landslides, all of them are classified actually as a complex one. So we trying to use the classification like this, we are getting no information. Yeah? So in a regional, of course, point of view, because if we are staying just in we are analyzing one landform, it's not a problem if we call it landslide, landslides, or debris flow, whatever. We are focusing on one. But if we are trying to look at regionally, then we are getting quite a big problem. From our point of view, the features are the most diverse thing, the landforms that we have observed, is the type of the bedrock, if it is solid bedrock or deep weathered tropical soil cover in these areas, or if the permeability of the bedrock is quite important factor that it's really difficult to evaluate before the landslide, but after we can see the signs of the other processes that are very strongly connected with this factor, and of course if it's shallow or deep-seated. So very basic things, but if we compare all these three basic things, we are getting some kind of classification that allowed us to say what type of the landforms we can face in our study sites. As you can see, this is a sketch of typology, because any classification systems would not accept to make a one type for a one study site, of course, as you have in three examples here. But anyway, the depth of the landslide, the permeability, and its bedrock differs the landslide so strongly that it influenced also, in our point of view, from our observations, it influenced the transport zone because the amount of volume of the transport material have erosional strength or sometimes have not. So we've made these 5 types as a sketch for discussion, of course, for later discussion. But anyway, it allowed us to group somehow if the biggest differentiation actually is between two first types, where we have a shallow landslides, but some of them are on a barrow rock, usually on a granite, sometimes metamorphic rocks, and some of them are just 2-3 meters, first 2-3 meters of the soil, where deep weathered soil cover is much deeper. And as you can see, these classes are most often, and it is quite logic if we have a rainfall induced landslides, of course. But as you can see, also the typhoons and monsoon rainfalls causes deep-seated landslides in North Vietnam. They are much rarer, and as you can see, we have only 4 examples from 14 better studied as deep-seated ones, but they happens also. And so these classes are, of course, the sketch, but I would like to show you, not to present the solution, because it's not finished yet, definitely, but rather to discuss if we maybe should to do some landslide typology or classification inside the area that we have a monsoon and typhoon landslides, mostly shallow ones, because the diverse of the types is huge, but in the same time we very often do not know what we are talking about if we are comparing different areas that we have in quite close area between Southeast Asia. Why do we need such a classification? Such classifications can allow us to point for the secondary triggering factor. And why this is important? Because, of course, the main triggering factor is monsoon or typhoon rainfall, and amount of the rainfall as a triggering threshold is the most important thing to find, and that's why so many research teams are working on this modeling. But we would like to point also that there is a lot of secondary factors, geomorphological mostly factors, that they are very important in generation of the intensity of the landsliding in different catchments, different valleys. Because, for example, as you can see on these 2 pictures, we have a quite intensive suffusion or the piping underground that concentrate the rainfall on a impermeable sliding surface. On the lower picture, you can see that actually this is a deep-seated landslide that were activated 2 days after Yagi typhoon last year. So it proves also that the piping, very difficult to recognize on the surface process, it was one of the main processes that have caused the concentration of the water that infiltrate the soil and then concentrated after 2 days and caused the landslide. So Going to the conclusions. The main trigger is, of course, the rainfall, but the special distribution of the landslides are not based on the rainfall because it falls similarly all over the region, actually. Of course, there are some spots that the rainfall is much more intensive than on the other, but actually, if we have a few catchments just nearby, of course, they've got very similar amount of the rainfall during the monsoon or typhoon rainfalls, but we have completely different react of the environment from the landslide point of view. And that's why we would like to point that these geomorphological and definitely secondary triggers are responsible for the special distribution of these features all around the Southeast Asia, where we have a contact with rainfall-induced landslides, definitely. And very often, usually, actually, we are forgetting about them because we are treat them as a secondary, because they are secondary. The main trigger is the rainfall. But anyway, if we would like to look at the problem from regional point of view and also try to build some kind of sustainability mapping or hazard mitigation or hazard zonation, we have to take into account the very basic geomorphological processes, even if we have a very advanced modeling of the rainfall threshold, because the special distribution is definitely led by secondary triggers. And in the morning, Scott Anderson said that the professionals nowadays focus on how and why, not on what and where. Actually, in our area, the question where is very important, because one catchment is very influenced by a landslide, the second one not. And through the question where, we are going why the landsliding is so important, is so influencing so strongly one catchment, and just nearby mountain is completely untouched by these processes. Thank you very much for attention.
Thank you for your presentation. I think we have time for 2 questions. Okay, no more questions. Hey, one question.
Thank you. It's a nice presentation. Here is only not a question, just my observation or queries. Rainfall major triggering factor. This is on the rainfall or other antecedent rainfall areas?
Definitely, as we observed the last 3 years and talked with our colleagues from Vietnamese Academy of Sciences and Technology, definitely 90% of these landslides are rainfall induced. There is no earthquakes there. There is no other triggers that they are common, for example, in Nepal or in Taiwan. But yeah.
Like in Bangladesh, 441 millimeter in one day, that major landslides occurring in my case. But there is such type of amount rainfall, or this is 6-7 days rainfall accumulated?
Usually, this is as in there is quite big difficulty with it. There's a very scarce meteorological station in this area in the Vietnam, so we don't have very exact data about the rainfall. But as was in the Łukasz presentation, you had a sketch. The most important, usually, it's a cumulative rainfall. And the cumulative amount was about more than 430, as I remember. And the last rainfall was about 160, I think, in Hobon place.
And this accumulated.
But for 2 weeks, it was accumulated for more than 400.
Yeah, in this region, that's why I told this Bay of Bengal, in the monsoonal region, this not also antecedent rainfall and major one-day rainfall is main triggering factors for landslide. Thank you.
Thank you.
Thank you for the discussion and for the presentation. And now please welcome next speaker, Alexander Strom.
So, dear colleagues, I and my colleagues want to discuss the problem of the potential hazard assessment of the Sarez Lake, one of the largest and most hazardous landslide-related sites. How it, okay. So the Sarez Lake was formed in 1911 when about more than 2 cubic kilometers of rock collapsed from the slope and blocked the Murgab River valley due to earthquake. The lake is up to 500 meters deep nowadays and contain about 16, 17 cubic kilometers of water, and the minimal freeboard is about 40, 50 meters above lake level, depending on the season. And the main problem with this lake at present is the so-called right bank landslide. Yes, here it is. So, in 60s it was found that there are evidence of ongoing slope deformations on the right bank, not far from the dam itself, and that if it would collapse, the wave can, it was supposed, assumed, the wave can overtop the dam and cause some significant damage. So the problem is that recently there were several publications based on INSAR data, and they showed, here, that there are several areas close to the dam that demonstrate ongoing deformations. And the main problem is that these areas are very localized, because INSAR show us not only where movements occur, but also show us where they do not occur. And it is unlikely that so concentrated large areas with ongoing deformations reflect shallow superficial movements. Because why these movements, if they are shallow, why don't they occur somewhere nearby where the geological structure and material are more or less the same? So most likely that these are deep-seated deformations. And in 1986, the deep borehole was drilled at the base of this sliding surface, and the assumed sliding zone was revealed at a depth of a little bit more than 200 meters. So with an area of about 5 square kilometers, the right bank slope could be of the order of half cubic kilometers in volume. And the left bank landslide that activated after 2015 earthquake that occurred not far from here is smaller, about 20-30 million cubic meters. There are some evidence indicating that there is not some combination of translational and rotational slide. And it also supports the idea that it might be rather deep slope failure. So, the problem is that well-grounded assessment is complicated by the very high level of uncertainty, practically of any aspect of this complicated problem. There is no direct data on, except data on this slope motion about the internal structure of this right bank and also left bank. There is no direct data on the internal structure and grain size composition of the dam itself. Thus, neither numerical numerical nor physical modeling of these phenomena cannot be justified, and its correctness cannot be tested beforehand, before something would occur. So, to assess what might occur here, we analyzed natural analogues of the events that can form this hazard chain. I mean, landslide, impulse wave, overflow of the lowest part of the dam bridge, and catastrophic outburst flood. So, the first question is, if this, at the moment, slow-moving slope could convert into catastrophic slope failure due to an earthquake, for example, how fast this huge mass could enter the water body. And according to analysis of several case studies where velocity of sliding was either measured directly or could be estimated from the data on the run-up of the material on the opposite slope, which can be calculated using this formula, we can say that more or less roughly the velocity of the rock mass that could enter if right bank slope will fail could be of the order of 160 to 100 kilometers per hour. And here are some relationships between slope height and velocity and volume of velocity. Of course, it is very rough estimate, but anyway, better than nothing. And here we can see the next question is, how large could be the wave if half cubic kilometers of rock or something like this will enter the lake? It is the aerial views from drone of the Buria rock slide, rock avalanche that occurred in 2018 in December, and the slope was not very high. It was 300 meters only, and volume was 25 million cubic meters only, but the wave was 90 meter high. And you can see the trace. It swept the taiga forest for about 3 square kilometers area. And most of large, so-called mega tsunamis, which height exceeded 50 meters, were caused by landslides. And we know some other example. It is the 2018 Baige landslide. It was collapsed twice, and the first one fell just into the river, not into the lake. But the splash of water on the other bank was about 140 meters high. The highest one, the famous Lituya Bay 1958 event, it was not so large, at least initially, about several 30 million cubic meters, comparable with half cubic kilometers, but the wave was more than 500 meters high. So, these examples arise doubts upon the conclusions based on the numerical modeling that were made in several reports, that even if slope will collapse, the wave will not overtop the dam, which is only 40, 50 meters above the present-day lake level. And very good example is the Vajont. When Vajont landslide was recognized, it was pre-computer era. Italian colleagues made a physical model, and they modeled what will occur if this huge mass will fall into the lake. But final result, when it really occurred, the wave was 7 times higher than it was modeled. So it showed the problematic of modeling when we do not know all conditions. 7 times more than 200 meter high wave. And so, if it will really occur, all this wave will cross over the lowest part of the dam, which is around 800 meter wide, and all this water finally will concentrate in the narrow gorge, which is now eroded through the downstream face of the dam, of this natural dam. And actually nobody knows how this canyon will react on such amount of water. How deep it is clear that some additional erosion will take place, but how large, how deep, and how it affect the overall stability of the whole dam, which nowadays is considered to be stable. And what can happen if such wave will really overrun the dam? It is the photo of the IAEG dam close to Almaty in June 7, 1963. It is a prehistoric dam. There was a beautiful lake, a place of resort near Almaty, and it was composed of diorite with big blocks on top. And there was a powerful debris flow that entered the lake, caused waves, and these waves, when they swept away these big boulders from top, it was found that the inner part of the dam was composed of very heavily fragmented material. And then further erosion was very fast, and it practically completely cut through the dam. The dam was 200 meter high and caused disastrous secondary debris flow. And it is another example. The problem is, again, nobody knows what is inside Usoy Dam. There are several hypotheses, but based on numerous natural analogs, we can anticipate that inside the Usoy Dam is heavily fragmented material, and it is a natural analog, Köfels in Austrian Alps. It occurred in prehistoric times on the slope composed of gneiss, and its size is quite comparable with the size of Usoy. Not so high, but more or less similar volume. And on top, we see these big blocks, meter-sized blocks of gneiss, and in the erosional gorge, we see same gneiss crushed sometimes up to powder. And this internal material cannot survive turbulent overflow if the upper carapace, blocky carapace, will be removed. What can happen if, again, if the dam will be breached? It is the example of prehistoric rock slide dam, about 300 meter high, that was found close to Kyrgyz-China border in Chinese territory in Aksu River Valley. The dam was about 300 meter high. The lake was about 2 to 2.5 cubic kilometers in volume. And there are, we can see some traces of the outburst that left, can be seen till now. And the wave was 120 meter high and 700 meter wide on top. And peak discharge calculated by one of colleagues from United States was estimated as of the order of 1 million cubic meters per second. And this lake is 7 times smaller than the Usoy Lake, Sarez Lake, sorry. And so we can say either even the probability of all this hazard chain is low, the possible consequences are so high that risk cannot be considered as acceptable. And monitoring, which is going on, will not save people in case of if something will happen. Maybe even if they will be evacuated. It is high mountainous area where they will go after. It will be a world-class disaster. And that is why, besides monitoring, some mitigation or prevention measures should be performed. And there was a most obvious way is to make, suggested many, many years ago, to make a bypass tunnel through this Shadao Lake and then just maybe to cut or it will be eroded itself through the left bank of this river valley. Because some suggestions that we can intensify the seepage through the dam is unrealistic. First, how to do it, and then it will be uncontrolled lowering. Here we can get the controlled lowering. And so, we need some implementation of some technical measures ensuring the Sarez Lake safety that will require, but the problem is that it will require long time to do it because the area is remote and hardly attainable. Though at present the lake is, and the whole system is considered as more or less stable, what will we do if any evidence of instability will appear next day, next year, next decade? To do something, we need time. And it means that measures aimed to remove this Damocles sword hanging over the entire Bartang Pan Jammu Darya River Valley should be performed nowadays when the situation is stable and when we have enough time, I hope, to do anything. Thank you for your attention.
Thank you. Thank you very much. In our session, there is one presentation cancelled. That's why we can to have a questions even if the speaker used all the 15 minutes. So there's any questions?
Yeah. Hello. My name is Hans Havenit. We have been working together for many years with Alexander Strom in Central Asia. I also have never visited the Usoy site because it is difficult to access it. While I've been working several years also in Tajikistan. In addition to this long-term mitigation measure with the tunnel, they have never been thinking about putting a series of cascading check dams downstream where they could use also maybe the energy from Murgap River or something like that?
You see, I don't think that it is reasonable. First of all, the cost to catch, let's say, 10, 15, or I don't know, cubic kilometers of water, it would be not a check dam. It would be Nurek-like dam, which will cost enormous amount itself. Then any dam there will submerge, or the area upstream that can be submerged should be left from villages. I think that economically, the most reasonable way is to construct the bypass tunnel to lower gradually, slowly, not to stipulate slope failure by our activity. I think it is the most efficient way.
Thank you, Professor Strom, for your nice presentation. In IAEG region, there are like tens of numbers of glacial lake. Should be the solution be similar, like tunneling the glacier lake to lowering the water level?
Sorry, are there any projects where lake levels were lowered?
Yeah, glacier lake, like it's like a time bomb in IAEG Hindu Kush Himalaya region. What could be the possible solution?
for glacial lake, similar to the landslide dam lake, or should we consider another approach for
Difficult
mitigation?
question. I think we will discuss, not to use time, we can discuss during the break. Thank you. Okay, thank you.
Okay, thank you very much. Okay, we would like to invite the next speaker. The next speaker is Niran Donald Cheng with high-resolution UAV videogrammetry for discontinuity mapping in a steep rock slopes. The floor is yours.
Thank you very much to the chairperson. My name is Nirandol. I'm from University Science Malaysia. So today we'd like to present on the high-resolution UAV videogrammetry for discontinuity mapping in steep rock slope. So here is my presentation outline. So let me start with the background of my presentation. So rock slope stability depends on the discontinuity such as joint, fractured bedding plane, and their orientation, spacing, and geometry must be accurate mapped for the relevant stability assessment. Conventional method like a scan line, we use the compass, limited in terms of the area that you can map, and also time dependent and unsafe in the steep slope. So UAV photogrammetry offer non-contact, high-resolution mapping, but it struggle in occlusion resolution loss as slope base, especially at the bottom part of the rock slope. And it's really on the ground control point in order for you to map it incorrect in terms of deep angle, deep direction of the rock slope. So this highlight the more adaptable and efficiency method to capture a complete discontinuity data set in complex terrain. So the problem statement is the stability of rock slope depends on accuracy of the mapping that you conduct in the rock slope itself. So however, traditional method like scan line, survey, and compass inclinometer is measure have a clear limitation, as I mentioned just now. So they provide a limitation in partial coverage, especially in the bottom part of the rock slope, and also the time consuming and operator dependent. In the area that has slope, they can be even more unsafe for the people to carry out the measurement in the rock slope. So most important, this method produce a sparse data set, which means they are faint to capture the full 3D dimension of the rock slope and geometry fracture of the network itself. As a result, the structure interpretation can be often incomplete or even missing some part of the rock slope. Why UAV photogrammetry has become a popular for non-contact method to produce a high resolution of the photogrammetry or 3D model, it still have several limitations. Fixed flight plan mean it a struggle to adapt in complex terrain, and occlusion in overhang or steep slope often leave gap in the data set for the rock slope. So the resolution also drops significantly at the base of the slope due to camera distance from your slope and also from the camera that you capture using the drone. On top of that, the method really on the ground control point for your drone or GPS in order for you to capture incorrect for the deep angle direction of the rock slope, which can be costly, time consuming, or even impossible to use in tunnel where the confined area that you cannot get the signal or GPS. Altogether, this gap limit its ability to detect discontinuity and assess slope stability. So here is the objective of my presentation. First one is develop UAV videogrammetry for workflow for high resolution 3D for rocks modeling. And the second, to implement a semi-georeference tool for accurate spatial alignment without GNLS in challenging environment, especially in the confined space like a tunnel. And second, and third, evaluate and compare structure characteristic and kinetic analysis from UAV videogrammetry, again the conventional photogrammetry. So the study area is at the Federal Road at Malaysia. So it's a cut slope with a 70 high and 50 wide. And the geological of this study is Semangon Formation, which consists some sandstone, shale, and characteristic steep rock slope with a variety geological and discontinuity pattern of the rock slope. In this study, we use the UAV videogrammetry with the DI Phantom 4. Instead of taking a still photo, the drone capture a continuous 4K video at 50 frames per second, which allow us to extract a very dense data set of image. We fly the drone at UAV free fly mode, means that the pilot could dynamically adjust the path and camera angle to adapt the slope discontinuity. This approach overcome the limitation of traditional vertical and oblique photogrammetry, which often lose the resolution at rock slope based on missed feature due to fly path that fixed fly path. Without this method, we are able to effectively capture overhang, steep, incline, relation area with a maintain high image quality using the drone camera itself. And also, the key strength of UAV videogrammetry is real-time adaptability, which unlike the fixed flight path, it allows us to adjust the terrain complexity as we fly. This flexible means that we can capture fine scale of geological and we can focus on the certain area for you to capture and record the slope itself. Compared to that conventional method often miss in that part. By recording from the multiple angle, we can document a fracture with different orientation, leading to highest point cloud density itself and better precision in fracture mapping. So this produce a more accurate 3D model of rock mass discontinuity. As mentioned here, it show a free flight videogrammetry, improve our vertical and oblique method, especially under overhang and steep terrace. And also we can apply this method in the tunnel that we have limited in terms of the space for the drone to fly itself, and in confined space where we cannot get the GPS signal. One of the key challenges in photogrammetry is partial reference. So traditional method, we use the total station or RTK. It's accurate, but it's often time consuming, costly, and impractical, especially in a tunnel or steep slope where instrument payment is difficult. And sometimes in the tunnel itself, we cannot get the signal. So to address this, we developed a coded target-based semi-georeference tool. It uses a 4-symbol coded target printed on A4 paper, which can be flexibly paid on the rock slope. So of course, and then we need to, they have some manipulation behind it for you to calculate the coordinate for the local coordinate. We have X value, Y value, and also Z value. So in this step, we extract the frame from UAV and smartphone video, and then we combine it together with a multi-videogrammetry. So we set the extraction as a medium step. So they have 3 for this. We have a small, medium, and last. It depends on the how much you want the resolution of the 3D model itself. And then which give you a 90% overlap between the frame and ensure a good picture tracking. So next, we remove the motion blur frame to keep only the sharp image. This produce a clean, high-quality image data set with exception for the accurate 3D reconstruction of the 3D model of the rock slope. In this step, we use a metashape to reconstruct the 3D model frame. We'll first align into the sparse point cloud, then refine in the dense cloud with the noise filtering using the semi-georeference tool, and then we need to key in the value for the semi-georeference tool of the local coordinate itself. And then UAV videogrammetry with the smartphone data will capture stability and consistent. Finally, mesh and texture will generate and produce a high resolution in terms of the 3D model itself and accurate to preserve the fracture and orientation for the analysis of the rock slope. So in this slide, show the improvement in the data quality using videogrammetry that we combine with the smartphone videogrammetry. with the conventional photogrammetry. First, the ground sampling distance improved from 5.9 centimeter per pixel in the oblique model to 0.727 centimeter per pixel in the oblique model to adjust. So this is the 21 time higher resolution. And second point cloud density itself increased from the 2,300 point per square meter to the nearly 40,000 point per square meter, giving us a much richer data set in terms of the for the analysis in terms of the fracture of the rock mass, and finally in terms of the accuracy. So the error that reduced from 0.88 millimeter to 0.4 millimeter, which means that UAV improved really great precision. So the result of videogrammetry provides a superior resolution, density, and accurate, enable us to really detect small fracture and compact of the rock slope, and also the orientation, and compared to the oblique photogrammetry of the mist on that part. In this part, we validate the semi-geo reference that we developed. So by the compare of 50 discontinuity plate measure in the field with those extract from the 3D model that we developed in the videogrammetry 3D model. In the result, that show mean that root mean square error 2.16 degree for the deep, and also 6.52 degree for the deep direction, which we fell within the acceptable limit for the geological operation. Looking at the error distribution, the angle error were tightly clustered with a mean of negative 0.3 degree, showing only slight underestimate for deep direction, and wider spread with mean of 2.33 degree and few moderate outlier. In this section, we compare the thread network extract from the both data set from the UAV videogrammetry and also the oblique photogrammetry. So we identify the 186 trace, while the oblique photogrammetry produce only 150 trace. In the different come mainly from the higher resolution of the 3D model and clear texture that in the UAV approved. So looking closer, the UAV data set capture 161 curved trace compared to 127 in oblique model. This shows the ability to resolve the curvative and complex geometry, especially in overhang or steep area. For clove liner trace, UAV data detect 2 pair, with oblique detect only 1. The visual compare also make this clear. Oblique photogrammetry often produce destroyed textures and unclear trace line, where the videogrammetry reveal a sharp texture of the 3D model. In this analysis, we use the Q-Prasad KD3 algorithm to extract the discontinuity for the both data sets. So the results show that the UAD videogrammetry detect 146 discontinuity compared to only 920 detect with the oblique photogrammetry. So that increase of nearly 60% in the improvement is due to the highest frame density, adaptability, and also the point cloud itself that generate from the 3D model of videogrammetry. So this advantage allow us to capture more small apertures and complex discontinuity that oblique method often miss. In this part of the study, we compare the kinematic analysis result between UAV videogrammetry itself and also the conventional photogrammetry. Using UAV videogrammetry, we detect 186 discontinuity and group in the 5 joint set, plus additional set X, which represent the orientation outside the main familiar in the group set, which represent orientation. And for oblique photogrammetry, we detect only 902 discontinuity and limited in 3 joint set only, compared to the videogrammetry that we detect 5 joint set. So looking at the failure mode, so UAD data set capture all 4 type: direct toppling, fractural, toppling, planar, and also base sliding, with a balanced distribution across multiple joint set. This show that the more comprehensive picture of the potential slope stability itself. On the other hand, oblique data set also show all failure mode, but the result will heavily concentrate in the few joint data set. For example, in J1 joint dataset contribute more than 80% direct toppling, while the J3 dominate nearly 50% of the fracture toppling. So to conclude that, so this research developed a geological workflow combined UAV and videogrammetry that be combined together. So and also semi-georuin tool enable high resolution and relevant discontinuity mapping compared to oblique photogrammetry. The method achieve much higher resolution in terms of resolution, in terms of the point cloud, and also the orientation accuracy, with the error when in the geotechnical tolerance. It also allows us to detect more joint set and multiple kinetic failure model. That's all for me. Thank you very much.
Thank you very much for your presentation. I think we have time for a quick question.
Thank you, Irandul, for the presentation. I'm Farouk from Malaysia. So I have a question between photogrammetry and also videogrammetry. How big is the difference between the processing time and the data capture time at the field and also at the lab? Thank you.
Yeah, actually for the videogrammetry, so of course they will be take a longer time, and also it depends on the skill of the pilot to fly the drone. But for you to get the more details, so that's why we propose the videogrammetry to capture. But if you focus more the last area, so that is possible also for you to use the fixed fly pan that you set on the any convention software. So for the videogrammetry, it focuses on the small scale that for you to get the more detail of the rock slope itself.
Okay, thank you. Thank you for the discussion. And please welcome our next.
Good afternoon, everyone. My name is Xian Wang, a lecturer of Chang'an University. Today, I'd like to share a research with you how the internal forests mitigate debris flow. I'll start by talking about why the topic deserves attention. Then I'm going to give you a brief overview on how the development was carried out. Finally, I will show you the results and the conclusion. Let's begin with talking about the background. Why we want to research internal forests. Firstly, because it is a natural phenomenon. In the internal time of debris flow activities, internal forests grow naturally. Most low Perkins debris flow channel contain forests. These trains, especially the trunk part, have the function of disrupt the movement and the depolarization of debris flow. The picture shows the field evidence from China and Italy. Secondly, for this disaster radiation needs, for pushing the development of nature-based solution in debris flow mitigation, scientists and engineers studied many bioengineering measures like the wooden cells and so on. In France case, after the bioengineering measures, the internal vegetation recover well after 3 years, achieving good effect on ecological restoration. The artificial structure similar to the forests like buffers had been extensively studied and application. But there are clearly differences between the forests and the buffers. Based on the data we collected, the buffers cover as is very different from the forests. Most buffers only have 1 to 5 rows, but the forests, most forests covers long channel, and the plant distance of buffers is very large, about 22 to 250. As a contrast, the plant distance of forest is small, only 1 to 14. In the view of controlling force, the buffers regulate debris flow with physical trapping the coarse particles in debris flow because they have a high plant density. But for instance, regulate debris flow with the hydraulic effect because they cover long channel and increasing the flow resistance along the channel. Therefore, it is necessary to research the internal forests on the regulating effect on debris flow. Here we can see the experimental setup and materials. The experimental setup include a three-part hopper, flume, and forest model. The first model is made of plastic, and I focused the function of tree trunks and ignore the effect of the branches and leaves. Here we can see the test arrangement and conditions. There are 14 cases with two sediment concentration of debris flow, 0.3 and 0.5. And there have 5 degrees of diameter of tree model, 1 to 5 centimeter. And there are 3 degree row spans, 8 and 16 and 32 centimeter. And in our study, there are 3 mean measured variables: flow depth velocity, the impact force, and the deposition landform. And there also have 4 mean dimensionless parameters: the resistance energy slope of the forests, the attenuation rate of impact force, and the sediment retention rate, and the base slope increment. Here we can see the pictures showing the flow process. When entering the wooded channel, the velocity of debris flow decreased where the flow depths increased. And finally, in the wooded channel, reach a balanced state in the new resistance environment. From the view of the resistance energy slope, there also have the following process. Before entering the forest, the resistance energy slope is closer to the channel bed slope. As entering the forest, the energy slope increases sharply. And in the forest, the energy slope decrease and the bed slope increase gradually. after that, finally, inner slope and the base slope became closer again. Here we can see the characteristics of the deposition. The deposition height decreased gradually from the upstream to the downstream, leading to an increase in the bed slope within the forest area. And the density of debris flow also have a clear impact on the deposition landform. For the various debris flows, the max deposition height was concentrated upstream of the water channel, the left one picture. And for the diluted debris flow, the max deposition height was concentrated in the water channel, the right one. Here we can see the impact force, accumulation rate, and the sediment retention rate, and the relationship between them and the characteristics of forests, like the trunk volume fractions, relative openings, and the resistance energy slope. The impact force attenuation rate was found in the range of 16% to 79%. And the sediment retention rate was found in the range of 3% to 32%. Both of them have negative connected with the relative opening, positive connected with the initial resistance energy slope, and the tree trunk volume fraction. We can see the first picture showing that proportional relationship between the bed slope increment and the initial resistance energy slope. Based on this, we established a method to calculate the deposition slope in the water channel, the middle one. After that, based on the simplification of channel landform, we established a new equation to calculate the potential sediment retention value. Finally, we evaluate the ability of natural forests to regulate debris flow. Based on the data we collected in the natural forest, the max value of trunk volume of fraction was about 1.4%. In this condition, the max value of impact force attenuation rate was about 61%. The max value of sedimentary retention rate is about 15%. The max value of bed slope increment was roughly 0.04. Here we get some conclusions and that I have mentioned before. Thank you for your attention.
Thank you very much for your presentation. Do we have any question? I can see, so I have one short question. In your testing experimental, you've made a very regular net of the trees. Did you try to experimental made a quite diverse spice diversification of the trees in your spot? In your study plot, yeah? When you've been studying, the regularity of the trees were very strong, yeah? Did you try to make it diverse like in natural forest?
Yes. We use dimensionless parameters to control the tree model and natural forest. It's a tree trunk volume fraction. It's a ratio between of the volume of the trunk and the all volume in the forest. Yeah, thank you.
Okay, thank you very much one time more. The next presentation will be from Matt Shalfkil Islam Sani. We would like to hear about evaluation of seasonal high resolution automated weather station.
Thank you. Honorable Convener and session chairs and the distinguished guest, thank you for giving me the opportunity to present my research work. My research work title is Evaluation of Seasonal High Resolution Automated Weather Station Data and its Impact on Society and Sustainability, a case study at Jahangirnagar University campus. So here is my outline. So today we'll discuss about the studies and there's in outline background of the study, aims and objectives, methodology, result analysis, key findings, and a recommendation. So my basic studies is based on some basic importance of our societies that are going to be some leading importance and significance. Like we know that climate is the weather pattern of a specific area over a long period of time, usually at least 30 years. Weather is short atmospheric condition that can change from hour to hour, day to day, month to month. Weather change on the dependent parameters on time, geographical position, land to survive, understanding, studying surrounding climate is important for humankind. Every year we face many natural calamities due to the abrupt climate change. So these are some kind of natural calamities causing due to climate change. So for the studying the seasonal variation of climate, we need data to summarize, analyze, and interpret the upcoming climate change effect. For a high-level study, Jahangirnagar University, Bangladesh, and Kago University, Japan made a collaboration to establish automated weather station under the funding of Ministry of Japan. AWS collects high-resolution digital data based on climate parameters. Here is the AWS established in front of the Jahangirnagar University Department of Geological Sciences. Here we can see there is a 3 sensor. One is Vaisala weather transmitter recording pressure, temperature, humidity, relative humidity, winds. And there is 2 pyranometer that select the solar long wave, short wave, and solar radiation data. And there is a central data compiler, CR300 series, which compile all the data, and the power is come from the solar panel. So these are the data came from this AWS machine. There is 11 parameters, and then temperature, wind speed, wind direction, air temperature, relative humidity, air pressure, precipitation, heat, and solar short wave, long wave, and radiation. I have picked the 7 parameters from here for my research work. So these are my aims and objectives. I like to examine in the seasonal variation of temperature, relative humidity, wind speed, precipitation, session level air pressure, and solar radiation, including temperature, short wave, and long wave data. So I will also try to, in my research work, to compare the AWS data with the historical climate data from the Bangladesh Meteorological Department and try to evaluate the seasonal heat wave, to evaluate precipitation pattern, and also the impact of this climate or an weather and seasonal change in the student and the public. So I have tried to survey among the JU student about the knowledge and the hazardous health hazard of their to make an outline and the and outcome from this. And I have also tried to collect Jahangir medical. There is a medical, so I have tried to collect medical data and reverse calculate to know what is they been gone through in this the several season. So I have collected BMD data Bangladesh Meteorological Department from 2014 to 2024, so 10 years data. And the AWS data established, the machine was established at 2023, and I have started to having the data from September to July 24. And the survey I have done, and all the data was analyzed in the competitor software, Microsoft Excel, and the simple data analysis software. I have firstly divided the season into these months. The winters I have divided into December to February, pre-monsoon March to May, monsoon June to September, post-monsoon to October to November. So here we can see the average temperature. First, in the left side, we can see the BMD data, and the right side, we can see the AWS data. So for the average temperature, there is little bit change. We can see the peak value of from the BMD to the AWS. So this pointer is not wrong. Okay, I can try to show it here. No, it is not working. Okay, the lowest temperature recorded in the 30 degrees Celsius in the winter season, and the highest temperature is recorded 36 degrees Celsius in the pre-monsoon season, probably the March to May. And here is the total average maximum, minimum, and the total average data, which is recorded by Bangladesh Meteorological Department. And here is the left side, we can see the AWS data, heat wave data recording, which is greater than 36 degrees Celsius. But in the BMD recorded data, we can see that there is no heat wave. Means there is no upper peak greater than 36 degrees Celsius. Here is the humidity data of 4 season, and you can see the peak value changing, the data resolution. The AWS data is recording per minute data, and BMD data is recording in their traditional ways. Annual average humidity data for the birds is 4 season, and the total annual graph is we are seeing here. Here is the average rainfall, the precipitation rainfall for 2014 to 2024. We can see the rainfall trend per year. Average rainfall is recorded by the Bangladesh Meteorological Department. And here is the precipitation pattern. We can see the per minute value is giving this very nice peak, the very regular data, and their traditional method is there is so many difference and variance. We can see also in the trending line. So here is the wind speed data. Left side we can see the BMD, and right side the AWS. So we can see there is zero data, which is the poor quality of data is indicating, and the high resolution data is here. The wind speed is also, we can see in the season that the post-monsoon, the wind speed is decreasing, and winter is increasing, and the steady is in the monsoon season. Here is the wind speed graph from the BMD data for seasonal graph, and the annual graph. Here is the analysis station labor pressure, the air pressure we have in our station. So this is the seasonal change and the variation of BMD and AWS data. We can see that the trending is going up at post-monsoon and steadiest winter, and decreasing in a monsoon season. There is the BMD data graph, seasonal. And here is the solar radiation data. We cannot see any kind of BMD data here because the Bangladesh Meteorological Department has so poor quality of recorded solar radiation data, so I didn't have any kind of data, so I just presented AWS data here. So here we can see a major drop in February 2024 to March 2024. So in that time, the sensor didn't receive any solar radiation directly because of the fog and the cloudy environment. So this was special from the winter season. Here is the solar radiation shortwave data. So I have found some from BMD. So I have tried to correlate it with them. So we can see that there is a increasing trend in the winter, steady in the pre-monsoon season, and the decreasing rate in the monsoon season. So there is the total 2024 to 2010 1-year solar annual shortwave radiation data from the BMD I have collected. And I have conduct a survey among Jahangir University students. There is this is an ongoing project. I'm still collecting the data. So from them, I have got 120 response, and these are randomly picked, and every batch and every different kind of faculties and the year students has been interviewed. From them, there is 83% of male and 24% female is contributed their response here. So I have asked some question. There is question is also here. In your opinion, how does the seasonal variation at Jahangir University, considering factors such as high temperature, without the use of air condition? So they have seen this. The 42% of them said there is really slight effect, and the moderate had 24% have responses. There is a moderate effect. In fact, the seasonal impact they are having in different kind of season. So I have asked them that how in which season you're having the most difficulty. So we can see that in pre-monsoon they having 37% of students having the difficulties, and 39% students have difficulties in the monsoon, and the mostly 32% students having the difficulties winters. One kind of difficulties they are having some illness due to the seasonal impact. So here is some illness that I have collected from their response, that if there is a seasonal trending is going, the change is affecting how kind of illness is like fever. In winter, the very much they have got the fever, same as a respiratory problem in winter, headache, fatigue, or allergy and skin problem. The maximum are the winter season. So we can see that the winter season have them winter season student having the more difficulties and the problem, and the less in summer season they are having the little bit slower. But the alarming issue, there is no record of them they are taking having 75% students have no kind of records of their health, and they did not go to medical center regularly. So there is my findings. These are about the health hazard, and these are the my recommendation. Thank you.
Thank you for your presentation. Have you got any questions? One question over there.
Thank you for your presentation. I have just a quick question. You said that plus 36 degree is as a heat wave. Is there any criteria you have followed for defining it as a heat wave? And the second quick question is related with your automatic weather station data as well as a survey. Are there any linkages, or there are like two different studies that you want to present together?
Sorry, I didn't get the second question.
The second part, my question is related with the survey that you did with students from your university, and you have some high resolution automatic weather stations. So are there any connections? How do you relate those two findings?
Oh, I'll answer the second one first, because the weather station was established in the campus. So I've tried study in my campus student the impact of the seasonal change that record in my automated weather station. So I tried to relate and correlate with the health hazard and the seasonal data recorded from the AWS. And you have, the first question was the relation between the heat wave. First question is heat wave. So there is a published paper that if the in our country papers, I'm sorry, there is a published paper which is regarding this heat wave. They have this minimum value, they have 30 degrees Celsius. So before it go, it is counted as a heat wave. So it maybe can we go upper increase, but the minimum value is 36 degrees Celsius wave, heat 36 Celsius temperature. I think you got the good answer. Thank you.
Thank you for your one more question.
I have one short question. Did you try to correlate the answers of the students with the weather?
Yes, I'm trying to
correlate. Yeah, I know, but if they were answering the survey during the heat wave,
yeah,
they feel that the climate change is more stronger than during the Primos,
No,
for
I
example,
have
time?
surveyed the month 2 or 3 before, and this data was collected from the 2023, the March and April, that Bangladesh goes under the heat wave action. So I have asked to them on their memory basis, and I have collected, trying to collect the Jahangirnagar Medical Station data to the prescription data they have prescribed to the student. The basis of them, I have tried to back uh, reverse medical data engineering, I think. So I tried to find out for the disease they are suffering, which it is in which season they is having the most of the disease, and which prescription they are getting. So I'm getting the prescription, I will make it reverse, and I will have the exact disease they are having and then I will compare with the seasonal weather, seasonal basis month which they are having the most difficulties.
I meant the different thing. If the student is answering a survey during the very hot temperature and he's sweating,
yeah,
the answers is different when they are answering in a 20 degrees
so
time.
when I surveyed,
because you know you are analyzing the answers comparing to the illnesses during the year, for example, but the answers differs from it depends, you know, how temperature is during the day. If you have very difficult day, damp day,
yes,
answering that the
yes,
climate is changing more.
Yeah. So this was difficult. So first when I was interviewing, I have to make them to get in flashback 2023 to back his memory and answer my question. So I have to first I have to make them understand that what I am asking, the exact question from that date, from that month. So it was really difficult. So I have only collected 102 data. I am targeting for 400 data. So it's an ongoing project I will try to make. Thank you.
Okay, thank you for the discussion. So now is the time.
Sorry, I have a small announcement. The poster session has started, so if any of you have a poster outside, I would request you to go and stand in front of your poster. Thank you.
Okay, thank you. Yeah, now is the time for our last presentation.
Yes.
Now is the time for our last presentation. Please welcome Sanjeev Regmi, who will deliver the talk on rim slope instability of reservoir and mitigating approaches. The floor is yours.
Hello, good afternoon. Honorable Chairman, Co-Chair, Rapporteur, and all the present here, and dear all. Thank you all, and it's my pleasure to present you on the title of Rim Slope Stability of Reservoir and Mitigating Approaches. And me and my supervisor, Ranjan Kumar Dal, is the author. And my content is introduction, project details, method discussion, conclusion, and recommendation. And it's my introduction, just what, why, and what are the factors, just like what is rim slope stability. As you all know, rim slope instability refers to the failure of rock slope burdening a reservoir. Unlike typical landslide, it is directly caused by the fluctuation of the reservoir, and it is artificial hydrological environment created by impoundment and operation of the dam. And what are the impacts? Impacts are failures can generate impulse wave, threatening dam structure, reduce reservoir capacity through sedimentation, and endanger upstream settlements and infrastructure. And what are the key driver of this are the water level fluctuation, rain infiltration, and especially geology, lithotypes, permeability, direction of the rock slope, and orientation, and all this. And in Nepal, it is important because in Nepal it has a big hydropower potential, and right now we are making big hydropower project. Many reservoir are building, high dam is building, and as you know, it's a complex geological setting, and so the instability along the reservoir threatens dam safety, as I already explained, and reservoir capacity due to sedimentation and endanger nearby community. And my study area is the Dutkoshi storage project, which is located in Khotang, eastern Nepal, and it is a given steep slope, and it is the physiographic map of Nepal. And dam's height is concrete fill, rock fill dam, and it is 220-meter high. And I do not go to the details of the project because my main concern is the river fluctuation of the river, and there will be 80-kilometer reservoir will be formed by building 220-meter high dam, and there is a Dutkoshi River, and alongside there is the Thotne River and Robua. These are the tributaries of the Dutkoshi, and it's a headbridge tunnel that you see that is 13-kilometer long, and there is a powerhouse, and it's a capacity of 670 megawatt. And what are the methods? The geological survey and a review of field investigation that I have done, and review of remote sensing analysis, review of geotechnical assessment, and my limitation is the rock mass classification. Rock mass strength is in Hedox area, that is high level that I have in, it's 80 kilometer. So I mainly focus on rock type. So I hope it could generalize the limited information and limited observation of the study. And it lies in Kuncha formation here in the eastern Nepal. It's a green color is Seti formation as per DMG, and project area is located in Okholdunga tectonic window, and main boundary thrust and south boundary thrust MCT is nearby the area. The main rock types belonging to the projects are quartzite, phyllite, paranite, orthonite, schist, limestone, and marble. And here you could see the two red line. This one represent the Dutkoshi River, and one represent the Thotne Khola River. There you could see the dashed line. It's represent the Lilamint. And in another second figures, the yellow quadrilateral is represent the dam site, and the red line represent the Lilamint nearby the project area. And there you could see the two rivers. One is Thotne River, Thotne Khola, and another is Dutkoshi River. This is the lineament density map. You could see the reservoir that I have already mentioned, 80 kilometer long. Lineament density map is prepared that exhibit the quantity of linear geographic structure on the surface. I hope this presents the main density orientation lineaments. All these red areas represent the high, and green represents the low. Nearby dam site area, there is a high lineament we could see, and when you go to the upper stream of reservoir, we could see the lineament gradually decreases. Here in the first figure, we could see also the dam and lineament and tunnel alignment is seen. It's a Google map, and it's aerial photo analysis as taken on this. This is the INSAR study, that is nearly, that is a tributary, the figure that you see the confluence of Dudhkoshi River and Thotni River, and that arrow shows that there is in the INSAR study, 2 points of the Majigaon are used for, Majigaon is the area that the arrow show, and for the moment of analysis for one year only. It's a limited data, sorry for that. Subsidence rate up to 15 millimeter were observed, which is quite significant movements. And this is the geohazard study, and the land, there you could see the landslide, landslide nearby 2020, and landslide in the range, that yellow, green and red color, you could see the landslide potential, geohazard density, you could see. And that is the figure that you see, the DGST, deep-seated gravitational slope deformation. Right now we have made a certain study in this. It is not threatening, but it is taken as, it is determined, diagnosed as deep-seated gravitational slope deformation. There is certain scarps over there, and detailed study were taken. And orange color that we see are the distribution of the landslide and distribution of the landslide of the area. There are three main types of potentially unstable areas were identified that I have already mentioned. Altogether, 15 landslides were pointed in the reservoir area, and deep-seated gravitational slope deformation that I have mentioned is only one, and erosional area is more than 50. That I have mentioned earlier, rock mass determined in reservoir fluctuation. If the rock mass is quite high, higher value of rock mass is more stable. So I take the data of Q value from 3 audit, which is on the upstream and downstream of the dam axis. These audit are 150 meter long, ER2, EL2, EL3. R represent right, L represent left of the dam side, and first figure represent Q value, and second represent RMR value. And we could see that it's a ranges between poor to good, and some person in the audit GNH there is poor, very poor rock or seen, but it is quite limited. I think it's poor to pure rock we could determine, and in the RMR value, the rock value ranges between poor to pure. And there is the changes that you could see on the horizontal axis, and Q value on the vertical axis. And there's the mechanism of the failure, and there is the probability of the percentage that I have shown. It's on the right bank of the river. The wedge failure is quite higher, and probably when the slope angle increases, it increases, and plane failure and plus toppling failure is quite, it's not increased drastically. And another figure, we could see the frictional angle with reference to the failure percentage. It so that if the friction angle increases, failure percent decreases. And that I have done on the right and left bank of the dam side. And what are the major factors and effects of slope instability? Factors and effects. Slope discontinuity orientation effect is slope failure, mostly modes failure accompanied by plane failure, wedge failure. And there is a drawdown in our river 125 meter fluctuation in one season. One season means nearly 6 months dry season. When the reservoir water level drops rapidly, the water inside the slope pores cannot drain quickly. If it does not drain quickly, it creates pore pressure, pore lagging, increase in pore pressure, and decrease in pressure, which both increase the failure, slope failure, and the rain infiltration effect is permeability condition. If the rock is permeable, it's go down, it decreases shear strength of the rock and decreases the and increases the potential of slope failure. And what are the mitigation approaches? Is reshaping the geometry of the rock, proper drainage system, just like releasing pore pressure from surface flow, subsurface flow, and really making artesian well, relief well. And structure solution is there, returning wall, gap-in wall, anchor piles, and bioengineering is another technique that we could recommend. And what are the monitoring, instrumentation, and drawdown control and satellite monitoring are the measures and should be regularly monitored. And if instrumentation inclinometer measure the subsurface, you could determine the area is displaced or not, there is slope instability or not. And if there is drawdown control, we could reduce the chances of failure. If satellite monitoring, we could observe the monitoring what it is displaced or not. And my conclusion revealed that Dudhkoche Reservoir rim comprises risk slope zone, which are strongly influenced by geological discontinuity, monsoon rainfall, and anthropogenic disturbance such as road cutting and deforestation. Moreover, rapid drawdown conditions were found to significantly decrease slope stability due to released pressure and reduce effective stress. And impact of geomechanical structures, just like discontinuity, geomechanical structures like fault, dynamic reduces, RQD, RMS, GSI. Slope failure differs in block masses and disintegrated rock mass, and deep-seated gravitational slope deformation on the right bank of Thotnekola and slope-based displacement in Majigaon area are our main concern. And influence of rock mass parameter on slope stability. Rock slope stability depends on rock mass parameter like RQT jointing, which I have mentioned. And my recommendation is the slope management measure, continuous monitoring in INSAR inclinometer return, and slope drainage improvement, bioengineering stabilization, and control land use around the reservoir. Thank you for your kind attention.
Thank you very much for your presentation. Do we have any question? Yeah, we have there. Yeah, I can see. But on the back row was the first hand.
Thank you, Sandeep sir, for your wonderful presentation. You mentioned about the INSAR study, measuring ground upliftment. Right? INSAR study.
Sorry?
You mentioned about the INSAR study.
Yeah.
So, my short question is that which SAR data you utilize and which platform you utilize?
Thank you for a good question. In the INSAR study is quite limited. We are going detailed study in the project area. Right now it's the initial phase. In the INSAR study, the Majigaon area, which is just nearly 2 kilometers upstream, we see the displacement in 1 year, 15 millimeter displacement. And we are going to make a detailed study on this. Right now it is ongoing and we are going a detailed study on this. It's not completed. I've taken the review, okay, from our consultant. Any
Sandeep
question?
sir, I have a question. I'm Dinesh Raj Sharma, Tribhuvan University. In your analysis, what is your data source? Image, satellite image, or survey, or GIS data?
Yeah, I conducted geological survey, RQD, RMR, Q value that I make take data make data acquisition, and just like the INSAR study and other study that mentioned in RMR, and something that rock mass strength, all this are I extracted from our study of the project study detailed investigation. And yeah, satellite image from our consultant. Any question?
Any question? No more questions. Thank you very much.
Okay, thank you.
Thank you very much together with Professor Łukasz Pawlik. We appreciate your presence at the session, and we appreciate the discussion, because actually there were no presentation without question from audience that we wish to have such a score of questions in every sessions, because discussions are most fruitful. Thank you very much.
Thank you so much, Chair. Now I would like to request the Chair and the Co-Chair to please come on the stage for the certification ceremony.
Please come to the stage. Our invited speaker, Mr. Mike Winter. Please come to the stage. We have a certificate for you. Then, Mr. Alexander Strom, please come to the stage.
What about you?
Okay, the next speaker, Fatin Nadirah Ahmad Pauzi is here. Okay, the next one. Mr. Nirandor Cheng, please come to the stage. We have a certificate for you. Thank you for your Mr. Kian Bank, I will have you. Thank you. Mr. Shafiqul Islam Sani. Mr. Sanjeev Regmi.
Now I'd like to request Dr. Anne Williams to please present the certificate and token of appreciation to our chair and co-chair, and rapporteur also, please. Yeah, maybe first with the certificate. Yeah. she's giving the token of appreciation to the session chair, co-chair, and rapporteur. Can we take a group photo with all of you, please? And also, I would like to request the presenter to please come on stage for the group photo. Thank you, everyone, for the wonderful session today. And it is the last session for the day, and we will meet here again tomorrow at 8:30 for the keynotes. Thank you.